Good afternoon, everyone. It is 2 p.m. in the Netherlands and we are live. Today is the beginning of a groundbreaking era in photonics. The team of Fleet Events and the team of Epic have been working extremely hard to make sure that we provide you an experience as close as humanly possible to the traveling and photonics networking. The whole point of these 2 afternoons will be for all of you to get to know each other better. And I have the honor and the pleasure and the energies to chair the keynote session today. And it's quite fascinating. We have a program combining keynote users for most of the application fields that photonics is making a huge difference. Today, we're going to have fiber sensors, semiconductor manufacturing, MicroLEDs and micro-optics, and beyond 400G. And honestly, I can tell you that when we hear from companies such as Fibersail or Siemens or ASML or Electrolux, OSRAM, Volvo, Cisco, or Telefónica, is going to be fascinating, but also even more fascinating when we ask them the so much famous EPIC question. What can they do for the 685 members of EPIC, and what the 685 members of EPIC do for them? And let's see how we can start new cooperations. I really can't wait. But before we start, I would like to acknowledge the amazing work that Fleet Events and Epic has put together to make this happening. We're going to fight against the radio frequency waves. We're going to fight against fiber optic communications, and we're going to make sure that you get the experience. Be patient, things are gonna work, and we trust on the World Wide Web not to be an obstacle today. But with this, I would like to start with one of my biggest passions in the world, and that passion is fiber sensors. We have been at Epic exploring the market of fiber sensors on every application field, from medical to structural health monitoring. And one of the biggest push that we have observed in fiber sensors have been the wind turbines and the wind energy market. So we try to scout a company that actually is making a difference on that market using fiber sensors, and we found in Portugal the company Fibersail, and they are looking for partnerships in fiber sensors. This is a huge opportunity for the companies developing fibers, interrogators, or they're doing system engineering of AVG sensors. Let's see what we can do with them. Pedro Pinto, CEO of Fibersail, thank you so much for being the opening speaker for this keynote session. The floor and the attention of everyone in Photonics Plus, and that means the whole world, goes to Portugal, goes to Pedro Pinto, goes to you.
Okay, José, thank you very much for the introduction. It's a pleasure to be here. So, good afternoon to everyone. My name is Pedro. I'm the co-founder of Fibersail. And this is our vision. Rotor smart wind turbines that can predict when a blade will need maintenance. This will help to reduce operation and maintenance costs, especially on offshore operations. Also, smart wind turbines that can detect rotor imbalances. This will help to improve the performance and reduce risks of failures during operation. And thirdly, to help optimize the lifetime by controlling the blade loads. This will help to understand what is the remaining lifetime at each moment of the operation. At Fibersail, we believe that this is not just possible, but also feasible in the near future, with the right technology, the right team, and the right partners that we have. So let me show you how this works. Wind turbines are today getting taller. The blades are getting longer. We just saw the new blade getting 108 meters. This means that very critical structures will need to operate for the next 20 years. Now, the problem is that composite structures, due to the manufacturing process, are unique. All of them are different from each other. This means that different structural behaviors can lead to vibrations and imbalances on these rotors. There was not the need up to now to monitor the blades in a very deep way. This is why, like most of the components of a wind turbine are very well monitored today, but blades, not yet. This is the right moment. Why? Because now the blades are getting longer and operations are getting further away in the offshore.
Pedro,
So
we really want to see you when you speak because you look fantastic. Is there a way that you could click on the camera icon just next to, just at the bottom of the corner, the camera icon? So when you say, there you are, you look much better like this.
Okay. Perfect. So, thank you, Jose. Okay, so from now on, it is critical to have a very reliable and extensive data analytics to better predict and optimize the operations and maintenance of these offshore turbines. So we are a Portuguese-Dutch startup company. We have researched at the engineering faculty of Porto. We own IP for blade shape sensing technology, and we are backed by Portuguese and Dutch investors. The company is led by me. I have a background and expertise on wind dynamics. A couple of years ago, I was coaching high-performance sailboats in the Olympics. So I really understand how the wind behaves and what we need to get the perfect shape to get the highest lift from the wind. And together with me, I have Carlos Oliveira. He's an expert from the wind industry, and he's coming from one of the leading turbine manufacturers in the world. And both of us, we have the vision that wind turbines in the future will need to be controlled by the deformation of their blades. This will pave the way for a far more competitive wind industry. So let me introduce you to our solution. So we have developed a shape sensor that is installed from the root to the tip. So we can continuously measure what's happening in the blade from the beginning at the root until the end of the tip. With this information, we can analyze the structural behavior of each blade. And by detecting failure patterns, we can identify when an early stage failure is starting to happen. Now, let me show you the technology itself, how this works. So fiber optics and especially fiber brake gratings are here, have been used for the last 20 years. So it's a very well-known technology. What we came up with the idea is to use parallel arrays of FPGs and get a short distance between them, so we can calculate the difference between what we are measuring in terms of strains, from the top to the bottom, from the left to the right. So in this way, by using 4 parallel arrays embedded on a rectangular composite beam, we are able to measure the flap-wise and edge-wise deformation of a structure. And this also grants the robustness and reliability that the wind industry needs. So we need to remember that building a sensor to install on a blade of a wind turbine, it will need to stay there for the next 20 years for operation. So it needs to be very robust. And another thing that we need to remind ourselves is that a blade with 100 meters will have very huge deformations. So this means that the fiber optic sensors will have huge strains. So that's why we came up with a design of fixing it in one hand and not fixing in the other. And from the test that we've been doing, we are happy to announce that the sensors are using 1% of the maximum strain that it could get. So which means that we can ensure the entire lifetime. So you are imagining, okay, but what's the real big difference between what's happening out there and what we are doing today? So on the right, you can see how the fiber optic have been using on the wind industry. So they are placed on specific locations on the blades, normally next to the roots, and they measure strains. And one of the problems that for these strains, they are very dependent on the blade design and the mass for each blade. And that's some of the problems that we have overcome with our sensor. And another thing is that we are able to fit the sensor until the tip, even if the blade is already produced. So we can introduce it from the root to the tip with a closed blade already. So we are not only producing the sensor, the hardware itself, but also analyzing. So we are computing, we are simulating a lot of failure modes to understand which kind of patterns we need to identify. So let me show you an experimental test that we've been doing. So this is a blade with 24 meters. We installed 3 shape sensors. So one is a complete from the root to the tip. The other is just next to it, and another we placed on the root. We used an approach of a 3-step load and unload. So you can see on the left, on the tip position, the tip was going up during 3 steps up to 1 meter. And we were measuring in several points. So one of these is the ending point, and the other it was at the 84 point. So at 84% of the length of the blade. And these were the results. We did some dynamic tests also. So you can see that the tip was pushed and loaded in the beginning, in the bottom on the flap-wise. It was released, and we could start to see some dynamic response, and we could build the shape. During this dynamic response. Another thing that you can see is that we used 2 sensors distant from 16 centimeters from each other. And the reason is that the industry is looking and demanding for measuring the torsion. So by measuring most of the sensors in flap-wise and checking the difference, we could see the torsion along the length of the blade. So on the right, you could see what is the evolution of the torsion during the blade. Now the third sensor, it was installed near the root. We understand, and the industry understands, that the root has deformations, very small deformations, when the tip is bending flap-wise and edge-wise. Now these have impacts, especially on the connections between the blade and the hub. And these connections can bring some failures if they are not correctly monitored. So here we were able to show that we could measure deformation in the root, even with very small deformations on the tip. So for you to have an idea, the blade at 24 meter long, so we deformed at 35 centimeter in the tip, and we could detect difference of 1 millimeter on the root. And here we were able to understand the deformation on the root. So when the tip was going up and down, we could see a flattening and a more curvature on each side of the blade root. Now this shows here the potential of using shape sensors to measure what's happening on the wind turbines. So data platforms need excellent historical data sets to produce quality forecasts and analytics. There is no doubt that blade monitoring will be critical to ensure the life of these giant wind turbines in operation. Being the only technology to reach the tip, Fibersail is innovating on data quality to produce excellent forecasts and analytics and help to reduce the levelized cost of energy of wind power. With this, I end my presentation, and I'm able to answer any questions that you may have. So
thank you very much
for your attention.
Pedro, for the fantastic presentation, also for being one of the examples on how we can actually bring the shape sensing world into real life applications. And I'm quite amazed on all the discussions we had in the last 6 months since we first met, and who have seen the rapid development of Fibersail. This is not a surprise for you. You expect what's happening now. What is coming is the epic question. What can you do for the 685 members of Epic, and what can they do for you?
Jose, Thank you for the question. So we have been developing the technology. We are working now with manufacturers and operations. I can tell you that our first large sensor was installed a couple of weeks now in the Netherlands in one blade, and it will start in operation in the next 2 weeks. So it will be the first live data and real data that we will have. So today we can say that the technology is ready to start measuring real life structures. So we are looking to partners that are in need to better understand the behavior of their structures.
I have some questions in the chat, but before that, I would like to ask you something else. At the end of the day, any fiber sensor system, it has two things. It has a fiber and an interrogator. That's every fiber sensor system. Let's talk about the fiber first. You have already worked with many suppliers, and actually many EPIC members are talking to you at the moment. What are the challenges today in the supply chain to get the right fiber for shape sensing?
Well, Jose, at this moment, we are still, we have our own suppliers at this moment. We are doing some testing, but we always look at the future. So reliability is for sure one of the challenge that we have. We need to have not just the fibers, but also the embedding process on the composite. Everything needs to be sure that will withstand this very harsh environment. So testing accelerated conditions on the offshore, it's what we are looking now to the future to develop. So that's the challenge here that we need to solve, is how we can bring the technology to be very reliable and much more reliable than what we have today through our competitors.
You are addressing one of the biggest challenges in terms of reliability that you can face, which is the offshore windmills. Nobody wants to do any maintenance of those, and maintenance is extremely expensive, and we want to reduce it. Of course, the fiber sensors are going to have a very, very strong structural health monitoring of those structures, so we are only going to have to monitor them. But how about the reliability of the sensor itself? Do you have some calculations of the lifetime of the sensor system?
Yes, that's quite important, Jose, and that's what offshore operators are discussing with us. They are not much concerned on the accuracy or the resolution, like getting 1 millimeter of difference on the tip. They are very concerned of, okay, we installed that, we cannot go there again to replace the sensor. So what we did is a 3-month fatigue test, accelerated fatigue test with one of the leading manufacturers in the world of blade producers. And we have been using that same sensor. It was the first one that we used. It went through a couple of million cycles. And in terms of fatigue, the sensor is still like it was in the beginning when it was produced. So one of the main points of our sensor is that it is fixed on one side, but in the other side, it's not very well fixed, so it can slide a little bit. This means that the range of wavelength shift that we have on our sensors is very small, very small. So we are talking about the range of operation normally in 1% of the maximum that it can support. So it's difficult to put fatigue on the sensor, and that's one of the main spots that we have here.
I have a few questions. One of the anonymous question is asking me, what is your wavelength? What is the wavelength of choice? And why did you decide on that wavelength?
Well, I would need, we are working with wavelengths between 1,520 to 1,580. The choice for that relies more on our R&D engineers. We would be very happy to answer, but we would need to place the question directly to the R&D team.
Another question.
I'm happy to redirect that question.
Another question in the chat: is there a possibility to combine shape sensing and strain sensing?
Yes, definitely. The thing is, strain sensing has a lot of information that we are not getting on the shape. So we see like our competitors that does strain sensing, not just as competitors, but also collaborators. So we actually are doing some conversations to see the potential to bring in connection both technologies, because both of them have different qualities. So yeah, it's very there is a huge potential to unite both technologies.
Pedro, I'm so happy to have met you, because thanks to you, many companies are really entering this energy market, and there is so much money put from the European Commission, so much interest on actually going to renewable energies. We're going to have soon a meeting on green energies. We're combining the photonics industry for the hydrogen fuel cells, for the solar, and of course for the wind. I want to have you there, Pedro. Congratulations, and keep going, keep innovating in photonics.
Okay, Jose, thank you very much.
Let's continue with the program. We started strong, but we are moving now even stronger. When people ask about the European industry, very often you hear the word Siemens, Siemens, Siemens. What is Siemens doing in photonics? What are they doing in 3D printing? What are they doing in fiber sensing? Our next speaker is Evangelos Diatzikis, fellow engineer advisory expert, sensor and advanced control at Siemens. And he's going to tell us what the EPIC members can do for Siemens and what Siemens can do for the EPIC members. And we're going to start cooperations. Evangelos, thank you so much for being with us this beautiful afternoon in the Netherlands. The floor and the attention of everyone goes to Siemens.
Thank you very much. I appreciate the introduction. I'm going to, let's see.
You look fantastic with the blue shirt. I love it. Evangelos, could you click on the camera icon so we can see you and also the slides at the same time to make it a closer experience?
Of course.
Oh my God, I can't believe I'm talking to Siemens. I get so excited. Yes, let's go presentation mode in the PDF. I think Control L does the trick. We're going to go presentation mode. Everybody's so excited to talk to Siemens. The floor is yours, Evangelos.
Okay, so you can see it in presentation mode?
I see it crystal clear, Gorilla Glass clear. The floor is yours.
Okay, great. Thank you very much. I'm going to talk a little bit today about one of our biggest products that we make, and that's our turbo generators, and how we came up with a solution in order to monitor certain measurands of the generator. And the three measurands that are very important for us for operation of the machine is vibration, temperature, and strain. Here you can see a cutaway view of one of our large turbo generators. And for vibration, it's very critical, very important that we measure the vibration on the end windings of the coils of the stator, as you can see here in the picture. Also vibration, we've measured the main leads on some of our customers' generators also. Temperature measurements are also important. The gas, most very large generators are cooled by hydrogen. So it's important to know the gas temperature coming into the system and exiting the system for recirculation. Also temperature measurements on the metal itself, on the copper, are much valuable. And of course, knowing the temperature in the stator, of the slot of the stator, is critical for operation of the machine. And then we also are interested in strain measurements. And internal to the machine, we like to know what is the strain value along the spring bars. And external to the machine, a very important measurement, what we call the frame foot loading, is to ensure that the generator is properly loaded on all four corners of the structure, so we don't have any imbalances, because most of these machines are running at very high RPMs, typically 3,600 RPMs in the Americas regions, etc. So the question is, how can we best measure these measurands, knowing that Siemens has been in the industry for over 150 years? And you can imagine that typical sensors that exist in the market are not applicable internal to the generator because of the very high electromagnetic fields and harsh conditions that are inside the generator. So we determined that the best type of sensors to use for these type of measurements will have to be fiber optic sensors. There's no question about that. And we looked at many different type of fiber optic sensing technologies. There's so many out there, and I'm not going to list all those. But what we decided was that the most appropriate choice in order to measure all three of those measurands with one type of technology was the use of fiber Bragg gratings. And the number one reason for going to a fiber Bragg grating solution was it's an all optical dielectric sensing. And they do have a very large broadband frequency response. And I mentioned the immunity to the electromagnetic interferences, etc. They're small, and compared to some of the other sensors, highly resistant to hostile environments. And the possibility of multiplexing these sensors was also a key reason for going with this type of technology. Of course, you know, we can have distributive measurements if you want to go with that type of networking of the sensor, or you can have a star type of distribution where you have one sensor going directly from the analyzer, and if you were to lose that particular sensor highway, you don't lose the rest of the sensors. I think for me personally, one of the most one of the best reasons for using a fiber Bragg grating technology is that the measurement is a spectral measurement. So we're measuring the wavelength of the reflected light from the Bragg grating in order to make the measurement, as opposed to other systems that use the intensity of the measurand in order to conduct the measurement. I think this is very important because it gives you a definite relationship between what is being measured and the value that you get of that measurement. And of course, as we mentioned before, we can configure the fiber Bragg grating sensors to either measure vibration, or to measure strain, or to measure temperature, and all three of those measurands can be measured on one analyzer. So I'd like to talk about a particular case study where Siemens, with the cooperation of our technology partner, HBK Fiber Sensing, we created a solution for an existing product that Siemens, through Westinghouse, before Siemens acquired Westinghouse here in the Americas, we had a fiber optic sensing solution. We called it an FOVM, fiber optic vibration monitoring system, for the end windings of our generators. And the original FOVM system that was deployed back in the mid-1980s used an intensity type of measurement. So when we decided to upgrade the FOVM system and go with the fiber Bragg gratings system, it completely changed the technology that we were using for the FOVM. But we had the experience of deploying optical sensors and running the optical fibers within the generator, and also exporting or feeding through the optical fibers through the pressurized generator, the big ones that are hydrogen cooled. And so we had to completely come up with a system that would be possible using the fiber Bragg grating. And the five major components that you see of the FOVM system are here, and going from left to right are the sensors, a pressure seal, an optical multiplexer, our fiber link cable, and the analyzer. And those five components make up the bulk of the FOVM system. The interesting part with the multiplexer is that, if you recall earlier in the slide where I showed that you can either have a star technology type of network where you have one sensor connected to the analyzer, or you have multiple sensors on one optical fiber connected to the analyzer. In our case, we have it's a hybrid system. We have one optical fiber that's connected to four fiber Bragg grating sensors. But if we lose that one fiber, we don't lose all of these sensors on the network. If we lose the fiber here, we only lose the four sensors, for example, in channel 2, if we lose the fiber here. So we found that this is a better type of architecture for us in order to mitigate any issues that you may have with any accidental cutting of the fiber or breakage of the fibers, etc. And the reason that we needed to monitor the end windings are because even though this is a very big machine, if any of you have ever seen these type of generators, they're huge and they're very heavy. They weigh a lot. There's a lot of iron, a lot of material there in those generators. But once those generators are up and running at the appropriate frequencies, they do move, and it's amazing to consider just how much motion that you get from the end windings of the stator coils. And so it is very important that we do not shake the machine too much, because if we break the insulation within the end windings, then we can have catastrophic failures. And so our designers, they determine through finite element analysis for a particular design of a generator where we need to be measuring the amplitudes of vibration. And then we determine where the optical fiber sensors will go. And through our software in the FOVM system, we have a modal interpolation. It's essentially a software program that tells us what is the mode shape of the vibrations that are set up in the end windings of the generator. And by monitoring the mode shape, the amplitude of the mode shapes, etc., we can ensure that we keep the generator running within safe operational conditions. And this is very important, because should a failure occur, you can have catastrophic damage, not only to the machine, but perhaps even to personnel, etc. And I'm showing some photographs here of some of these failures. This happened on a machine that was not monitored by Siemens. I don't even think this was a Siemens machine, but you can see when you have a short, for example, from one phase of the generator to another phase due to breakage of the insulation, let's say, then the protective circuits within the plant will isolate the generator from the grid. And so now you have all this energy that is being produced by the generator, and now it is cut off by the circuit breakers. And where's that energy going to go? That energy is going to go into destroying the machine. And you can see some of these photographs here that showed for this particular failure. You can see the machine here will have to be completely rewound, and this could be very costly, into the tens of millions of dollars to rewind the machine. So the benefits of having a monitoring system on such big machines are quite large, especially for our customers, because by adequately monitoring the mode shapes and trending the vibrations of the system, you can have an online early detection of the condition of the generator. And so what a customer, a power plant operator, what they do not want is a forced outage, because a forced outage means that nothing has been planned. There was an incident or an issue that comes up with one of their machines, and then they have to shut down the machine, and that gets to be very expensive, especially if you have not known beforehand that you need to shut down and do some type of maintenance on some very, very large machines. And we're talking about above a gigawatt. That would be a 1,000 kilowatt machine or a megawatt machine or higher. Shutting down for some customers could be very, very expensive, up to perhaps even $1 million per day of being down. And it's not only just loss of revenue for the customer, it's also the possibility of not being able to supply from the grid, from other producers, being able to supply enough energy for the end users, et cetera, like we're experiencing now here in Texas because of the severe cold weather that we're having. So we want to avoid these outages, these forced outages, and we also want to know what is the condition of the machine while the machine is running in situ. And with that, that concludes my presentation. Open floor to any questions.
Many questions, Evangelos. I have goosebumps. I'm talking to Siemens about my passion for fiber sensors, so I really I'm really gonna enjoy this. The first question is obviously, how many measurement points do you need to do for this ultra large generator?
Yes, typically All right. Well, let me go to the finite element analysis. Our designers tell us that with the minimum, we were able to determine the mode shapes with 6 sensors on each end of the machine. Imagine the other end of the machine. One's called the exciter end, the other end is called the turbine end. And in order to be able to adequately calculate the modal interpolation, 6 sensors is a bare minimum. But typically on our design, we have 8 sensors per end of the machine. And of course, you know, this has to be, as an engineer, you would say, well, 8, well, that's great. Why not 16? Well, why not 32? Why not a measurement point on the end windings every 2 or 3 centimeters? You can do that, but no customer is going to want to pay that kind of money, you know, for the installation, because it costs it costs money. So we have found that typically 6 sensors per end is adequate.
Another question. You already said that you're working with HBK Fiber Sensing. Luis Ferreira, from CEO of Fiber Sensing, you're watching. Hello, I know you're watching. When we are thinking is one EPIC member, AMS Technologies, actually has developed a project with Rolls-Royce for adding shape sensing to the turbines in an airplane. Is shape sensing also interesting beyond the measurement for strain, vibration, and temperature that you already mentioned?
It's my personal opinion that any technology that could be applied to better monitoring our machines is exciting for me. I personally have not looked into using shape sensing for this type of measurements, as you can imagine, but it certainly is worth looking into.
One of the key added value for you to use fiber sensing was the being completely independent to radiation. These wind turbines are going to get extremely hot, extremely hot. What kind of temperatures are we working with here, and is that a challenge when it comes to the fiber to choose?
For the type of temperatures that we typically see within the normal operation of the generator, this was really not a challenge at all. We did not have to use any type of special high temperature fiber Bragg ratings or high temperature fiber, you know, specially coated fibers like gold coated or some type of carbon coated or polyimide coated fibers. That was not necessary because we've often said if the temperature in the generator exceeds a certain threshold, it doesn't matter what kind of temperature sensing you have, you need to shut the unit down or run away.
One more thing, Evangelos. We are already in February, but I'm still going to ask you this Christmas question. If you could have a Santa Claus wish list, a Santa Claus Christmas list of a partner or a prototype or a need, a challenge to further monitoring the generators, what would that be? I know it's a difficult question.
You know, every different technology has its pros and cons. And for example, we're exploring strain sensors using white light interferometry, because interferometric measurements are extremely precise compared to other sensing technology. And we know that we have fiber optic interferometric measurements, but you know, white light technology is not applicable to fiber Bragg grating technology. Different types of fibers, one single mode, one is multi-mode, different type of light sources, etc. And so it's you either go with one or you go with other. And if I had a wish list, it would be that I could have one technology that gives me the best of all worlds. But you said wish list, and if Sam's listening, we'd be very happy.
He's always listening. I'm a believer. One more thing I had to ask you, Evangelos. This is very important for me to understand. We have already understood that you want to use vibration, temperature, and strain, and the idea of using FVGs for their the slide. I loved it. I had to bring it back because I really love this slide. The idea to bring this because it is stable, and you mentioned that it's small and lightweight, and you mentioned small, and that for me triggered an interest. Why is small in these huge reactors, in these huge generators? Why is small a need? Why do you need it to be small
course.
in the
Yes,
aspect ratio?
Yeah, that's an excellent question, especially for someone who is not doesn't see these machines many times or very often. Although the machines are very, very big, there is really not a lot of space available internal to the machines. The cutaway view is great for the presentation, but if you were to see a generator assembled, there's not much space available within the generator.
Okay, so then in that sense, Europe is exceeding the integration of different technologies in photonic integrated circuits, and companies like Technovis, I'm sure they are watching, they already are telling me that they want to get in touch with you to see that they can do something to furtherly reduce the size and weight of the whole system. And I think here I do believe that there is some room for cooperation. Evangelos, thank you very much for being epic. Thank you for this great presentation and this fantastic Q&A. I can't wait to meet you in person. We are doing an online experience, but traveling is the real thing, and I want to travel and see you.
Wonderful. Thank you so much.
It is 2:40, and it is time now to continue with this fantastic experience. Let's all go to do networking, to visit booths. Let's get to know each other better. I will be back at 3 p.m. with the next session of this fantastic keynote session. Such a beautiful jingle. It gives me goosebumps. Photonics Plus. What is this? We are making history today. I really am so happy welcoming end users, talking about their needs for the photonic supply chain, and answering the EPIC question, which means how the 685 members of EPIC can help them. The first session was really cool with Fibersail and Siemens looking for cooperations. The second session is about semiconductor manufacturing. And we have ASML and Electrolux looking for strategic partnerships in the photonics value chain. What an amazing experience. The first speaker of the second session is Umberto Emanuele, business developer and product manager for ASML. Umberto, thank you very much for being with us today. Tell us how the companies in the photonic supply chain can make the great ASML, the huge ASML, the success story by definition of ASML even better. The floor and the attention of everyone. We have 300 people watching now. Is yours.
Hi, Jose. Good afternoon. So I hope you can hear me well.
Loud and clear.
Yeah. I'm glad to be here today and to share about the ASML and photonics, because basically it's where we see the future. So let me start with basically the
Umberto, do me a
outline.
little favor, because
Yes.
I really want to see you at the same time as you show the slides.
Correct.
Go to
Yes,
the
correct.
camera icon,
Yes,
click there,
correct. Yeah, totally correct.
so we can see you very well. Because people really want to do business with ASML.
Yeah. It's good to.
You've been
to look
driving
at
the
the
photonics
eyes.
innovation.
It's good to look at the eyes, even if in those times. Yeah. So this is the outline of my presentation today. So basically, I would like to guide you through ASML, who we are, what we do, and the connection with lithography technology and photonics, especially photonics. And I would like to start with a first statement that can be recognized by everyone. So chips are everywhere. It's really hard, almost impossible to imagine a world without chips. So then we have in front of us at this moment, we have on us, so we wear them. It's in our cars, in data centers, we can connect today through chips. And this is basically is a driver, but it's also a global economic catalyst. Just think about the size of the industry. It's huge. Only in 2020, so last year, 1 trillion chips were shipped. That means that 130 chips per single person on this planet were shipped in just 1 year. And the size of the sales is also huge. That means that chips are in our daily life, and then will be there to stay. So how we connect ASML to chips? And this is the introduction. Basically, we are the makers of the machines they make those chips. So our president recently defined our scanners, our machines are very expensive and complex printers, but somehow I will explain later in this presentation that is partially true. So lithography is a critical step in the production of chips or semiconductors. Last year, ASML had quite good year despite the global situations. We had 14 billion, and we are running the company with about 30,000 employees. And just note that the 1/3 is busy with R&D. So that's the main message, that we do innovate and we do look into the next possible challenge in technology. As all big players in the Silicon Valley of semiconductors, also ASML started in a kind of a garage container site. So there was 84 as a spin-off of Philips and ASMI. So 31, very few people with can-do attitude, and sometimes you can also define stubborn, started this company. And it took a decade of struggling and basically challenging the at the time technology to make this successful. So the first tool was shipped to IBM, if I'm not mistaken, almost 10 years later. And there, the very success of ASML started. And today, that container became a big campus. You can see a picture from the top. It's one, so we are recognized from all major chip makers as the leading the market leaders. We are in Europe, the biggest tech company by market cap. And again, there's 10,000 employees, basically cost us more than 2 billion per year, but that is well worth. It's the innovation is basically the right investment as we consider. Also, this slide is quite important, and I would like to explain basically what we do, why we do, and how we do. And that's why we have a purpose, a mission, and a vision. Our purpose is basically to unlock the potential of people, but also the society, just by pushing technology to new boundaries, to new extensions. But why we do? Because basically we want to help and to solve humanity or man challenges. And the way we don't do in an isolated way, but we do together with our partners, suppliers, and customers, and just looking at the possibility to develop and the patterning solutions that drive the new advances of the microchips. This is really general, but if you look, one of those challenges at the same time, the technology limits are within these 5 pillars that are healthcare, energy, mobility, entertainment, and communication. And we see right today with pandemic and the last year that this is quite actual, and then this can really help humanity and people to face big challenges as indeed we see. But so how do we see ourselves in the industry? So ASML is guided through and by the Moore's law. So was 1965, a very smart guy who later was the co-founder of Intel, Gordon Moore, in his very complex paper, defined a trend. He saw that the number of transistors per chip was doubling every year. Right after, he corrected himself and he said, no, by the way, it's not every year, it's every 2 years. And that statement, which became a law, was held for more than 40 years, 4 decades. And then if you see this nice graph of the microprocessor transistor counts, they perfectly almost fit in this linear trend. And there where we stand. Moore's law is the driver of lithography of ASML, especially. And I have a next example to explain what that means. Here I would like to compare one of the first IBMs, the personal computers, and the latest iPhone that also works with the Samsung phone, by the way, if you like it more. 36 years apart. If you compare the price for the actual current currency, that will be roughly the same. But then on computing, on memory, internal and external memories, in resolution, in instruction per second, then you have a notion in between. You have really order of magnitudes of difference, of improvement. But then look back at the last line, 13 kilograms for that personal computers, they can do 1 billion less actions that can do your phone with 200 grams in your pocket. That is Moore's law, it's so powerful. And what we see that wasn't ending in 2011. We also see that this trend is continuing for the next decade to come. And then this industry is pointing towards 1 million transistors per millimeter square. It's sometimes when I think and rethink on those numbers and this trends, it's really unbelievable about this. And Also, another flavor of basically the same discussion is the comparison between the first integrated circuit that in the 60s was of the size of a fingernail. Now, a few years later, but in 2012, then in the same surface that Intel was able to basically fit and to put billion of transistors. Then you can see that the shrinking was about a million factor. This is again amazing. But how do you see this trend? It's not isolated. It's really behaving as a recurrent trends. So now in this next graph, I want also to explain the information technology or the semiconductor trends areas. So in 65, we had the mainframe computing. Then it was a room filling big computer where you needed multiple person to talk with and to operate it. Very complex, and the performance we can already imagine that they were poor with respect to today. 20 years later, then we got this personal computer. Similar what I showed, the IBM case I showed before. Then you had one person talking with one computer, then giving instruction and getting results. That was already a good achievement. And that lasts again roughly another 20 years. And then we enter in the new revolution, which was mobile computing. One person talking to multiple machines. And this picture is indicative. So nowadays we have a laptop, we have a smartphone, we have a tablet, and then we interact with all of those. But now we are already at that stage that the new revolution, which is ubiquitous computing, then you have multiple machines directly talking with multiple machines. Sometimes the human is it's an addition, added value. So that's why now we are entering in a big market, but also big revolution, which is made by mobile, autonomous driving, Internet of Things, and high-performance computing. And there is what you can also you can join me in this thinking. The photonics revolution can take place. Basically, exactly in this space, in this framework, where you have information processing, computing, robotics, measurements, sensor and imaging, biophotonics, you can name it. There, the need of efficient devices and photonic solutions, it's really key. And there we like to see and to participate in this revolution. That's why we are part of EPIC, and that's why we are here today to present. But then the question is photonics, does photonics require Moore's law? The answer is no, not entirely, and that's also why ASML is not pointing and looking only at Moore's law, not only the double patterning, but what we look at, what we are investing very much is the more than more, what we call mature markets. So the point of not double patterning, but to apply functional diversification. So the idea there is not to go and to shrink more and more, but just to be able to insert different products in a package, on a chip, such to give the added value. And there where we like to focus our attention, especially looking at photonics. Now, one small digression about the lithography probably is not needed, but I would like also quickly to share the lifetime life cycle of a chip, a semiconductor wafer. So basically, very easy. We start with the deposition, and then we have a photoresist coating. At that time, we have our lithography to take place. So basically, we shine light onto the wafer, such to interact with the photoresist. And then we develop, we etch, there will be ion implantation, remove photoresist, and this loop is not finished. So nowadays, especially, we have multiple layers, and then this cycle will continue more and more. But there where we stand in the exposure line. And then also here, just to take a small step forward to the very schematic how the lithography works, basically in very short. And this is a nice picture I took from ASML for Dummies. So very powerful lasers create light. This light is entering in a reticle or mask, basically where you have your pattern you want to print on your wafer. And that's that light with the information that you want is going through the laser. It's going up to the wafer and basically printing your features. If you look back at one of our machines, this is just a schematic of what is happening inside. Let me see if I can make it. You have a laser, typically a source of light, can be laser or lamp, then can create light, which is conveyed in the illumination system, getting into the reticle. So reticle is, as we said, is a mask where you have your pattern designed. And this reticle can be fixed, also can be moving in a reticle stage. And then this information is conveyed through a lens to optimize light in a perfect way, you can say, up to reach the wafer stage, which also can move with respect to the other. And these, I will have a few slides, are the key functionality of ASML tools. So technology is important, but technology is not, again, something per se. So what we looked ourselves at, what is demanded from our customers, is to keep the manufacturing affordable. So the relative cost per pixel needs to go down in order to make business and in order to compete. And that's what we did. In every decade, basically, we launched more or less a new product, and we went through multiple revolutions. So we could scan through the wavelengths of light. We could increase the wafer size, so our wafers can moved a long time with the in size. But we also moved from one technology, which is step and repeat. So what is the stepper functionality, to step and scan. So basically, we could move relatively the reticle and the wafer such to improve throughput, but also quality of resolution. And then recently, we had the immersion lithography, and then very recent, the UV, basically the leading edge technology, where we are the leaders in this field, ending up to a very complex. And then complexity is the key, because in order to do so, the complexity of our systems went extremely dramatically up. And then with the same explanation I gave, basically the same systems to be affordable, but to have the resolution and the capabilities became so complex. So now the question is, in all this chain, how do we target photonics? Do we need the latest? Do we need the So here again, a repetition of few of our platforms, 80s, 90s, 2010, and 2020. Do we need the latest? No, the answer is easily no. So to target photonics and to be competitive in this market, which we call mature, then we can perfectly target the past 5500 series, which I like to call them to define machine with history. Was 91, again 90s, when we launched this platform to the market. At that time was dramatically able to reduce manufacturing times, but it's still today very competitive. It's as a modular design, so it's easy to serve and to manufacture, but also to serve at the customer side. And the key point is that it's so versatile that the same system or the same generation, you can customize such to implement for the product you want. It can be MEMS, it can be radio frequency, thin films, power devices, LED, MicroLEDs. Especially now in photonics, this diversification and this versatile behavior, it's quite important. And then most importantly, the capability of handling wafers that they are not standard, not only silicon, but exotic substrates, sizes, thicknesses. It's one of the key elements of this platform. It's so flexible that indeed you can make it as much as what you want. In this in this blue rectangle, I basically highlighted the main characteristic of this, which is not a single machine, but is a generation of machines. So we can move from I-line to ARF. The resolution goes from 400 to 90 nanometers. So then you can resolve tiny features. The overlay, it's also going from 100 to 12, and the wafer size can be flexible. And that is why, basically, because of the size of the tool, the weight of the tool, the cost of the tool, the performance, the specifications, the support we attach to it, the copy exact, this is also very important. Many factories, they don't need only a single tool, but they need multiple tools that they can match with each other. For all of those reasons, I consider the past 5500 generation the perfect fit for photonics products. And the last point, which is basically connected to this platform, but in general with ASML. So we don't do innovation in isolated way. We do it through an open innovation. So the way we handle everything basically is combining our very, very advanced and optimized production process together with our R&D, and then I already shared a couple of times the expenditure we have for R&D, but also with the network of and partnership with suppliers and customers to create a collaborative ecosystem such to also welcome ideas or spin-offs or startups or eventually collaborations with companies that we can mutually help each other. And that's also why we stand here. And basically, we are open to listen at everyone and to help everyone to basically make the new world and the new future better.
Making the new world and the new feature better. That's a small challenge for ASML. You are taking the world by the horns. It's quite outstanding, the effort that you are doing collaborating with many companies and actually developing the next generation of lithography solutions for photonics. You know, Umberto, I was in Eindhoven the day that the wafer stepper from ASML arrived at the R&D Center of TU Eindhoven. And the cooperation between ASML on that actually created one of the biggest booms that we have seen in Europe on the indium phosphide photonic integrated circuit manufacturing. And now we have, thanks to that, companies like Smart Photonics making indium phosphide foundry surfaces with a wafer stepper. And also we have Effect Photonics actually making transceivers with that technology. And that was thanks to talking. And I love talking. So I have a few questions for you, but the first one is the epic question. I have 685 companies here and they are my best friends, so treat them nicely. What can you do for them and what can they do for you?
Yeah, basically we can help each other, and this was always the case. It will be always the case with companies that we can bring a new solution for the future, that we can help them to develop their products, but we can also receive very important inputs, so our systems can be used and we can learn from each other. So the easy answer is help each other in the next time to come.
Umberto, in photonics, what we have seen now is different trends, but the first one is the need for maskless litho for the manufacturing on wafer level micro optics. In your presentation, you didn't address the maskless litho, but many companies really would like to talk to you about potential cooperations. What is? Can you share with us a little bit about the potential interest of ASML on maskless litho?
For that one, I think I will need to discuss and follow up internally with the ASML, but the main idea is that we work with lithography with masks, but I think there is always open innovation, as I mentioned again. So if there are potential benefits for both, I think we are always open to think and to discuss. But at this stage, I think it's something to be potentially discussed.
We have Maxim from Allan 3D. Allan 3D is one of these startups that gives me goosebumps. Actually, they have something called the nanofabricator, and they fabricate structures atom by atom. And when it comes to the next generation, the next revolution, we hear quantum technologies everywhere. We go to that particular need. I love the 7 nanometer node. I'm a huge fan, but we go to that particular need, understanding every material atom by atom. In the quantum technologies as a framework, is there any room for cooperation?
It is. There is. We have some projects which are ongoing or about to start with some of our partners. So we see potential there. I think I have to say that it's probably not as per today. Or we look at already a result for tomorrow, but we have a vision on that, and we are already there collaborating with partners. So we
Umberto, it's so great to have you in our network. You know, the micro-optics revolution is coming. The quantum photonics revolution is coming. The huge boom for photonic integrated circuits in non-telecom applications is coming. But the big one right now, the big one today is co-packaged optics. It is co-packaged optics. And there, for doing co-packaged optics, we need E-beam lithography, optical lithography. We need to combine all lithography processes into one. How do we approach you? How do we get you, ASML, as part of this ecosystem for the co-packaged optics?
Just approach and discuss. As I said, the collaborative ecosystem is there to work and to be fulfilled by ideas and by collaborations. So then we have also, there is part of a strategic marketing task. We have some interest and we have to look at the packaging, but it's something again to be developed, and we are there to listen and to collaborate.
For those of you who are interested, EPIC is developing the roadmap for co-packaged optics, working very closely with Cobo and with the Ethernet Alliance. We have an upcoming event with Intel, with Microsoft, with Ranobus. I want to have ASML also there. Thank you so much, Grazie mille. Thank you very much for being with us.
Thank you,
and
thank you, everyone.
Join me now, because now we're going to go to one of your clients. We're going to go to the consumer market. And to go to the consumer market in Europe, is to talk to Electrolux. We want to understand from Electrolux what it means semiconductor manufacturing in photonics, what it means to bring photonics to the high volume production, to the low cost, and to the reliable systems. And for that, I have the honor and pleasure of welcoming our next speaker. All the way from Electrolux, our next speaker is Cristina Bertoni, project leader in Italy. Cristina, grazie mille for being here. The floor and the attention of everyone in the Photonics Plus community, 350 people watching you right now, is yours.
Thank you. Good afternoon, everyone. Let me just switch to the sharing window so that I can share with you my presentation.
Fantastic. Let's go to presentation mode. And please. Electrolux has been working with EPIC in many different frameworks, even mid-infrared technologies. Cristina is one of the people that we have been contacted, and there's been so many different cooperations. Cristina, we are now in business. The floor is yours.
Okay, can you see everything?
Gorilla Glass Clear.
Okay, so the title for today's presentation is From Consumer Needs to Value Proposition, How Photonics Can Help Sustainability at Home. I'm Cristina Bertoni. I work at Electrolux since 2007, and in particular in the research and development sector. There are, as you will see later, several centers around the world, and I'm from a department located in the northeast of Italy. So Electrolux is a leading global appliance company that is quite aged right now. It has 100 years and was founded in 1919 in Sweden. Electrolux produces washing machines, dishwashers, cookers, and ovens mainly, and so all the kitchen appliances basically, and the laundry. And at the moment we are strongly focusing on trying to push sustainability in our solutions for the better of all the society. So this is our footprint around the world. We have major sites, manufacturing sites and R&D centers in Europe, in North America and Latin America. And we have also activities in Middle East and Africa, Asia and Australia. But certainly the major presence is in Europe, North America and Latin America. Certainly, Electrolux Italy, that is the company I work for, is one of the most important support of the Electrolux leadership at the European and the worldwide level. And this is not only for the production volumes and the high level of automation of Italian manufacturing sites, but also for the wide range of products, their quality and the level of technological solutions being implemented in them. Here you can see the R&D centers of Electrolux around the world, and as I said, in Italy we have manufacturing sites for all the product lines, and also research and development centers for all the product lines. Okay, so Electrolux is in 2019, and for the 13th consecutive year, was included in the Dow Jones Sustainability Index World and Europe indexes, and thereby ranks among the top 10% of the world 2,500 largest companies for social and environmental performance. Additionally, Electrolux has received recognition from other indexes and organizations, including the United Nations Global Compact Top 100. Electrolux is also a member of the World Food Programme of the United Nations, then in 2020 has been awarded with the Nobel Prize for Peace. So here you can see a slide where basically are summarized our 2030 2030 goals for better solutions for consumers to make our company the best in terms of impact on the climate by reducing greenhouse gases emissions, also to act ethically and help the supply chain to move towards high sustainability rates. On the other side, regarding the territories of taste, well-being and care, we certainly will strive to make sustainable eating as the preferred choice, make clothes lasting longer with half of the impact, and make homes free from allergens and harmful pollutants. And in this case, of course, we are actively working in terms of R&D on indoor air quality systems capable of moving towards this goal. Regarding drivers and trends, certainly the company priorities have been reviewed according to the next normal that is taking place after the COVID outbreak. While a strong focus is kept on health and safety measures for all employees, as I said, at the workplace, strong priorities raised by the pandemic are to reorganize the supply chain, to accelerate time to market of prioritized projects, and to boost cross-functional teamwork. In any case, Electrolux remains committed to its science-based climate targets for 2025 and to become climate neutral along the value chain by 2050, in alignment with the Paris Agreement to keep global warming well below 2 degrees C. Concerning product development in the last decades, Electrolux made its transformation from a typical manufacturing company to a consumer-driven company. And in line with this transformation, addressing drivers and trends in our offering is imperative because the need to capture prevailing trends became absolutely relevant and more important than ever. Now product and service offerings are being tuned to the new normal, to new hygiene practices, to online shopping, to reduce to the reduction in incomes that is taking place, to the quest for trusted brands, for digital services by keeping a strong commitment to sustainability. Pandemic increased the time spent at home, as you can see in this slide, where I report data on Google mobility trends up to September 2020. And as you can see, after March 2020, the time spent at home, that is indicated as residential, increased quite a lot and is now stabilizing around 10% plus with respect to before the pandemic. And the new organization of work and life with the adoption at systemic levels of smart working paved the way for new possibilities for being sustainable. In fact, sustainability requires time. And now, by going smart, we have more time at home that can be spent to tasks and actions that before we didn't even have time to consider. So going smart actually provides a unique opportunity to devote more time to sustainability-oriented behaviors. And of course, the appliances industry can play a huge role in driving these new behaviors and making more sustainable our life at home, our new life at home. Several sustainability indexes can be made available to users at home, such as, for instance, as I show here in this picture, energy usage and generation, heating equipment performances, but also we can show how we perform in terms of water usage and food storage and consumption. And in today's presentation, I will focus on developments that we made towards a better water usage and also a better food storage and consumption. Regarding water usage and consumption, in this slide I report some EPA data regarding the use of water at home. As you can see, there's a huge percentage of water used as tap water, also for washing, and also for laundry, basically, so washing clothes. Certainly, strategies like regarding water pricing, water metering, efficient household appliances, and water-saving products can play a huge role in orienting the behaviors of customers. However, you can find several tips on how to save water at home. And among these tips, one that is related to the washing of clothes and dishes is normally related to the detergent. Often, I think you have heard that it is important to use the right amount of detergent. However, the right amount of detergent is a tricky question because detergent efficiency depends on many parameters, including, of course, the soil, the amount of dirt, the amount of load in terms of dishes or clothes, but it depends also on the quality of water. In particular, the water hardness, that is basically the content of calcium and magnesium ions, which determines the water hardness, is a parameter that greatly affects the detergent efficiency. Therefore, one way to use better the detergent and lower our impact on the environment is by softening the water, that is by removing magnesium and calcium ions. And many of you have at home a dishwasher that has inside a water softening system that you periodically need to regenerate by adding salt to the reservoir that is dedicated to that. Now, once the salt is put inside, there is a brine solution that is building up inside, and that is regenerating the ion exchange resins that enable the softening of water. I here show you the results of a development work that took a couple of years of activities, and I show you in particular the pictures of one module that was developed internally, and that basically, as we are always committed to, we need to find the simplest way to realize and to make an object that is feasible, reliable, and it costs less than whatever you can think. So what we did was to start from a commercial turbidity sensor that is also a feature that is certainly in our dishwashers, that is used to monitor the quality of water along the process by the aid of infrared LEDs, and it works in transmittance for those of you that have a technical background on this. So here below you can find the typical datasheet regarding turbidity measurements for the type of sensors. Now, by disassembling this commercial sensor and separating the electronics from the optics, and by basically substituting the head of the sensor with the two pins going into water where the LEDs look into the water, and by adding a new refractive element that was built to adapt the optical element to the emitter and receiver locations, we managed to build and test and demonstrate actually a module that is derived from a commercial sensor that with a small change can be converted into a salinity sensor. A salinity sensor that has been patented together with other embodiments that we found by working on this project, and that can be easily and effectively fabricated in a short time to make our softening systems more effective in warning the user to load new salt into the dishwasher or the washing machine. This to use better the water at home. Now I will move to the food storage and consumption, which is another very important sector of activity for us, especially in the next future. You know that within the Green New Deal, there's a huge amount of money devoted to projects or initiatives to reduce the amount of food that is wasted. From the literature, one can find that among the different type of food categories that we normally store inside the fridge or at home, there's a huge quantity of food that is wasted. In particular, consumers are the biggest wasters along the food supply chain, with a share of 38%. And based on waste sorting analysis and household waste surveys, one can discover that most wasted products are liquid dairy products for around 25%, vegetables and fruits 20%, and bread 17%. Hence, the introduction of solutions able to impact significantly on food waste prevention can provide quickly a payback to the user and can help the consumer to develop awareness and provide a feedback to move towards a positive change in food consumption behavior. So here I report about a fridge camera called Fridge Cam Plus that was inserted in the market by Electrolux AG, that can be simply mounted inside the refrigerator, and that can pairs with a smartphone app. Basically, as you can imagine, with the aid of this simple camera, one can get images of the food stored inside the fridge to the phone wherever one can be, and therefore this enables the consumer to buy really what is needed and optimize the shopping list. On the other side, one can also keep track of expiry dates, so to avoid food waste. And from the app, the consumer can also get links for online shopping. So the ability to check the content of the refrigerator remotely is something that create more responsible behaviors in food purchasing and usage, and can help reducing food waste. And also one other functionality that the app is providing is the suggestion of recipes that the user can consider for cooking the food that is inside the refrigerator. So this is an example of how photonics, in this case just with a simple camera, can make a huge difference in terms of behavioral changes. Here instead, I mention basically a work that I'm currently leading inside Electrolux for the MIRFAB consortium, where Electrolux entered as an end user in 2019. We provided along this project specifications to the supplier regarding interference analysis and the mid-infrared spectrum of the target gas mixture that we wanted to monitor with the MIRFAB prototype. The module arrived in September 2020 after a period of, let's say, difficulties that everyone had because of the pandemic. But finally, we are characterizing in our laboratory in operational conditions very near to the final application this module working in the mid-infrared. The testing is going well, the sensor is working, and it is collecting quite good feedbacks from the end user the internal end user, or if you like stakeholders, is the food preservation product line, because the monitoring of the selective monitoring of some gases can really make the difference in the ability of our appliances to manage the food stored inside the refrigerators. And what we hope is to move together with the partners we work with within the Mirfa platform, to move towards miniaturization, so to enable a large-scale production and hopefully a reduction in cost, which, as I said before, is something that we need to be compliant with all the time. In this slide, I mentioned another initiative of Electrolux that is related also to sustainability. In 2018, Electrolux created this open space that is called Innovation Factory, that is based next to the R&D center where I work, and where basically all the R&D units and startup companies, universities, other suppliers can gather together and work together to innovate quicker, because the demand is to accelerate innovation. And as many of you know, the path from the innovative idea to production is quite long and engaging. And Electrolux Innovation Factory is publishing every year a call for partnership by addressing every year new topics. This year, for instance, among the topics that I report here for your knowledge and maybe interest, there is also a call on low water sustainable washing, as I said. That is one of the area of work and effort by the company to make our appliances to be more sustainable as possible. This call for innovation is open, and it will end on April the 2nd. At least the collection of requests for participating, and after that there will be an event where the submissions will be selected, and those that will meet the requirements and needs will move forward to a specific path and activity within the company. So thank you.
Thank you so much.
Your attention.
You have made me so happy with this. I think we have some problem with the sound, but we'll solve it. Thank you so much. You have made me so happy with this, because there is so much room for cooperation here. You've been a star on bringing mid-infrared technology to the consumer market in the Mirfa platform. And for that, I would like to really thank you. But let's try to explore other cooperations. The first one, we have this amazing opportunity, the call for innovation for Electrolux. And one thing that we are seeing more and more is the need for easy to clean surfaces. On that, we are using actually ultra-fast lasers to make structures that actually could define an easy to clean surface as a surface that can be cleaned by 3 passes of a cloth. To what extent is that interesting for Electrolux?
Well, my research center is a cross-product research center that is dealing with all the technologies, or at least we try to cover all new technologies that can be of interest for the company, not only for the existing product lines, but also for the future of the company, which means also to change the business and to consider manufacturing new tools, and also to provide new services to the final user. So if anyone has some proposals in this regard, I'm certainly I can say that I can present this internally, and there will be people interested into that.
And we have really amazing technology to solve this for you. So you will be quite amazed. The next one is, I also have a smart fridge and I love it. I go around with my phone and I can see exactly what's on my fridge. It's really fantastic. But I think that's just the beginning, right? I mean, we really want to know the quality of the food. We don't want to trust expiration dates. Is there a roadmap to actually with multi-parameter sensors, even to the point of gas and solid chemical composition into our fridges?
Yes, absolutely. This is actually the roadmap in the sense that the camera is the first entry point, let's say, that is sustainable for us from the economical and manufacturing point of view. But then with this camera, there are a lot of things that can be done, and especially there's a huge expectation on the integration of this camera with other sensors, as you said, and that's why as well I showed in the same presentation as well the work done within Mirfab, because the gas atmosphere inside the refrigerator can also provide enormous or at least really valuable information about what is happening inside in terms of freshness of the food, as you said. So there's the recognition means that is, for instance, the camera, but then there are other parameters that we need to monitor to improve and to move towards something that is more complete and providing a better service to our
this call for innovation is really amazing for us, because you really have been in Mirfab brave enough to be the first consumer company targeting the inclusion of quantum cascade lasers for chemical characterization, and that's huge. And you were the first one, because now there's a trend. We have seen even the consumer companies, the large ones, the large consumer, I don't want to say, but everybody thinks about Huawei. One of those is really looking at QCLs, and that's really something that really makes us happy, because we have integrated photonics coming. And if we want to answer to you is, what do you need from an integrated photonics platform? Cost is only a small part. Reliability, but what is the first question that comes to mind when a person, for a company, for example, Lyonics, comes to you with silicon nitride photonic integrated circuits that can do biosensing? What is the reaction from the consumer company?
Sorry, I had someone at the door right now, and I didn't catch very well your question.
The question is, we need you. We need you to help us going into volume production with the photonic technologies. We need you to help us. Why? Because you are the one who can tell us, okay, today the technology maybe doesn't satisfy the price per unit that the consumer market is awaiting, but maybe in 5, 10 years, or maybe in 3 years, working together, enabling the large volume, it can happen. You have done it in quantum cascade lasers, and you're going to do it in many integrated photonics technologies. Thank you so much for this presentation. Please make sure that the person at the door knows that you are in case an important package. And I would like to thank you and ASML for a fantastic session. Grazie mille. And we are going to take now a little break until we move to the next session. And in this break, I want you to try your best with a positive mind, like mine, a positive mind, a lot of energy and happiness. Try your best to see if there is a chance that we can see a few of the exhibitors, and use the chatting rooms, use the social rooms, the networking. We are trying our best to make sure that we give you an experience that is as close as traveling, but nothing takes over traveling. I can't wait to start traveling with the coronavirus being over. Wear a mask and wash your hands. And I see you exactly at 4 p.m. Let's get to know each other better. Ladies and gentlemen, it is 4 p.m. 4 p.m. in the Netherlands. We've been doing this already for 2 hours, asking end users what the photonic industry can do for them. We started with the fiber sensors, and we had Fibersail and Siemens. Then we continued with semiconductor manufacturing, and we had ASML and Electrolux. And now we talk about micro-LEDs and micro-optics. Many of you are texting me, telling me, I cannot see the footage, but can I actually see it later? Do not worry. We are making history today, and history is here to stay. So we are going to make sure that all of you get the footage of these fantastic presentations. The micro-LED and micro-optics session is going to have OSRAM and Volvo. OSRAM Continental and Volvo are enablers of cooperations with the photonic industry. First, we're going to talk about projections. And we talk about projections, there is nobody better than Michael Rosenauer, all the way from OSRAM Continental, the head of advanced development and modular architectures. Michael, thank you very much for joining this amazing epic adventure today. The floor and the attention of everyone goes to OSRAM Continental because they want to work with you. The floor is yours.
Thank you very much. That's, yeah, a very warm and very warm welcome, and thanks for the nice introduction. Let me just quickly share my screen. Second.
Michael is like me. He likes to show the logo of the company he works for behind it.
Yeah. So since we cannot meet in person, yeah, that's the way.
Michael, can you do me a favor? Can you click on the camera logo that you have
Yes,
there so we
sure.
can see you while you show the slides? Fantastic. The floor is to OSRAM Continental.
So I hope you can see now both presentation and my video feed. So thanks again for the invitation. I'm honored to be here to tell you about the amazing opportunities that we have in terms of projection solution, especially now in the automotive industry. So this enables basically projection, new functions, new possibilities within the car, but of course also around the car. So where did we come from? So as you already mentioned, so OSRAM Continental is a fusion of the capabilities of OSRAM in terms of lighting, the capabilities of Continental in terms of electronics. So for sure, lighting in the automotive world was always for a mere means of sight. So you illuminated your way, the way in front of you to see better, actually to visualize things. So with only, but in the past, with only a numbers of pixels, a limited number of light spots. Basically in halogen and in xenon, for example, you had on and off functionality and low beam and high beam functionality. So the next step was now, and what we are currently having is advanced lighting, vehicle lighting. So with the democratization and this approach that in almost all cars now, LEDs are included. So with this high performance that LEDs are delivering in terms of efficiency, but also in terms of the light color and the tunability that you have, in combination with electronics, we have automated some features. So for example, an automated high beam adaptive lighting to highlight things that you are more interested or dangers in front of you, actually to visualize them. So this is where we are now. So now comes the step to digitalization. So, and this enables completely new functions. So we have now connections from the onboard sensors, for example, to also external data sources, to events that are then put into the car's intelligence, actually from, for example, cloud data. We have the possibility with high resolution lighting, and this means 1 megapixel upwards. So you imagine you have a beamer more or less in the headlamp included, to use now this technology for communication, for projection on the road, to guide the driver, but also to make the pedestrians and the environment aware of what is going on. So this enables car-to-X communication. And also it opens up an interesting topic in terms of services. So you have maybe completely different revenue streams, completely different options then to capitalize those functions. So, and you have now all these possibilities already in hand. So the next step, now you have increased functionality, safety, but of course, cars are mainly also sold via design and via now the individualization. So one of the topics we are currently working on very strongly is the integration of those lighting modules, of those light features and function into material. So what is the user seeing in the end? It's hidden away technology. You sees the high quality surfaces, for example, is what we call, and the industry is calling shy tech. So it hides away and it appears when it's lit up. So you can illustrate actually high quality surfaces, wooden surfaces, in case of like high quality stone-like surfaces that you basically are lighting up then. So, and this increases the comfort and the features inside of the car. So we are seeing that also the interior is changing and becoming basically a third place. So besides of home and work, you have a third place actually where you can enjoy that life. And light is always some kind of feature to increase that comfort. So, and as if you want to look for an analogy, and I've actually thought about this, what can be, what could be an analog or a metaphorically figure that you could imagine. Now we are creating not only like music, we are creating really a symphony with that, with this combination of elements, of lighting elements, but also with other elements. If you would compare it actually to an orchestra, you have like the stage, which would be now the vehicle. You have a conductor, which is basically the electronics control unit, which guides all the elements inside. You have the electronics parts. These are basically the musicians that are turning and tuning the instruments. The instruments are basically then features of light, of sound, but all the other things that are now working together. And then you have the software part, which is basically then the music that you're playing. And if you think about like this, you have to have new tools and approaches how to develop this. So you are not only developing, for example, for cellos or for violins, but you would actually develop for a complete orchestra. And you have to include all these different elements inside a vehicle. So, and to come to that, this is a proven area. So projection basically in entertainment and architainment is one of those things. You have not only the image that you're seeing or the visualization, but it's all your senses that you are experiencing with that. And that is something that needs to be translated also in the automotive world. And projection is, I think, a good example actually that you on the one hand side have functionality and safety, which is included, but on the other hand side, you have a strong design and emotional impression that it makes basically on the consumer and the end user. So what just to give you a rough overview, I think if you are from the automotive world and you are working in lighting, basically it's not very new to you, but basically what are projection opportunities that we are seeing. Of course, most of you know, if you open the door, you see a brand logo on the floor, which is projected out of the door sill, for example, or out of the door trim in the interior. You could have it in the mirror to light the way up to the car. You have from BMW firstly introduced the light carpet, which is basically an MLA-based solution, which goes along on the side of the car. And the new technology enables also to have like beamer-like or projector-like opportunities now from the headlamp as well. So imagine you're driving up an icy road, the car detects that it's icy in front of you and it displays, for example, this warning symbol, a snowflake, or it guides you with guiding lines that are moving. That's something to increase also the signal lighting and the functionality to increase the safety. On the other hand, if you go now from the exterior to the interior, it's somewhat overlooked, I guess, up until now. But for the interior, you have many new opportunities. If you imagine you take the hand off the steering wheel, you would experience the interior completely different. So basically, this whole area is now a room actually to put projections on, to put lighting into a different. Actually, lighting used to create different feelings now in the interior, and projection could be used to project on surfaces that you, for example, you cannot include displays into because you have an airbag behind it, but you project on these areas, for example, and create some sort of interfaces or just create some sort of orchestration for the interior design, for example. On the other hand, you can have the projection, for example, on glasses, on the side windows, on the back window, for example, in taxis or at shared mobility providers who use this for information, for guidance, but for advertisement, there are a lot of opportunities actually what to look for. And it all comes down to certain modules and technologies that we need to provide to the end users, to the OEMs, who are then including this. But of course, there are some certain challenges. That's not something very new, but it's always something that is a lot of discussion actually. So this is the daytime visibility. So you have different grounds, different surfaces where to project on. You have different times of the day, of course. And I've just put together a couple of images where you see what kind of difference this makes. Of course, projection, so it's very hard to beat the sunlight for sure. So on a cloudy day, you have like 19,000 lux. Roughly, and you need a certain lux level as well for the projected surfaces to be able to distinguish between the projected content and the background luminance on that. So for sure, for the dawn with 750 lux, roughly, it's clearly visible. And in parking garages, for example, it's clearly visible. So typically where you actually use your car lights. But there are options actually to overcome certain aspects. So for sure, maybe not the clearest day, the most sunniest day, but for sure on a cloudy day, what would this mean? So if you would go for an LED light source that would be able to beat that, we would end up with a light source that would deliver basically 3000 lumens if you would project it on 3 square meters. That would be necessary to make it, to distinguish the simple projector basically from the background illuminance. But you could also go for a laser light source, and we have been the first, OSRAM has been the first provider actually of a laser light source for a headlamp, for example. But in fact, actually this could be, there is the technical potential actually to achieve the daytime visibility. If you imagine now the laser coupled with a MEMS, for example, and projected certain symbols, certain guidances on the lines on the road. But for sure, what you definitely have to make sure is the eye safety. So if you use lasers and if you use laser light sources, for sure you have to be certain, if you include that it does not hit somebody in the eye. Basically, nobody is able actually, or should not be able to look into directly or by reflective surfaces on this laser light. So this is something that we are working on, but basically we have worked on also in the past to make sure this is laser safe. But this is something that is definitely somewhat of a challenge, and this has to be worked out together with consumers, but also with the OEMs on where actually projection or actually lighting on surfaces starts. For the interior, it's somewhat different. For exterior, you see these images, what it in the end means. So what is the technology that we are working on, and what could be something to come up with, and what we distinguish basically between 2 design streams: the straight system designs with freeform reflectors or lenses and taper solutions with graphical optical blackout areas, and advanced systems where basically a couple of more things come into place on the next slide actually. But just to stay at the straight system designs, with those 2 options, you have the ability to create very homogeneous light patterns. For the freeform reflectors or lens solutions, you miniaturize the system complexity and the system itself by a reduced component count. For sure, freeform optics is not something new in this application. I would say it is to a certain extent to create really a uniform a lighting pattern on the floor with sharp edges. So quite distinguishable element actually in car lighting, in the surround lighting. And it's efficient in cost and cost sensitive actually in that sense, because reduced component count for basic illumination. The taper gobo, what does this mean? So we have the LED, and typically you have collecting or collimating lenses. What we are using is a silicon optical taper that is very close to the LED. So it collects a lot of light directly exiting the LED, so it increases the optical efficacy. It also has the functionality of homogenizing and collimating the light. It creates a quite homogeneous light pattern when exiting this taper solution. And this is basically then at the interface to the graphical optical blackout slide, the gobo slide, where the picture is basically printed on. And this more or less creates the picture. And what the third step, the projection optics, we reduce to 1 hybrid aspherical element, of 1 element basically in this, to also get the system smaller, get it more compact, get it more cost attractive, and to create a certain acceptable sharpness and a quite high luminance actually on the floor. So this is for the straight system designs. So for the more advanced system designs, there are 2 options that we're currently looking into and are also quite interested for in the market. This is a microlens array approach. So for sure you've all heard of it. So basically each of these MLA consists of a multitude of small lenses. The superposition of those images of the small lenses then create this homogeneous or this calculated light pattern. So in each single lens that is used, and that has the separate mask design. So you have to be able to do that and to lay the system out, basically design it. So and this is as BMW introduced it firstly, actually very ideal for a quite inclined projection geometries. You have it in the rocker panel and projection on the side of the car, for example, but it can also be used in other areas. So this is something that we are currently strongly also working on. And but basically it's still a hardware encoded image. So the really first digital actuator would be the application of a DMD. Also, that is not something brand new to the automotive industry. In head-up displays, they are already being used. But for projection, interior and exterior, for configurable content, actually, this is the first time that this being used. So the DLP is a proven technology. As I said, from head-up displays, we use it in combination with the white high luminance LED. And what we have developed is a kind of scalable projection optic tool set or kit for the various projection areas. So for sure, you want to develop this once and use this for different applications. And the latest status of what we are working on is this kind of what I said in the beginning, a latency-free orchestration of multiples of those included in the car. So not just the one projector or two projectors which run simultaneously, but basically really to bring this together to one picture.
Thank you very much for a great, fantastic, really fantastic presentation. You talk about freeform reflectors, you talk about lens arrays, you talk about optical tapers, you talk about laser light. There's so much room for cooperation, Michael, here. I always ask companies like this the epic question. I have 685 companies behind me. What can they do for you? What could you do for them? Maybe share with us one or two challenges, one or two items of the next Santa Claus Christmas list.
The Santa Claus Christmas list, that's good. Yeah. So what we are offering is the system design integration, the application know-how in terms of optics, mechanics, electronics. We develop those modules in series and manufacture those. This is what we can offer to the community. Of course, we are in strong exchange to OEMs and with OEMs, but we are also very much looking here for partners and on same eye level, actually, on suppliers to develop and bring those things forward. On the one hand side, you need the consumer or the OEM to drive regulation forward, but you also need very competent partners for that as well. And this is what we need here also, that basically for compact optical designs, for example, ultra short throw designs, this is there. We are looking for solutions and partners. We're looking for new light sources for matrix application, for light sources with high temperature stability. So, but overall, actually, it's necessary that we all come together and look at it holistically, not only maybe from the lighting and the photonics industry, but also maybe from the sound department, from the interior department, from a design and material perspective, to really create this one holistic view.
We have a question in the chat, actually, from a company that I love. The company is Heidelberg Instruments, and Dominic Collet would like to talk to you about your supply chain. How do you fabricate freeform optical elements? Are you perhaps looking for partners on that?
Yes, so exactly. So we are not doing that. So we are working here with partners, with suppliers as well. So on the one hand side, we have in-house capability of certain steps. So for example, for the silicon tapers that we can do in-house, but for other elements, we are looking also here for partners. Very welcome to. Yeah.
Michael, you know that we are living these days the micro-optics revolution. I call it the European micro-optics revolution. You talk about the light carpet. I went to visit SUS Micro-Optics in Neuchâtel, and I saw the demonstrator. It gives me goosebumps to see that the technology of Europe is enabling this kind of production. One thing that I would like to ask you, when it comes to a tier one like OSRAM Continental, what is the item that you think we need to tell as a final message to the photonic industry? How do they make automotive qualification of any optoelectronic device?
Yeah, so I think what there are two, I guess, I think on the one hand side you have functionality and you have the emotional experience that you would like to transport, but for the suppliers, for tier ones, and also for the OEM, you have basically two very important topics. And I would say on the one hand side, it's the time to market. So from the first idea until you be able to put this on the market, I think this time will get shorter and shorter. So we have to speed up here. And on the other hand, it's for sure cost. So this should not be, so these features on the one hand side are for sure coming down from the high quality and premium vehicles, but to really distribute this into a higher mass market, we have to look intensively and very be focused on the costs.
I promised myself I wouldn't ask you this question, but you are so approachable. I have to.
Sure. Go ahead.
Laser lighting. By when? And you talk about eye safety as being one of the challenges, regulations as being another one. In your personal opinion, in your preferred future, by when? By when is going to be the light source of choice?
That's quite, it's the same topic. So it's, I think, a matter of volume and of distribution and broader range and reach, actually, and the functionality. So we have included this as an additional functionality, so an add-on to the high beam to really see further. That was the first feature. So we have developed also a couple of new features with that as well. But for sure, to be on a comparable level price-wise and performance-wise to LED lighting, for sure the first step now is LED lighting, and this has to be distributed broadly to really push you onwards to have the correct or the right, the appropriate board net architecture, and the high quality functions that are there. And then it's definitely also the laser development on component level. This is not standing still. This grows and continues to be cheaper to get the costs down, to get a higher yield, to get a better performance out of it. And then it really has this advantage of having, of having premium or actually superior optical performances with the laser light, so to really minimize optical apertures, to really go down in the size. And that is something that the OEMs definitely are going forward with it. So to reduce really headlamp sizes and optical apertures.
We have one more question in the chat. This one is coming from one of the leaders of the micro-optics revolution. It's coming from Anterion. Dr. Chalrian, she would like to know if there is an interest for near-infrared and shortwave infrared shortwave infrared sources or detectors in your current wish list.
Yeah, so for near infrared, this is definitely something that we are interested as well. So for sure we have the modules laid out for visible light, I would say, but also for the illumination, for example, to enable a better sensor view, for example, in terms of structured light. Also near infrared is of now interest in on our wish list. Yeah. Correct.
We had discussed with some of your colleagues about interest in mid-infrared as well, but time is of the essence, and I need to move to the next speaker. I could talk to you, Michael, for hours, but you've been great. You've been great. Paul, the next speaker today, the expectations are very high to see you can match what Michael has done. We go now to Volvo, and Paul-Henry Matha is here looking for cooperations with the photonic industry for the automotive sector. I have a Volvo S60 and a really happy owner of that car. The floor and the attention of everyone. This is great, it's fantastic. This is a fantastic day. We go to Volvo, Paul-Henry Matha, the floor is yours. Paul-Henry Matha has been interacting with Epic quite a lot lately on really working on micro-LED events. And we've been actually managing to actually enable many cooperations with the micro-LED supply chain. And it's great to have Paul-Henry here. Paul, thank you very much for being with us in this epic afternoon. The floor and the attention of everyone goes to Volvo. I think, Paul, you are muted. We can't hear Paul-Henry Matha from Volvo, and we have to hear him because this presentation is one of the ones to watch.
Yes, I think you hear me now, perhaps.
Loud and clear.
Yeah, and do you see also my presentation? Yeah?
Not yet. Let's try to share the screen. I think we can see now. You go to presentation mode.
Yeah. Now I have to, my camera is open. So do you see my screen now?
Let's see. Not yet. We are having a bit of an issue now. No, not yet. We are not seeing the screen. But when we make that work, I have to say that I'm extremely happy that the interaction that Volvo has had with Epic in the last months and how many introductions we have made, and you, Paul, have followed up with all the introductions. It's been truly epic. At the end of the day, this meeting is all about cooperation. So you are developing micro-optics, micro-LEDs, packaging and assembly technologies, any kind of optical adhesives. There is lots of room for cooperation. Contact me offline. Oh, Paul, this is working fantastic. I see it. Gorilla Glass Clear. The floor is yours.
Okay, thank you. So I hope all will be okay with the technology. Yeah. So thank you for this introduction. I do not know exactly what was presented by OSRAM Continental about automotive lighting. So I have tried to do a presentation to explain what are the wishes we would like to do and why micro-LED technology is important for car makers and especially for Volvo. That's why my title of the presentation is Micro-LED application in automotive lighting, why we want it. So first, what are the usage for exterior lighting about micro-LED? So we have three different ones. We have on the left, you can see, which is the lighting technology. We have another one in the middle, which is a signaling and communication. And you have another one on the right, which is a road marking for the rear function and also for the light function. So I will focus my presentation about lighting only. So what you can see on the picture is what we call the low beam. And the low beam function has been developed 100 years ago. And then when you are in low beam, you have a visibility range between 70 millimeters on the left and 100 meters on the right. Sorry, this is low beam. So what do we do indeed with this beam? If you have an oncoming car here, you will not glare it because you will put the light below the horizontal line, so the oncoming driver will not see the light. So that's why we call it low beam. And then, if you have no cars, you will be able to go in high beam, or what we call also upper beam, and then you will have light on all the road, and the range will be 200 meters, 300 meters. It is like this for decades and decades now. So 20 years ago, 15 years ago, we developed automatic activation of high beam. Indeed, to be able to do that, we use a camera. So you can see two different pictures, one on the left from Ella, one on the right from Valeo. So we have a camera to detect if we have cars, if we have tunnel, if we have fog, if we have different things. And then we use this information. And if we have no cars in front of us, then we will switch automatically from low beam to high beam. And if we have a car, we will switch automatically from high beam to low beam. It is what we call the automatic high beam. Then, around 10 years ago, appeared what we call the adaptive driving beam. So adaptive driving beam is also a partial high beam. So indeed, the camera, you can see on the right, will detect some cars. But when you have some cars, before this technology, you go directly to low beam, so no light at all above the horizon. But with this technology, indeed, we can split the high beam in different parts, and then we will be in high beam, but in some area, we will have no light. That's why we call it the adaptive high beam or the partial high beam. And then you can see pictures. Here, for example, it is a bird view. So you are in high beam, you have a range 200 meters, 300 meters, but in the same time, you do not glare the car. And you have the same picture. Here it is a picture from the driver's side. So this technology has been developed by Volvo in 2013, so 8 years ago, with a xenon technology, and then later with LED technology. So you can see what we have, for example, today on all our Volvo cars, XC90, S60, XC60, for example, which is adaptive driving beam. And it was in a technology, for example, on this picture, it is a technology from Valeo, what is called sail beam. So indeed, you will have some motors in the headlamp, and then you will have some light with this shape, and this light will turn, and then if you have a car, you will not glare it because you will move this light on the side. So you will never glare with this technology. This was the first technology developed about adaptive high beam. When you see the roadmap, so this is a slide from Driving Vision News, you see the different technology for adaptive driving beam, called also ADB, and I will call it ADB now. First, we begin with mechanical solution, as what I have just shown before with Volvo. And then we have begun to go from mechanical solution to digital solution. Digital solution at the beginning with some few segments, 6 segments, 30 segments, something like this. And then we have increased to 50 to 100. And then we change the name to pixel beam sometimes, and after we have now the new generation with a lot of pixels, and then we call that HD technology, or with more than 1,000 pixels or million pixels. So when we have these pixels, we call that now digital light. And what is the Volvo target for digital light? It is to have always the maximum light on the road, whatever the traffic, to improve safety. And the solution is so to do this ADB with partial I-beam that will not glare the oncoming cars. And what is very important to have a very good safety performance in this case is the resolution of the system. Indeed, you can see on the picture below what is seeing the camera. So the camera will see the car and will create what we can call a keep out zone, so a black zone without light. And then the system with the light and with the headlamp will put the light where you do not want to glare. So if you have a system with a low resolution, you will have a big keep out zone system. And then if you have a good system with a lot of pixels, you will have a smaller keep out zone system. So you will have more light. So when you see the different picture here, you see sometimes you see the pedestrian. So you see that you have a pedestrian because you have very, very good resolution. But if you have a low resolution, you will not see the pedestrian. So then it will be less good for safety. So what is very important for car makers is to be able to have the maximum resolution, to be able to put light everywhere, and then to detect this sort of pedestrian, even if it is close to a car. So this is the main topic. So when we speak about digital solution, you can see different technology in the past. So we have the LED matrix, I will present it after. We have the DMD technology, and I think it was mentioned by OSRAM Continental just before I have seen it. We have the LCD technology also that was investigated in the past, and we have also the laser scanning technology. This laser scanning technology, for example, is developed for the LiDAR for the moment, but it is not developed for lighting. And you can see also the pros and cons with the different technology. So what we have seen on the market for this digital solution is then the first one is the step one. So the step one, it was what we call the matrix segment with a resolution around 2 degrees. So that is to say that each segment will have a resolution of 2 degrees. And you have, for example, on this one, something like 11 segments. This solution was not implemented in Volvo. On the picture, you can see ODTT, for example, with this matrix solution. So the second step was developed with more pixels, and not only one row of pixels, but 3 rows of pixels. So you have it, for example, of the Polestar 2 developed by Volvo. And on this car, we have 84 pixels. And then the resolution is better. The resolution is around 1 degree. When we see which technology we have, so we have a module like this with 84 pixels. And then when you project this light on a screen at 25 meters, you will see these pixels. And then it is not enough to have a good performance, so you add also an additional module to put more light, especially on the base light, so at 20-30 meters. And then with this solution, for example, you have a power consumption around 130 watts per car in low beam. So as a third step, our competitors, especially Mercedes and Audi, they have just launched what they call the HD technology with the DLP solution from Texas Instruments. So this DLP solution will be able to address 1.3 million pixels, so a lot of pixels, a lot of resolution, but just in a small field of illumination. So we will have a reduced field of illumination in horizontal and vertical. And then, if you want to be able to do the complete beam pattern, low beam and high beam, you will need to have additional modules to be able to complete the high beam. So it is the light you put in the green, for example, here, and also to complete the low beam, it is the light you will have to put in this module. And just this DLP technology will just do one part of the beam, which is in red on the picture. If you see, for example, what is the solution defined on the Mercedes S-Class, presented, I think, in December this year or last year, you have one DLP module, which is this one, and then you have 2 other modules. So you have not only one module, one DLP module to do the complete beam pattern. And how does it work? Indeed, you will have a light source. always on, all the time, with a very high power consumption. And then you will have the DLP technology with micro mirrors. We will put light or not on the road. So all the light will be always on all the time. So when you see this technology, it is very good improvement because the resolution is very good. But the drawbacks of the technology is that you have a very high power consumption, because for the DLP technology, you have to have always all the LED on to be able to do a beam pattern. And also the micro mirrors will do like windows on off to put light on the road. And then you need also an additional foreground for the low beam. And then at the end, you have a power consumption for the low beam between 150 and 200 watts per car, comparing to the pixel technology, which was around 100 watts per car. So what is the problem? I mentioned stop. What is the problem? When we speak about LEDs, for everybody, especially when you go to IKEA, LED, it is power consumption saving. So you will reduce the power consumption. If you check, for example, what we have in the past, I mentioned this picture with halogen lamp, a low beam, it was 150 watts per car. If you go to LED low beam, when you have a good optical system, very efficient, you can reduce a lot the power consumption. You reduce it by 3, by 4, by 5, and you can have between 20 and 40 watts per car. But what we have seen today is that with the power consumption of the DLP technology, you will be above the bulb power consumption. Bulb power consumption 150 watts per car, DLP can be between 150 and 200 watts per car. So this is not a good orientation. Why it is not? Because all the car makers now, especially in Europe, but it will come also in US and it will come in China, we will have to reduce our power consumption. So perhaps you know, perhaps you do not know, but the equivalence between power consumption and gram CO2 is around 1 gram CO2 is equivalent to 50 watt power consumption. So if you have 200 watts for the low beam, that is to say that you will have 4 gram CO2 just due to the low beam performance. And if we speak about battery electrical cars, so what we call BEV, so it is more complex to calculate because you can have the size of the battery you want. So at the beginning, we say power consumption is not really important because we will increase the size of the battery. But then we have discovered that battery is very expensive, very heavy. It can impact a lot the aerodynamics. And also, if you have a high consumption, then you will need a longer time to charge the battery. So this is not the nirvana, the size of the battery. And then the power consumption is also very important, and I think more important than when you have a thermal combustion engine. And then you can see that it will depend on the size of the battery, but 200 watt power consumption can be between 1% and 5% of the global power consumption of a car. So you will reduce a lot the distance you can do with the battery and the autonomy if you have a very high power consumption for the low beam. And the stake for the next decade is to reduce the power consumption, especially for lighting function and for all others like heating system, like seats, like safety, like camera, and so on. So what are the stakes indeed for micro LED? So what is good with micro LED technology is that you have a lot of pixels on the light source, and when you project the light on the screen, you will see also the pixel. So one LED on the micro LED will be 1 pixel on the road. It is not what we have today with the DLP technology, because with the DLP technology, you put all the LED on in the same time, and then you remove the light with the micro mirrors technology. And then due to this solution, you will be able to do a lot of solutions, so infinite solution for lighting, road markings, video, you can do exactly what you want. So this will be the digital lighting step number 4. And it is already on the market, or it will come on the market. All our lighting suppliers like Valeo, Automotive Lighting, Ella, and others are working on it. So you can see, for example, one module presented last year, I think, in Munich during DVN meeting by Valeo. So the module seems to be ready. And you can see that the power consumption, so the maximum power consumption, will remain important. You can have 55 watts just for this module. And also, you will need additional low beam and high beam module. It is not a standalone module. You have to use it also with other functions. But because you will switch on only the LED you want, the target power consumption for the low beam will be, with this technology, 100 watts per car. So the same power consumption that what we have today with the current solution with low beam, with pixel solution, for example. And the setup could be, for example, always with an additional foreground module, like what presented Valeo, but it could be also with 2 micro-LED modules, so without other optical module, or it could be also 1 micro-LED module, 1 unique one, but then we have to have a larger field of illumination. And also with this technology, we can have other benefits. So we can have a huge cost reduction. We can have also a packaging reduction. So the size of the module will be smaller. We can save weight. So we estimate that we can reduce by 2 the weight of the module comparing to DLP. And we can have also a simplified thermal management because we will have less heat dissipation. So we can change all the plastic in headlamp. So I think it is my last slide, but what we can see now for this digital lighting step 4 with micro-LED, the pre-development is now, the development I think is ongoing. Perhaps the step, what I call it 4.0 is perhaps frozen, but we will have new step 4.1, 4.2 and others. And then for this new step, we would like to increase the field of view, field of illumination to have perhaps only 1 module instead of 2 or 3. We would like to reduce the power consumption. We would like to reduce the packaging. We would like to improve the lighting efficiency. And we would like also for our designer to reduce the size of the outer lens of the module. So thank you. I will be ready to answer to all your questions.
You know, when you give a presentation like that and you finish with thank you, thank you, Paul. Thank you for one. I would say this is the best end user presentation I have seen in the 5 years I've been CTO of Epic. I have to congratulate you. This was outstanding, outstanding. There's a lot of room for discussion. So I want to just select a few questions I got in the chat to see that we can do something together. The first question is about the combination of headlights and LiDAR. Is there any potential cooperation there? Is there a dream? Is there a roadmap to actually combine headlamps and LiDAR technologies?
So we have no plan. I think it is too early to combine the same light source and the same optical module. But what we want to do is to use the LiDAR technology for detection. For example, you can detect with the LiDAR the wet road. And then if we have a wet road, you can change the beam pattern of the lighting to avoid to glare, for example. So you can use the LiDAR for the lighting, and also the lighting can be used for the LiDAR detection.
It is quite well specified that the technology, the micro-LED technology is lightweight, of course. The electronics behind it are not so lightweight. Sometimes the temperature control is not so lightweight. We need to work together to make this lighter weight. Is that correct? Is it still a challenge to have the reduction of cost, but also size in micro-LED modules?
Yes, if you have seen what I presented about the DLP technology, I think the depth of the module is 150 millimeters, so 150 millimeters. So it is huge. We would like to be able to reduce this to 100 millimeters. 100 millimeters, it is a common size for a lighting function. So if we can reduce 33% the size of the module, it could be very good. Because today, if you have 150 millimeters, you can put in a car like a Mercedes S-Class. It is not a problem because the car is very long. But if you want to have in the B segment, in the C segment, it is not possible to have this depth of module with 150 millimeters. It is impossible.
In previous conversations, we talk a lot about the need to increase also the AI collaboration with the photonics collaboration. At some point today, when you talk about the micro-LED arrays and the DLP, it was clear that you need some kind of intelligence to be able to subtract light for spots that don't need to be illuminated. Is, in your opinion, right now, enough cooperation between the AI and the hardware people for actually addressing these issues?
Yes, it is important to address these issues, but after that, I do not know if you have to do it with the car makers or with the set makers like OSRAM Continental or Valeo or Ela, all these suppliers. So perhaps the best solution is to work with the car maker and the lighting supplier all together to be able to define this sort of strategy and what could be good.
The best way is
to work all together.
The best way, of course, Paul-Henry, is to do it with all of them, at our online technology meetings when we bring the entire supply chain and we try to answer the epic question, can you do for them or can they do for you? And Paul, you answered it perfectly. It was a great presentation. Thank you so much.
Thank you.
Volvo gave this fantastic presentation and gave me the chance to send all of you for a 14-minute break. Do your best with a positive mind, with a smile in your face like mine, with a lot of energies. Do your best to see if we can actually use the chatting, the networking room, which right now has more than 100 people chatting. Go there and see whether we can do some getting to know each other better. I see you again at 5 o'clock. Welcome back. It is 5 o'clock, 1 minute past 5, and this session now, after the amazing program so far with ASML, with Siemens, with Volvo, this session now is not our 4G, it's our 5G. I really am working a lot on this topic for the last month with my colleague Tracy Vanik on developing a market report on this with the collaboration on market of fiber reality. You're going to be amazed by what we are putting together on that. But today, to talk about 5G, we really wanted to have an operator and the driver of the whole community on this. We have Telefónica and Cisco. And for that, I really want everyone in the room, and I know we have 316 people listening to this. I want you to post as many question challenges or just simply the name of your company in the chat, because I really want to start new cooperations here. First, let's go to Spain. I'm Spanish. Buenas tardes, Telefónica. Oh, I feel so happy saying that. Thank you very much for being with us. Let's go to understand a little bit how the optics community can help Telefónica in their new project, MAST, in optical networking. The floor goes to Juan Pedro.
Thanks a lot, Jose. Please let me share you my screen and the slides. I hope you can see that.
Gorilla Glass clear, and the sound is perfect, the image is perfect, the quality that Epic deserves.
Okay, thank you. Okay, I'll try to explain you, first of all, what is an open optical network and how this kind of networks, the open optical networks, could help operators as Telefónica to easily introduce new technologies in the optical layer. For example, optical white boxes, new data center interconnection solutions over the existing networks. And also, I would like to present you the MAST initiative, that is a group of operators where Telefónica is collaborating with Vodafone, Deutsche Telekom, Orange, MTN, and Telia in order to speed up the implementation and the development of these open optical networks. So the first point is, okay, what is an open optical network? And in order to explain that, let me present or describe what is the current situation. Currently, in the optical transport networks and the operators, we are using proprietary configuration and programming interfaces by the vendors. This means that if we want to include some automation in the network, for example, for dynamic restoration of a wavelength, dynamic service provisioning, or include an automatic planning tool in the network, then we have to buy every single component, the end-to-end system, to the same vendor. For example, we need the transponder, the ROADM, the amplifier, and also the network management system from the same vendor. As a consequence, if we want to introduce a new technology, something new appears in the market, for example, a new solution for 1 terabit transmission or whatever, we have to wait until the system vendor is including this solution in their portfolio, if they want or if they can do it. An example of that, and this is what we are living nowadays, is currently we have multiple solutions for data center interconnection in the market. But if we want to deploy these new solutions for data center interconnection, for example, from Cisco, from Infinera, from Siena, over an existing optical network from a different vendor, Nokia, Huawei, or whatever, then, okay, we cannot do it while keeping automation. So we can do it, but if we manually operate for example, the systems. So the operators have to do a balance, or have to decide between having network automation with dynamic service provisioning, planning, restoration, and so on, or having a multi-vendor network with transmission systems from one vendor and, for example, optical switching devices from a different vendor. Anyway, I think the idea is this could be solved in an open optical network. And this could be solved if we use open and standard interfaces for both, for the device configuration and also for the network programmability. There are two kinds of interfaces that should be used in an open optical network. We have on the one hand what we call the northbound interface. That is, an interface is an API, a programming interface that exposes an abstracted network view of the complete optical network towards the applications on top. For example, service plan or planning tools, activation tools, performance monitoring tools, or whatever that is interacting with the optical network. We need these interfaces in order to enable the network programmability. And we also need standard interfaces for the device configuration. For example, we call it the southbound interfaces. For this device configuration could be interfaces in order, for example, to select the output power in a transponder, the wavelength, for example, the modulation format in a variable bitrate transponder. And with this, for example, with this combination of northbound interface, standard northbound interface to the applications, and standard southbound interface towards the applications, then we can build up an open optical network. Let me say that, for example, currently, if we want to introduce or deploy a new application in the network in order, for example, to optimize the network resources using artificial intelligence or a planning tool or whatever, we need to do a specific and ad hoc software developments for each vendor, because each supplier is implementing a proprietary interface for the northbound interface. In Telefónica and also in the MAS group, we are selecting TAPI. TAPI is an interface that is being defined in the ONF, and it's a standard one, vendor agnostic, so that as one application, something that is developed over TAPI could be used in any vendor implementation without additional adaptations. Furthermore, if we combine both the TAPI, or standard programmability interfaces, and the device configuration, we could have this combination of network automation. We can have network automation in the network with dynamic service provision and restoration, automated inventory, and so on, in a multi-vendor network with partial disaggregation. Partial disaggregation means that the transponder, the transmission, could be from one vendor, and the switching, or for example, the ROADMs, the amplifiers, and the rest of elements in the network could be from a different vendor. Regarding the transmission, okay, the open terminals, this could be anything, could be colored interfaces in IP routers, they could be optical white boxes, they could be, for example, new data center interconnection solutions, or a transponder from a different vendor. We can have this combination of transmission from one vendor and transport or switching devices from a different vendor, and keeping automation. We can have it if we implement the open config modeling, as in the standard modeling in the transponders, in the transmission. They should understand and be configured with these interfaces, and also the support of this open config transmission. Either there are two options. They could be configured by the SDN controller or the network management system of the optical line system, the existing vendor, for example, that is providing the ROADMs. Or there is another option, is that, okay, if the SDN controller from the existing vendor do not support the open config, we can have the configuration of the open terminals, of the third-party transponders, whatever, by an external entity, an external application that is configuring, for example, the transponders, selecting the wavelength, the modulation format, the power, and so on, and also configuring the optical network, selecting the path, for example, what is, and configuring the ROADMs in order to do the required switching, using the TAPI, the northbound interface. And both would be standard. Now you may wonder, okay, this is technically feasible. The vendors are implementing this, or this is just a dream. Okay, we were wondering that last year when in Telefónica we hosted the OEF 2020 Transport SDN Interoperability event. In this test that were carried out between September and December last year, we tested the maturity of SDN controller implementations by different vendors, and also the interoperability of the interfaces, of these standard interfaces. Here in this picture, you can see a high-level view of the architecture that we tested. We combined, for example, from the hardware perspective, ROADMs, amplifier, an optical line system from different suppliers. In particular, we work with Siena, Nokia, ADFA, and Infinera. And open terminals is third-party transponders from Cisco, Siena, and Nokia. We did different combinations of them. The optical line system was configured. The light path were configured by the domain controllers from each vendor, but using requests that were coming from TAPI, from the standard northbound interface. And the transponders could be configured either by the domain controller from each open line system vendor, or by an external application that is a hierarchical controller that is also doing an orchestration with the IP layer. As a result of this test, in this test, we checked the interoperability for different use cases. For example, then we tested the network automation for service provisioning, topology discovery, traffic engineering, resiliency, performance and fault management, a wide number of use cases, and around 65% of these use cases were passed without issues. This is a very high amount and a very good result, because we have to take into account that the TAPI or the standards were released in July, and this test started in September. So one idea is that if once the standards they are defined, and if they have a clear specification, then the vendors could be really fast implementing that. I will go very briefly through the test that we did. For example, for the northbound interface, that is the programming interface that providing an abstracted view towards the applications on top, tools for more performance monitoring, service activation, or whatever. We tested use cases about, for example, discovery, in order to expose the complete network, the topology, and the services that are running on the network through this standard interface. We also tested the connectivity provisioning. For example, a given single wavelength or multi-wavelength connectivity, excluding or including given paths or nodes. We also tested how to fill an inventory using the information from TAPI. We also tested how to deploy or activate new services with different protection mechanisms, restoration or 1+1. And also how to take information about the alarms monitoring or fault management. These are, the novelty is not in the use cases. These are the day-by-day use cases that we are using in a network operator to maintain the network. The key novelty here is that, okay, these use cases could be activated using a standard and vendor agnostic interface, so that any software development any software developer could use this interface in order to activate these use cases. From the open terminal testing or regarding the device configuration, we also did a test of an important sample of operations that can be done over a transponder, an open terminal. For example, how to, in terms of discovery, requests about the configuration and the state of a given optical channel, a port, or for example, how to configure and establish an optical channel, configuring the wavelength, the power, and the modulation format of a given transponder. Also the service deactivation, and request about the counters for performance monitoring, the bit error rate, the temperature, some physical constraints. Once again, here the novelty is that we can use an standard and the same modeling for the different vendors, so that we don't need a specific or ad hoc implementations or software implementation for the different vendors. As a result, I think the results were very good. All the vendors were supporting totally the OpenConfig and the TAPI. And this means that, okay, if we have a good technical specification for these use cases, then the vendors could implement that and they could do it very quickly. According to that, in Telefónica, we also agreed, and we have working with other operators in order to push and accelerate the technical specification of these interfaces and also speed up the implementation of the open optical networks. According to that, we founded a group within the Telecom Infra project. This group is called MAST, the acronym for Mandatory Use Case Requirements for SDN Transport. And here, what we are doing is working together in order to define what are the use cases that are interesting for the network operators, and for each use case to design and technically specify the interfaces, the open interfaces for device configuration, and also for network programmability. These operators are Telefónica. We also have Deutsche Telekom, MTN, Orange, Telia Company, and Vodafone. You can find more information about this initiative and this group in the TIP, in the Telecom Infra Project website. There is a white paper there. And the important is that it's not only the white paper where we are showing, for example, what is the architecture that we are following and the working methodology. We are also uploading the technical specifications that we are requesting for the different use cases, for the device configuration, for the southbound interface, and also for the northbound interface. The first block of use cases or common technical specifications that we are using also as common technical annexes in our procurement processes will be uploaded in the TIP website, could be publicly, could have public access by next week. And we are also planning to have periodic quarterly reports with the technical specification for different blocks of use cases during this year. I will conclude my presentation also with the key messages. The first one is network automation is critical for the network operators. It's critical nowadays in order to provide the required quality and optimize the network resources we have for the existing services, but would be even more critical in 5G, where the traffic patterns, the amount of traffic, and also the dynamicity of the traffic would be much higher. Also, network automation is a must. And then also taking into account the network automation is a must, we need also more agility in order to introduce new technologies, new optical technologies, in order to face the traffic increase in a cost-effective way. And have more flexibility in order to accelerate the introduction of new technologies and vendors. We can do it if we have open standard interfaces for device configuration and network programmability. Then the open optical networks would enable that. In the OEF interoperability test, we demonstrated that this is technically feasible. We can have these open networks if we have a good technical specification of the use cases. And in this case, important is the telcos, as Telefónica and the others, should take the leadership and are taking that leadership in terms of even designing these interfaces, because we need a very good alignment and also very detailed technical specification of the interfaces in order to have a common implementation by the different vendors. And okay, that's the purpose in MAST, that we are working together with a common strategy in order to accelerate the implementation of these open interfaces. Okay, that's all. So now would be pleased to answer any question you may have.
Oh my God, a lot of questions, but thank you very much. Muchísimas gracias, Juan Pedro. It's been such a fantastic day asking the end users about their dream of photonics, and today you talked to us about the work on SDN from Telefónica, and as you have heard before, Epic is working very hard on preparing a 5G report, so we got quite a lot of input from you on this. The first question that I have for you is about timing. Timing is synchronization is always going to be the biggest challenge. How are you addressing it? And perhaps what challenges and what opportunities for collaboration do you see in the synchronization and timing aspects?
Yeah, as you mentioned, timing is key. Is one of the use cases that we have to address during this year. Sorry, yeah, this is timing. I think I say. For 5G, we need a very low latency, of course, and mainly if we have a virtual run. If, for example, we have an optical front haul, and the only way to have a very low latency is having optical transmission. We have two options. We can distribute also the edge, the IP routers, so the electronic edge of the network, or we can concentrate that and use optical transmission. I think the second option is much more cost effective. I think most of the cost, most of the investment in the network is in the IP. And okay, if we can have passive optical networks and direct optical connection from the 5G stations and the core and the network core, then we could really simplify the network infrastructure and optimize the cost. But in this sense, we need to reduce the latency and take into account the latency. And this is only feasible with optical layer and, for example, avoiding the intermediate OTN switching. This is one of the use cases, but in terms of, for example, of optical or device configuration, is not a challenge. It's mainly a question of network planning. We can solve the synchronization and the latency issues if we have the right planning, rather than, for example, a network automation in the network.
Juan Pedro, stop sharing the screen because I want to see you full size. No, it's okay. Don't worry. I wish I could have done it for you. But let me ask you something. I'm a big fan of Telefónica. You have made multi-vending, working with multi-vendors. You have made it an art. And you're working already with ADVA, with Siena, with Cisco, with Infinera, with Nokia, ADVA and Infinera Epic members. I would like to ask you, when it comes to the open config, is there still some challenges for operating with multi-vendors?
Sure. This is extremely complex, and the main challenge is to clearly specify how the open config modeling should be done, because each vendor have its own even hardware implementation, but we need a single definition of, for example, how a service is provisioned. This is not an easy task, and the only way to have this is if we have a clear specification and a common specification among the operators. If we establish a single way of doing things, and this is exactly what we agreed in MAST. The only way to speed up the implementation of these open interfaces is if we have a single way to implement each use case. And of course, we need to provide a guiding to the system vendors, because if we have more different options, then at the end, all the process could be delayed. Yes, it's not. We have demonstrated that this is feasible. We are started with for example, with the use cases for service provisioning, inventory, and traffic engineering. But there are lots of things to do. For example, in terms of performance and fault management, we still need to define the open config modeling for all these use cases. And this is, for example, one of the main challenges in MAST.
Juan Pedro, today is a fantastic day in terms of logistics. Please switch on your camera. Sorry for that, but we are hearing you loud and clear, and that was a very good message. The next question is coming from one of the companies close to my heart. In Eindhoven, we have a Smart Photonics, the pure play foundry for indium phosphide, and Spiros Mikroulis is actually asking you a very smart question. How do you see the challenges in terms of timeline on the need for optical interfaces reaching higher speeds, functional modules, and integrated photonic components to meet the needs for open optical networking for 5G? I'm going to summarize it in one sentence. We have lots of companies working with photonic integrated circuits, with silicon photonics. They're providing transceiver solutions to your vendors. How do you see the potential for innovation for these vendors to satisfy the needs of Telefónica?
Okay, I think what's important is that if we can have pluggables, the integration, for example, of the photonic switching and the DSPs in a single transceiver that could be installed, for example, in the IP routers, and could be important, manageable, and configured by software, I think the potential for that is, the potential is huge, because this could give us the flexibility to, on the one hand, we can minimize the total investment, the number of elements that should be controlling the network. A pluggable including the DSP and all the photonic components in a single element that could be installed in an IP router could be a great advantage with respect to what we have nowadays. Furthermore, if this pluggable, for example, if this element could be configured by software by an SDN controller, then we could have all the flexibility we need, for example, in order to cope with the 5G requirements in terms of capacity and flexibility. So I think that's one of the key is having this integration with trying to minimize the power consumption and the space to have this pluggable, including both the DSP and the photonic components and the full configuration by software.
Juan Pedro, we talk a lot about the 5G, about the SDN, the software-defined networks, but I cannot let you go with asking you about quantum technologies. You know how important that topic is for the future or the sustainability of photonics in the world. Telefónica and their test beds have been driving the quantum key distribution. How do you see this? Perhaps can you spot maybe some room for cooperation in your test beds?
Sure, we are doing some currently in this year on the first trials with in Spain. We really see a future, not a future, but also a business case and a market for this the quantum cryptography. One of the main, of course, I think this is one of the topics where the collaboration with the industry could be more interesting, because at the end each implementation for quantum cryptography is different. There are a lot of potential for banks, for example, the main customer, the client is the government. No, so with the quantum cryptography, is like the most secure technology that we could have. Yeah, I think we really see an application for that. We are very actively working on that. And in particular, this year, we are carrying on some trials. And of course, we are totally open for collaboration on this.
On that, you have really been fantastic. The test bed in Spain for QKD has incorporated technology of many of the EPIC members. And of course, here I tell everyone, all the people who are active in quantum technologies, stay around EPIC, because we are going to push this like crazy. And we're going to push companies like Telefónica Telefónica, like Deutsche Telekom, like BT, to let us in with all the photonic industry. Juan Pedro, muchísimas gracias por esto. Thank you very much for being part of this amazing day. And I would like to say, until the next time, nos vemos pronto.
Thank you.
This has been a really fantastic day. Why don't we now, with a positive mind, because I'm getting a lot of WhatsApps, you know, everybody is telling me, are you aware, Jose, that we are having so many technical issues? Of course I'm aware, but this is the way I live life. I switch on a light instead of complaining about the darkness. We are addressing this where Fleet Event is going to send an email to all of you exactly, I think at 6 o'clock, or maybe they had done it already, with what's going to happen tomorrow and how they're going to address the technical issues they've been having today. But today, I had so much fun. I really had so much fun talking to end users, and all the footage that they have collected, plus all the lessons learned that we have collected, we are going to make sure that you get it, This has not been a wasted day. It has been a crazy day asking end users for potential photonic cooperation. So we're going to make them happen. If you want to get in touch with any of the participants today, and I know that's a lot to say, you want to get in touch with any of the participants today, send me an email, jose.pozo@epic-asoc.com, with the reason you want to get in touch with them, and I will make an email introduction so you do business, because this is what drives me. This is what makes me happy. Until tomorrow at 2 o'clock, with another fantastic program with end users, I would like to wish all of you a nice evening. You are at home with your families. We didn't travel. Spend time with your family and enjoy. I would like to also let you know that we have about 200 people in the networking room. So you want to get to know each other better, go to the networking room. And we also have the booths operating. So go there, try to see if you can get some of the booth action. And if not, tomorrow will be maybe a better day. Today was amazing for me. Take care of each other, wear a mask, wash your hands, and stay safe. Good afternoon, everyone. It is 2 p.m. in the Netherlands, in Europe, and we continue making history. Yesterday was an epic day. Many people enjoyed the presentations. Others are going to get the footage. And today, with the fingers crossed, with a lot of positive energy, we continue trying to get the unmet needs from the end users of photonics. Yesterday, the presentation from Volvo, the presentation from Siemens, from OSRAM Continental were spectacular. But today, we're going to have L'Oreal, Intel, Global Foundries, Quartus Engineering, Valeo, Arcelor Mittal, and we start in this session about laser-based material processing. We start with one of the biggest business opportunities today for the solar industry in photonics. Hanwha Q-Cells has a pilot line in Germany incorporating R&D from any company that is actually here willing to help. With this, we would like to hear a bit more about the international technology roadmap on trends and laser applications for photovoltaics from Markus Fischer, Vice President of R&D Cooperations of Hanwha Q-Cells. Markus, thank you very much for being with us this beautiful afternoon. The floor and the attention of everyone is yours.
So thank you very much for this nice introduction. So it's a pleasure to me to contribute here to this nice conference. And thank you for your interest also in the photovoltaics. So photovoltaics currently are a key for all the future carbon-less applications. And therefore, I want to give an introduction about the current status of photovoltaics, the learning curve, and especially surely the laser applications. And then I give some insights about current situation of Hanwha Q-Cells and also an outlook. So let's start with the status on ITRPV and especially the learning curve. I think most of you heard about learning rates and learning. So in all the industry, it is quite common. And here we have for the photovoltaics also a very impressive learning over the last years. So this data here in this graph show the average spot market module prices, so PV module prices and versus the shipped volume of this modules. And there's always a difference between shipments and final installations. So, and what we see here over the years, so starting in 1976, so there the modules were at the price of over $100 per watt peak. So this is the normal measure we have. So price piece per watt peak and cents per watt peak. And the current price is that we see here about 20 cents. So the calculation is not completely finished. So 20.4 cent, 21 US dollar cent per watt peak. And what is very important here is the shipments from 2019 were about 130 gigawatt peak. And this year, despite all the troubles we had with COVID, we reached 133 gigawatt peak, so slightly more. And this leads to overall shipments of around 787 gigawatt peak and installation, so close to 750 gigawatt peak, so 3/4 of a terawatt. So this is very impressive. And yeah, so what we see here, so this is the shipments and the installations, and the production capacity is much higher. So about more than double the shipments. And this shows that there is a increased energy in the market, and there will be price competition. And we are on a track that we will continue the learning, and the learning rate, if we take all the values from 1976 to 2020, so 20 is the last value. So we have a learning rate of 23.9%. That means if when the installation is doubling, so then the price is reduced by about 23.9%. And what we see here, so we had since 2006 accelerated learning, and what we see is that this learning is continued. So last year, 2020, we had high volume shipped with increased product diversity. So a lot of new products were launched, and we had a slight increase in 2020. This ship volume was expected at the beginning much more, but anyhow, so a slight increase, and we had some new module concepts, new module sizes, new wafer sizes. But one thing is clear: the PERC, passivated emitter and rear contact, is the PV workhorse for CCPV. And what we see is that the price learning is continuing. So if we have here this chart and look here in the details for the different years, so we see that we had several laser applications in the PV. So there are some special applications. So we started here in 2005 with laser edge isolation. So 2009. QSers introduced laser marking. So then there was an intermediate phase of laser fired contacts, also laser use in the contacting of the solar cells. Then what is now contributing to the working horse, to the PERC technology, laser contact opening. Then a new module technology with half cell cutting, selective emitter, and yeah, we will see what will next laser. It's not so clear so far, but these are the main applications: LCO, half cell, and selective emitter that are currently in application. So now I will show some details about the different technologies. So what I mentioned here, we see the share of the different technologies here in the present and for the next years, and there we see the PERC, what I mentioned here, passivated emitter and rear contact, double-sided diffusion cells are the workhorse. Then we see heterojunction. Heterojunction is unfortunately not using so much laser, but here for the PERC, it's losing a lot of laser, and back surface field also not using laser in such a high quantity than the PERC technology. So also new technologies, tandem will appear. So from 2023 onwards, we expect this. But anyhow, main market and main workhorse is the PERC technology. And what we see here, there's also a possibility of bifaciality. So that means the modules are capable of collecting light from the front side and from the rear side. So this is an important point. Yeah, and now to some details here, especially this bottom with or this column part with 68% is now in more detail to see here. So we have here on P-type monopercs the main volume currently. This will be reduced a little bit, and passivated contacts will gain some market share. But here, the main technology currently in place is this cell type. And where is the laser used? The laser is used here for conducting here the rear side metallization to the silicon bulk. And you see here some examples how the rear side is looking like. And yeah, so what kind of laser is used in this? So it's a laser with 532 nanometers, about 30 watt power, and with 1.2 megahertz pulse. So these tools are really challenging regarding throughput. So 6,000 wafers per hour have to be treated here with such tools. And the biggest challenge is, so you have this lanes here of marking and contact opening. You have to maintain over a width of currently 158 to 210 millimeter wafer length, accuracy of plus minus 20 microns, and this you have several hundred LCO lines on the wafer. So this is a big challenge to the laser application. So then I mentioned here selective emitter. So selective emitter is something that happens on the front side. So we see here the big trends. So we have one thing here, the homogeneous emitter that is not applying the laser, but here we have the selective emitter. So there we have a sheet resistance so of up to 150 ohms per square expected in the future. And what is the challenge for the laser? So you have here this laser doped area. So this is a laser that is scribing over the wafer to to have a additional doping, and then the finger is printed above this. So and the width of the laser doped area is between so currently mainstream is 120 micron, but it is reduced currently also to 80 microns, and the finger width is below 30 microns. So this has also to be aligned. So a big challenge here. So, and we see laser doped selective emitter is currently mainstream, especially in China. So, and here, what I mentioned, one application for the photovoltaics that is currently also becoming mainstream, this is half cell module. So in the past, most of the modules applied here full cells. So you see here an example of a full cell with four bus bars, or with 6 to 9 bus bars. This is the mainstream currently. So, and how to get here a cost-efficient way to make here smaller cells, to make a little bit the power loss, to reduce the loss that is caused by resistivity. So by laser cutting, you can cut this cell into 2 pieces, and this is shown here. And then you have a half cell module that has much higher power. So about you can reach, compared to the same number of cells for half cell and full cell module, about 10 watt can be reached more. So this is a good thing, and that's why it's becoming currently mainstream. So that most of the modules produced are half cell modules. And there are 2 methods of cutting the cells. So one is laser scribe and break, and the other is scribe and cleave. And there you can use here different laser types. The challenge for this application is to really avoid cracks. So and this is what I mentioned here, a specialty of Q cells. So we have a special laser marking method. So each laser is marked with a dot matrix code, and with this dot matrix code, you can really get here a traceability within the production line, and you can here efficiently check for the performance of the line, and also you can check the quality also in the field. So let me show now something about Hanwha itself. So we are currently positioned here with 9.6 gigawatt of cell production capacity. So the R&D center is in Germany, and we have production sites in China, Malaysia, Korea, and in the US. US is only for modules. And the current activities that we have here is to improve the efficiency of our cells. So the current lead product is the Quantum Duo Z module. So this has a half cell module that has also technology that has zero gap between the half cells. So with this we can reach here module powers for rooftop application and also for large field application between 360 watt, 430 watt for this rooftop application, and up to 460 watt with this power plant application. So and here, this is the learning we had over the last years, and we have in mass production cell efficiencies of above 22.3%, and in lab in our pilot line that you mentioned here, we have this efficiencies of more than 23.4%. In our pilot line here in Germany, in Thalheim. And for new concepts, so beyond this PERC-like concept quantum, so we are looking also for new concepts. This is what we are doing. And Q-cells itself has a broad variety of applications. So the core where we are coming from is cell manufacturing and cell production. We produce modules, we deliver parks, we now also go downstream also to selling green energy. And so this is our contribution to the carbonless future. And this leads me to the last chart here to have a brief look about PV today and in future. So in the ITRPV, we always look on the trends and the outlook, and you see here the requirement is to have in there's a projection of 2050 to have up to 63 terawatt peak installed. So today we are with about 750 gigawatt only. So and what we see here, this is the market of the PV modules and also for PV manufacturing tools. So we expect here that the market with the different trends will grow significantly up to 1.4 or up to 4.5 in the most progressive scenario, 4.5 terawatt peak. So remember, 300 gigawatt are currently in the market as a market capacity. And this shows, so here the current shipments are marked here. So we are close for this ambitious scenarios a little bit beyond the schedule. So, but we are quite sure that the next steps with our technology will continue the learning. And we are able to meet these challenges and to meet really here the challenge to produce more modules and for the future. And the ITRPV will provide also future guidance to handle the current challenges. So thank you very much. So and now you have time for questions.
Thank you very much, Marcus. I can't believe how much information you gave us in 15 minutes. I will have a lot of work to process all this information. There is a lot of room for cooperation here. And as I said before, Hanwha Q-Cells has the pilot line in Germany and looking always for R&D cooperations. I have some questions in the chat. The first question comes from Alexander Teye from Agdar. By the way, Agdar is one of our EPIC members in the black coatings, making the absorbable mirrors. And Alexander has something in mind. He says, you talk a lot about laser technologies. What about other photonic technologies besides laser, for example, for quality control?
So for quality control, so we have no real laser applications, but we use cameras, cameras that inspect the cell and the module, and then we have applications for reading here the EL, or looking for the EL image, electroluminescence images, to make the quality control, and for our dot matrix code reading. So there we use also camera. So laser applications in the quality control are not so common currently. So, but what is a trend here, especially for flashing, for testing the modules? This is an application for light emitting diodes, so for LED. So currently we are using flash lamps in the flashers. So this is a flashlight to illuminate the cell or then the whole module, and there we apply in the new trends and new systems also LEDs. So this is a new application, but laser in the quality control not so far.
Fantastic, Marcus. You talk about the laser scribing. You talk about 1064 50 watt pulse and 1070 30 watt CW, and that was very interesting for scribing. What I have seen a huge trend for Europe right now is the development of ultra fast lasers for surface structuring. Is there any activity, any potential cooperation on surface structuring based on laser technology?
Yeah, surface structuring, maybe it can be used for the glass structuring, but so far the structuring application in PV modules is mainly for then laser marking, also for making barcodes there, or then in the production process itself. So laser structuring is not so far not implemented here.
But you will, because I have a lot of introductions to make about this, and you will be amazed.
Would be interesting,
Another question in the chat is from a very interesting company in France, Kiowa. They are really excellent on actually doing programmable beam shaping. And Floranti Vol, the CEO, has a question for you. Are the laser-related tasks like PERC or doping a bottleneck for cell production?
So this is the doping is for cell production, and here also the laser marking, So this is in the cell production lines. So here for module, there are only this intermediate application for the cell cleaving and cell separation. So this is the main application for lasers in the industry. But maybe, so if you have some good ideas, so let us know, and then we can check if we can apply and can make some crazy and new challenging applications. So this would be good.
This is the best part with you, Marcus, that you always are willing to try new things and try to start new cooperations. I'm sure Florent is gonna contact you offline. The final question is not technical. The final question comes from somebody called Carlos Lee. I don't know if you met him.
Carlos,
he's wondering.
So Carlos, yes.
He's asking, is solar manufacturing still relevant in Europe? Is his question, not mine.
Carlos, this is a good question. So. Solar manufacturing is an important thing. It's also a strategic thing to have manufacturing of cells here. But so far we have the big challenge about the value chain itself and about the competitiveness of the pricing. So, and we have here several module manufacturers in Europe. So this is good. So it's also an efficient way of shipping the cells from China and building the modules here. So shipping the glass is even expensive or more expensive than shipping the whole module. So some companies are starting to do cell production here. So we have in the Solar Valley also one company, Meyer Burger, they start cell production. So anyhow, it's a possibility. It's of interest. So so far, module production is in Europe, still active, and for cell production, we will see what the future brings.
I do believe, I'm a strong believer on pilot production when it comes to customized solar cells. And I do believe that there are new companies who are targeting, for example, the solar windows, who are targeting new solar cells in drone industry, whose volume maybe is not interesting for Asia, but for the pilot production to scale up to medium size is a great opportunity for you. And I think on that, you've done a fantastic job. Marcus, thank you so much.
Okay, you are welcome. And please let me know if you have questions. And for this presentation, you can download it from the ITRPV homepage or contact us. And for more details about Q-cells, also have a look at our homepage. Thank you very much.
Thank you so much, Marcus. And we continue with the amazing program. Now we know to one of the top multinationals on steel processing. We go to Arcelor Mittal. With Arcelor Mittal, we work a lot already on different laser technologies for automotive manufacturing, for naval manufacturing. We want to know a little bit what kind of needs we can solve with the technology of EPIC member. And for that, we have Juan Manuel Martinez Alvarez from Spain, R&D Engineer of Arcelor Mittal, talking to us about how the EPIC members can help Arcelor Mittal, a great company, being even greater. The floor and the attention of everyone goes to you, Juan Manuel. Buenas tardes.
Buenas tardes. Thank you so much for the introduction, and it's a pleasure to be here, and thanks for the invitation to all the organization. So yes, as you said, this is a total different topic, I think. Here we are talking about steels and laser manufacturing. Then my name is Juan Manuel Martinez. I'm leading the computational additive manufacturing project within Arcelor Mittal Global R&D. And Global R&D is doing additive manufacturing, Arcelor Mittal at the end. No? We are more than 1,500 researchers all around the world, and here you have, for example, the budget structure that we have in Global R&D, dedicated for many things, as you can see, mainly for products development, which is automotive mainly, and then for process, which is related with the steel making processes, no lasers at all in those fields. But then from 2016, it was released a new budget more related with exploratory breakthrough technologies based on additive manufacturing, artificial intelligence, digital twins, and nanomaterials. So in this is related with Industry 4.0, and this is the portfolio in which I am, in which additive manufacturing is to take place in that sense. Here you have the geographical distribution of our R&D centers, and my job, the main additive manufacturing part, is located in Spain, in Asturias, and we have two centers. One is New Frontier, which is dedicated for these new frontier technologies that I mentioned. So we are here. And now what we are doing in additive manufacturing, right? In Arcelor Mittal, we are trying to cope with the whole value chain of additive manufacturing, from obviously design and production of the base materials, powder and wire, okay? Then design parts and design applications, like the ones that you have here, collaborating with many industries, automotive, aerospace, defense, no? And then we have several technologies. Indeed, we have more than 10 different technologies. Not all of them, as I'm going to present you, are laser-based, but some of them, yes. And then we have some post-processing, like, you know, we are doing additive manufacturing, but post-processing like turning, machining is obviously necessary to ensure the final quality of the parts in many sense. And we try to characterize and certify, of course, the applications. During this whole process, we try to compute every single step numerically to try to verify digitally what we are planning to do, what we are making, control the temperature, control how the laser interacts with the material, and so on. And this is about my presentation. So, as I mentioned, now in Arcelor Mittal we have several technologies, many of them related, for example, with sintering, fusion, even ultrasonic welding. But between the fusion ones, we have 5 different technologies, but none of them are laser-based. These are laser powder bed fusion, blown powder direct energy deposition, wire direct energy deposition, electron beam powder bed fusion, wire arc additive manufacturing. As you can imagine, the laser ones are the three first. As the names are quite complex and quite long, we used to call them as the capital letters, the acronym. So we are going to talk about these 3, but it's important to say that although they use lasers, they are not the same at all. So now I'm going to present you more in detail the processes. Here you have laser powder bed fusion, which is based on, our systems are based in multi-laser systems. It means that we have 4 fiber lasers inside the machine, and the production of the part is doing layer by layer. Okay, here you have a picture of the part, how it's being done by each laser and how is the path of each laser. These jumps and switches on and switches off of the lasers are very transient. It's very fast process. We are talking about microseconds from one vector to the another one. And here you have, which is the interaction of each laser with the matter. It's a quite chaos there that occurs, in which the laser melts a powder, which is deposited in a layer, then the powder goes into a melt flow. You have molten metal over 2000 degrees. Then you have some projections of the powder due to the vaporization and the delta pressure that you have in your system. And this is layer by layer. Here you have the 446 layer out of more than 3000 layers. So you can imagine that these layers are usually very small. Even 50 microns is the more normal height. This is how it looks digitally, and this is how it looks once you print it with these kinds of technology. These are 5 big impellers that we are using in our steel plants in Europe, and the diameter is around 100 millimeters, and the total printing time is around 40 hours. So it's quite easy to get these parts out from this technology. Then we have the blown powder direct energy deposition. This is being done in total different way. Here we do not have any powder substrate. Instead of that, we have a robot with a attached laser. In this case, this one is a true disc from Trumpf, 4 kilowatts in this case, with some powder feeder which blows powder with a carrier gas. The carrier gas is argon, and a special nozzle designed for additive manufacturing. Here you have more in detail, which is the physical scheme of the physics, in which we have the laser in the center of the nozzle, and then we have a coaxial blown powder throwing the powder against the laser to create this little clad, we can call it. It's a clad over a substrate. Here you have the iterations that we are doing. Any time that we try to build a part is hard, because we have to adapt, for example, the offset of the laser, the switch off, how the material is deposited, the flow rate, the mass rate that we need. And so it's a quite iterative way of printing. Remember that we are R&D, so we are trying here to explore the technology, not for printing industrially many parts. So this is the kind of things that we are doing, like, for example, testing other lasers, testing different distributions from Gaussian to top hat to TM1, for example. And then we have a new promising technology that we have acquired recently, which is wired DVD. In this case, it's not a robot. We have a nozzle attached to a Cartesian machine, XYZ, Cartesian obviously, and it has not one power laser, high power laser. Instead of that, it uses 5 low power diode lasers. This one is the old system. I cannot show you the new one because it's under development, but this system is really convenient. Why? Because you are using low power lasers, which the cost is quite low indeed. If you have any problem with any of them, you can switch it off and you can continue printing. Maybe not so well as with all of them, but you can continue printing, and it's not necessary to stop your operation. And this is the kind of parts that it is possible to do with this technology. it's necessary to say that this technology is quite difficult to handle because the heat accumulation is really high. So this is necessary to do a variation, the printing parameters all along the printing. So for example, here you have a modification of the offset of the laser to try to compensate the heat accumulation over the part. And yes, this is based on wire, in which the wire obviously is in the center of the nozzle, and in this case, the lasers are the coaxial system. Then we are here to talk about laser material relationship. So it's important to understand that additive manufacturing is pretty new, a trend in the industry, and more materials are coming into additive manufacturing each month. So depending if you are a client of a certain industry, for example, you are prone to print just steels, just titanium, probably your solution will be very easy because a lot of commercial machines handles these materials very easily. But now there are some materials, for example, copper alloys, for example, some ceramics, matrix composite ceramics, which indeed they are very reflective and they cannot be processed with the typical technology. So basically in Arcelor Mittal, we are working with systems that works in this wavelength, right? And I love this graph. I do not know Japanese at all, but I love this graph because it's very complete. And this is a relation between the absorptivity of different materials with the wavelength of the lasers, right? So we are working in this frame from 1000 to 1100 nanometers, something like that. Typical for steels and titanium alloys, it is possible to print it really well. But imagine that you want to open a new business in 3D printing and you do not think carefully about the metals that you are going to print, and imagine that you want to print copper alloys. So basically, you are not going to print anything because you need to understand that depending on the laser technology that you are using, the absorptivity of the material will change. In this case, there is a new family of green lasers being adapted for additive manufacturing. For example, this machine is a TruePrint 1000 from Trumpf. They have released few months ago a new series, which is the green series, totally dedicated for this high reflective alloys processing. Okay, so imagine that you're a client, you want to process a copper with two different lasers, one from 550 nanometers, another one from 1070 nanometers, which is the difference in amount of power that you have to apply. So you need 11 times more power. So basically, there's a lot of systems which cannot handle so much power, no? And indeed, it's really inefficient. So once we have our material melted, or we have molten metal, what comes next, right? So we switch off the laser, we let the material solidify. The cooling source typically is the time with the argon, that we use argon in every process in additive manufacturing to ensure that the oxygen do not play any role in our material. And then we expect to get exactly the same material, but that's totally false. I mean, metals are tricky. They are crystallographic materials. Probably some of you knows about metallurgy, but metallurgy it's really important in materials lasers processing of metals, steels, titaniums, and so on. So how can we know what we are doing at the end, right? We have lasers, we have materials, but we are not getting the properties that we expect. So basically, we have to compute or to know the temperature and time. These two fields are the function that can give us the idea of what we are doing. Some of you maybe knows about that the metals have phases like austenite, ferrite, pearlite, bainite, martensite. They are different atomistic distributions in the crystallographic cells of the material. This is quite deeply metallurgy, but anyway, it is important to know that for us it's really important to understand how the laser deposits the energy and how much energy is absorbed by the material, because that energy will tell us how much temperature we will have. We will know the time because we program the machine, so we know the time. Knowing the temperature, we can extrapolate and we can predict the phases that we will have in our materials, and then we can predict the properties that we are going to have. This is extremely important. For example, Airbus is doing a lot of 3D printing for its planes. Imagine that they cannot predict which phases they will have in their titanium alloys. They will not be able to ensure the quality of the part once it will be in the plane. So this is totally a key point, okay? here you have an experimental work that we have done in Arcelor Mittal. The substrate, the base material, is a typical steel material for the construction, for beams in buildings, that we apply it a reinforcement in the sense of a wall. This is the cross-section of this wall. This is material A, material B, and this is the heat-affected zone, which is the most affected zone of the substrate by the laser. This system is a blown powder direct energy deposition, and here you have different numbers, 1, 2, 3, up to 8, that are positions of taking little samples to just measure the mechanical property of the harness. This is harness Bickerstein. Harness, as you know, is one of the properties of the materials that is related with the wear resistance, for example. So what we expected is, okay, we have two materials, A and B, but then we have a totally different harness profile. Why is that? This is because of temperature and time, because chemically the material A is totally the same, but physically it's not. For example, here you have the one for 500 Vickers, but then in the position of 3 you have 400 Vickers. The atomistic distribution between these 2 points is totally different. So the mechanical properties are also different. So this is the kind of things that we are trying to predict in Arcelor Mittal, and how lasers are using for post-processing, for control the metallurgy, how the wavelength can be adapted to tune or to tune in some zones of the parts, how, for example, multi-laser system deploys much more heat to our steels, and metallurgy is totally related with that, right? So if I have to say as a final conclusions, I see two fields. One is opportunities of lasers in additive manufacturing. The other one is the challenges that are present right now. In the opportunities, probably the biggest opportunity right now is to take advantage of multi-laser systems. Multi-laser systems opens a totally new door of fancy things like combining lasers, much more productivity, much more heat, obviously. But for example, in the States, there is a new company, a spin-off of the MIT, that is trying to put 100 lasers over a single machine. So if you can control all of those lasers, you can, for example, pre-process the material, print it, do a thermal treatment, all during the process. So the capability is incredible here. Another point is how these lasers could be combined. How can we, for example, put high-power energy lasers with big spots for the zones that are bulky and in which we want to do the process as fast as we need, and in other zones maybe use more detailed lasers with fine spot sizes in which they will give us a really good morphological resolution of the part, right? These little angles that we can have in these parts, these lasers are really suitable for that. So regarding the lasers, a lot of wavelengths, multi-laser systems, totally control of them. Playing with the focus is now a new opportunity, because some vendors let you to control the focus of the laser. The focus is really convenient for putting bigger spots and trying to print faster. And then obviously there are some challenges related with that, for example, in multi-laser systems, it's really challenging to control the robotics. In the sense, I will have, for example, 5 robots. With each robot will have different lasers. We need to be sure that the synchronization between this system is really good. The robot path is well done, that the lasers will not interact between them. For doing that, we are exploring, for example, artificial intelligence, specifically machine learning, to try to develop an algorithm which program automatically this kind of multi-robot system with multi-lasers. And then a multi-laser system also creates out a lot of problems in terms of temperature, smoke, that can interact with your mirrors, that can interact with your beams at different heights. So it's a problem for the gas, that you will need to put a lot of gas in your process to get rid of all of this smoke and all of these particles. And for the future, it's important that the laser technology, especially the high power laser technology, goes down in price, because right now additive manufacturing is dedicated for aerospace, dedicated, for example, to dental application, for bionic application, and for steels in some points, very added value applications, because at the end, the laser technology is quite costly. And for example, if we want to introduce additive manufacturing to automotive market, for example, we need to be sure that our process is quite cheap and our euros per gram deposit in our parts will be competitive with the standard in the industry. So with this, once more, I would like to thank you, all of you, to be here and to give me the opportunities. Thanks for your attention. And
oh my God, Juan Manuel, so much information. Muchísimas gracias. It's incredible how much. I mean, I'm collapsed. I'm saturated of how much input you gave us.
Yeah.
I would like to talk to you about DED. I would like to you about different materials. Unfortunately, I have a lot of questions in the chat as well, so I'm going to give them priority.
Sure.
The first question comes from a company that is really good at making active fiber, all the way from Canada, Coractive. Jean Noel Marang, he's wondering, what is the impact of laser beam shape on the process efficiency of 3D printing?
Yeah. Indeed, it's a really good question, that one. We have seen a lot of differences. For example, we have seen that typical top hat beam shaping has a lot of influence in how the metallurgy and how the grain structure is created. And we have seen that even just changing the beam shaping, we have seen difference in mechanical properties without the totally most same parameters of processing, but just playing with the beam shaping is possible to tune or to find the microstructure. And this is incredible, because in casting, in forging, in typical steel making applications, it's not possible to do it. But now with lasers, there's a new open world for doing that. So it's a really interesting topic, that one.
Next question from TU Kaiserslautern, Emerson Cándido de Oliveira. He's wondering, are there any steps taken in the processing to avoid porosities in the printed parts?
Yeah, hopefully there will be, but no. The point is you make to make sure that your printing parameters are well defined. You need to create design of experiments. You need to go first for cubes, little cubes, make density analysis, to try to extrapolate that to big parts. It's not so directly. You need to print the part. Maybe you need to do some tomography to detect little defects. But porosity and additive are enemies, obviously. But yes, it's hard to get rid of total porosity. We have achieved it with several materials, like 316L is a really good steel. We are doing like 99.9991% of porosity, it's really good, but depends also in the material indeed.
We go from Kaiserslautern to Jena. The next question is from Orafol Fresnel Optics. Fresnel Optics has the cooler type of optics I have seen in my life.
Yeah.
Jürgen Zussel, he's wondering, we did produce a lot of lens arrays for CPVs in 2012-2013, but this market did broke down at some point. Do you have some ideas on applications for Fresnel optics?
I do not indeed. As I said, I'm totally related with big industrial applications in Arcelor Mittal, totally steels mainly for PCBs. I know some people that are working on it. For example, KTH in Zurich is working on it, but I cannot answer that.
Don't worry, because I'm going to give you some homework. If you can find me a person at Arcelor Mittal that is interested in Fresnel optics, I would like to make an introduction. The final question is again from Coractive. Is the polarization state of the beam shape has an impact on the efficiency of the process? So does the polarization state of the beam shape has an impact on the efficiency of the process?
We didn't check that indeed. We didn't check that. It's something that we didn't change so far, but I can confirm you that this year it's something that we are going to look for. We have done, for example, beam shaping, modifying the offset, modifying, for example, the wavelength in changing the source of the laser, but not polarization.
If you want to tweak the polarization state, the fibers of Coractive are really a great tool, and here I think there is some room for cooperation. DED, wire DED. I had a presentation from Presitech at an event I organized last week exactly on that topic. And you will be amazed of some of the conclusions that we reached on that meeting. I'm going to share with you the slide from Presitech. I'm going to take the freedom for that.
Sure.
And in that slide, we compare a little bit the different 3D wire technologies that are being taken to the market. And I would like to ask you, when it comes to the cost, when it comes to the price, is that you consider a challenge, an opportunity? What is your vision on this?
It's an opportunity, obviously. It's an opportunity. If I hear you. Wire arc is the most cheapest one, but obviously laser technology is evolving. The technology based on low power lasers all stacked up to combine all the power in just one spot is really interesting way to save money, for example, no? And we have compared this new technology of low power diode lasers with WAM, and more or less is the same at the end. And for me, lasers has much more advantage than arcs, because arcs are very limited in the range of that you can play with. Lasers, you can have an open world about the beam shaping, about how the parameters is constant from 0 to up to 1 kilowatt. In arcs, it's not possible to do that. So if laser technology comes to the same price as WAM, laser is going to win every single match. The problem is that one is quite cheap right now.
Thank you very much, Juan Pedro. We took 9 minutes extra, but it was worth it having this discussion.
Sure.
And many people are gonna get in touch with you. If you wanna get in touch with any of the participants today, send me an email and the reason why you want to get in touch, and I will be more than happy of making that introduction. And with this, I would like to close this fantastic first session. I would like to give all of you some time to go to visit the booth or to go to the networking area, get to know each other better. We come back exactly at 3 p.m. with presentations from Valeo and Luxi about LiDAR. See you then. Have a nice interaction. Ladies and gentlemen, welcome back. After this very well-deserved break, now we talk about LiDAR. And in this session, we're going to hear from Luxi and from Valeo. And we're going to try to find some room for cooperation. The first company presenting in this session is a company very much loved in the Epic network, because they have used the Epic network to set up an impressive supply chain and always looking for cooperations. The company that we have here is a LiDAR company from Denmark. The name is Luxi, and Luxi is focused on LiDAR-based system solutions for many different applications. They actually use various LiDAR hardware, and the core product is software and system design. Even in airports, in airport ground support equipment, they have making a huge room for innovations and cooperations. Mirvais Yousefi, the CEO of Luxi, is here to find ways of the photonic supply chain make Luxi, a great startup looking for investment and partnerships, even greater. Mirvais, thank you so much for being with us today. The floor and the attention of almost 400 people watching you is here.
Thank you very much, Jose. Let me start by thanking for the honor to present in this very, very, it's a very cool society for us, especially for us at Luxi. We are one of the core members, I would say, one of the early members, but we are also, I like very much hanging out with the people.
Mirvais, couple of pointers. The first one, could you click on the icon of your, perfect, and then can you go full screen in your slides?
I will do that, thank you.
We want to see you like as bright as you are.
Thank you. So let me do the following. Let me jump into everything, and I will open the floor for a lot of questions, hopefully, and also a lot of questions on how and what. So as you can see, the title is very long, and I was asked by one of my colleagues earlier that, hey, you should let these slides sit for about a minute, because otherwise nobody will read the title. So let me simplify it for you. We build LiDAR solution for airports. Yeah, and our target is to simplify and to make it safer. Yeah, let me jump in to my slides. So I have planned to tell you about who we are, then why LiDARs. I will try to show you a bit of a trade-off table. Most of you are familiar with this, so this is nothing special or crazy, but hopefully it will give you some information. Then I will show you something new in this community, and that's airport ground support equipment and their ecosystem. and then specify what we do. I have a GIF instead of a video. I can give you a link to a video later if you want, but I hope the GIF works. Let me start by us. So we are a startup located in Copenhagen. It is very snowy outside today with a bit of rain, so I cannot say sunny Copenhagen, unfortunately. We're part of the startup incubator at TTU Science Park, 7 people at the moment. And our focus is LiDAR-based solution. As you can see to the right-hand side, we do everything with LiDARs, from range finding to navigation, etc. And our software is then handling all this through algorithms and helping the user make a decision. And so we build our systems together with the users, and we get the specification from them. Around that, we use our software to build the system. All right. A few words about us to say is we are 2 senior people, and we have a team of very enthusiastic technology enthusiasts, as they call it, technophiles, as they call it. And they are all focused on robotics and optoelectronics and essentially the hardware and the software side. The reason we say robotics is you will see later in our application, because LiDAR, of course, is one of the key technologies for robotics, navigation, and autonomy because of directly producing point clouds. So it is one level better in that way than 3D cameras, for example, because here you get the raw data directly and you can do a lot of analysis. All right, let me show you a table and explain to you why we use LiDAR, even though it's not necessary in this STEAM community. I will still try to convince you. So essentially, by the way, it says very clearly here that the cost is low. And a lot of you will be thinking, hey, but that's not true, because I mean, Velodyne 64, for example, is a few 100,000, or can be a few 100,000 Danish crowns, I mean. Well, that's not true, because nowadays there's a lot of LiDAR hardware out there specifically aimed for an application field, which can actually compete very well with other technologies, such as 3D cameras or radar and so forth. Yeah. On the resolution, of course, it is very high res. The ones we are using, at least, you will see later. Range, yeah, is unbeatable when it comes to that, because you can get a very fine resolution at 100 meter, 135, 200 meter. I mean, that's why they are the darling of the automotive industry. Accuracy, of course, they are quite good. And the most importantly, light insensitivity and weather insensitivity. I mean, of course, the weather insensitivity is not true. You have to set your LiDAR to emit more power, but that is a software level issue. It's really can be done live. And then the light insensitivity, of course, is much better than 3D camera. You will notice the 3D camera actually follows very closely to LiDAR. And in our application, actually, we do a sensor fusion, and we merge LiDAR and 3D camera data together to get both a long range, high accuracy, and a very short distance, very high accuracy. I will show later. All right, I hope you're not convinced now. We should get LiDAR for your application, and Luxi is the company to help you. Let me start by telling you what is the ground support ecosystem. So the ground, when an airplane lands, it's immediately surrounded by about 10 vehicles on average. And these 10 vehicles then prepare the air within half an hour to go up in the air again. And that is important because airplanes are very, very expensive piece of kit, and you need it to be in the resting position as little as possible in order to get return on investment. Most of these equipment currently are fully manual today. Yeah, and this has its plus sides in the sense that the manpower is cheap. However, it has its negative sides because it can lead to accidents. Now, especially with the carbon fiber airplanes, unlike the aluminum ones, the carbon fiber airplanes, when you hit it, they just bounce back. So in the aluminum body, you can actually see when it's been hit and do something about it and actually make sure that nothing happens in the air. While with a carbon body, the accident can be hidden. And so there is new rules from IATA, which tells that the equipment may not touch the airplane. Now, here comes LiDAR into play, because we can now equip these equipment with LiDARs and make an advanced driver assistance system where our equipment help the driver to navigate the equipment, the various type of equipment, up to 2 centimeters close to the airplane. That is the limit, yeah? We started by focusing on one of the ones that is causing the most accidents. It's actually the belt loaders. These things are used for loading and unloading aeroplane luggage. You probably sometimes when you arrive or you usually don't pay much attention to them, but they're actually very important on the airport. I will later show some example maybe. Here you see one from Mulag, for example, and we have equipped these with LiDARs and stereo cameras and now can navigate up to 2 centimeters close to an airplane repeatedly. So it's a fully stable system. We are deploying it now to the airport for testing. Why would you do that? And I personally am afraid of flying. So when I see pictures like this, I get super scared. Because this is actually true. This is real pictures from real life. These equipment, it doesn't happen often, but when they do hit the airplane, we are speaking of up to, on average, 50,000 euros per damage, but up to 1 million. There is the additional part of the damage, and that is the delay caused by these airplanes. And the delay is not onto your plane. The delay, because the airports are so tightly scheduled, the delay propagates down the chain. Yeah. So to tell you the business case, it's a very good business case. They are there, the accidents are there, and it needs to be removed. And especially insurance companies and airplane companies are very well aware of this. Yeah. Our job is to minimize this. All right, what's our system? Here's our system. It's already mounted, as you can see. It's 2 LiDARs. Because we are using a LiDAR, in this case, sorry, Jose, not from the supply chain. I'm sorry about that. It is actually an off-the-shelf LiDAR from Livox, a Chinese manufacturer. Our software is agnostic to LiDAR. So essentially, we use drivers to collect the data and then do the processing. So we are open and looking to new cooperations, actually, also. So we use 2 LiDARs, one for checking the pose of the airplane, as it's called, and one for the equipment. We use stereo camera, which takes over after 2 meters. So from 2 meters to, let's say, 10 centimeters inside the plane, stereo camera is in the lead because it can give you a 5 millimeter resolution, while the LiDAR has a plus minus 20 millimeter. And then, of course, some computers, some PLCs for controlling the equipment, so we control the brakes. And below, you see a sketch of how the system works. Essentially, the so-called conveyor has a roller track, and it tries to dock inside the cargo hold of the plane. I will show you a LiDAR image of this part of where it's docking in the next slide. So what's our software? It's an we build our software on top of open source platform, and it's Linux based, of course. And we provide a bunch of algorithms to our customers, but also we can provide a full solution. In this specific case, in our first product, we're building the full solution. So it's a binary together with some hardware and some PLCs, and the whole system works together. Of course, we're open to working with just providing 1 or 2 of the algorithms also in form of API. Again, let's see what the customer wants. So here's a bit of an idea of what we do. We are actually computer vision, if you want to look at it that way. So we are working on perception. So the perception of the hardware. And this is done through various algorithms. Here you see, for example, edge detection, LiDAR calibration. The 2 LiDAR must be calibrated together. In the other bottom side, you see a stereo camera where it's trying to find the cargo hold and the points, etc. And this helps us, all of this algorithm together with good project management, as you have seen here in the picture, and good planning, allows us to make equipment or make a system that has 2 centimeter accuracy at long range, and at short range can be down to ½ centimeter because of the stereo camera. Be aware that in the short range, the LiDAR is still on, so it's a backup. In case the stereo camera fails, we can do the backup. In the GIF, you can see several of the data sets. So first of all, the yellow is our Livox point cloud. It is a very special type of LiDAR that does the scanning of the beam by rotation of 2 gratings. If you rotate 2 gratings with a monochrome light, you will get a pattern, a non-repetitive H-like pattern, and that's what it does. And you can see that here on the point. And then our algorithm first identifies the fuselage, which is the white, then identifies the entry point, which is the red, and then identifies the center point of the entry. And then here the equipment is not moving, it's standing still. For this specific GIF, I just took this. This is real life picture, by the way. This is really how it looks in real life. Yeah, I mean in the computer. So what's in finding the hole? Why would you want to find a hole? Well, finding a hole is a very important thing from robotics perspective, and robotics automation. As I have told you now, it's important in airports, ground support equipment, etc. It's also important in harbors, where of going onto the ferry or off to the ferry, or also automated equipment going on and off ships. It's very important in cranes, especially in harbors like Rotterdam or Hamburg, where you need to find a hole. Again, our software is perfectly suited for this. Our whole system, together with our LiDAR, is perfectly suited for this. And we can either help the driver to navigate or do full autonomy. So we can, together with partner, take over the control and do this autonomously. Other places where we see our technology coming to play would be agriculture. Of course, this is the reason we chose this environment is very simple. This is a so-called sparse environment. Here, there are little or no humans. Yeah. Why would a small company like us work in this field? Because if you don't have the humans on the ground, say on the airport or on the apron actually, and or in the agriculture field and so forth, then the problem, as you can see in this GIF, simplifies very much. There is actually people passing in front here. We filter them out in our problem, because if there are no people, then the problem actually becomes a pure technology problem, and we can solve that very cleanly. If there are people, then yeah, then you have the automotive companies where you need teams of hundreds of developers to try to resolve the issues and do AI and so forth. Another key field for us would be robotics. We are expanding in there slowly. At the moment, we are going to deploy our first system on the runway in the next few weeks. And that, as you know, is an automation system. So the first system took a lot of blood, sweat, and tears. Now the next system is essentially a copy. I am within time. It's nice because it brings me to my summary. So we are a first mover in LiDAR application beyond automotive. Yeah? So we are specifically focusing on any field minus automotive. So the Venn diagram would be all applications that are us and automotive. We build system-level solutions using LiDAR, stereo cameras, and perception, computer perception. That means essentially the customer gives us the challenge and tells us, hey, I need to park this thing here. I need to lift this thing from here. We then build a system using LiDARs and our software for them, together with them mostly, because, I mean, we only know the perception part. They usually do a lot of the motion part. We are ready for the airport aprons, and keep in mind, it's not for runways, it's for the aprons. So it's when the plane has landed and there are no people around. So this is really sparse environment. And one of the key tasks I want to achieve here is to raise your attention both for as our partners, but also as investors. So we are searching right now for both investors and both hardware and software partners or application partners. With this, I thank you very much. And I think my contact details are available or ask Epic. We are a proud Epic member. Please ask Epic if you want to contact us. Thank you very much.
Thank you very much, Mirvais, and do please ask Epic if you want to get in touch with any of the participants today. Mirvais, I have a few questions for you. The first one is coming from the company Coractive. Julien Tremblay has something in his mind. He's saying, what is the laser wavelength of most of the LiDARs you use?
We are currently we are using 905 nanometer, but we are totally agnostic because remember, we're on the system level. So if you can build the hardware for us and give us the driver, any wavelength will work, all the way from 1.5 micron. For some reason, if you build a UV LiDAR, fair enough, we will run with that also. It's up to you as a manufacturer.
We have organized a lot of online meetings on LiDAR technologies in the last months. 940 and 905 seem to be more or less the wavelengths of choice. When it comes to laser eye safety, is there any challenge, any regulations, any way to work on this?
Okay, that's a very good question. It depends very much on the type of LiDAR. So we, again, make decisions together with our customer, and this depends on the application. How sparse is your sparse environment? Now, if you're in the agriculture space and there's nobody in the field except some cow, you may go to higher power. Let me be honest, and this is maybe not a nice joke. But if you have a scanning LiDAR or something like this, then actually this is not a very big problem if your beam is very well collimated. So I would say the laser eye safety at the moment for 904 is not a problem. depending on what type of LiDAR you're using. And I think the next speaker from Valeo can tell you much more than what I can about this.
You talk a lot about the robotics industry, which is an industry that we are exploring quite well. Actually, maybe I have a nice slide to share with you. I organized a meeting with Epson in one of our events, and I asked them the very specific question: when it comes to sensors for your robots, what kind of technologies are you looking for? And he shared with me this slide that I'm going to show you. And he said it is all about the 3 items: control, accuracy, and speed. And then he told us everything that we need to know, it has to be about the synchronization of multiple robots. When you are put into that challenge, you actually have to not only know what is around a LiDAR, around a robot, but know what is really around every robot, make a system with that. What is the first thing that comes to your mind?
Well, this is a very interesting slide, because it's exactly the problem we are facing. It's about sensor fusion. So I think what you said is speed and accuracy is the key here. The reason we choose LiDAR for the very long distance, where actually the vehicle is moving rather fast, is because you get pure raw point cloud data. For us to process raw point cloud data is much faster than having to use a 3D camera and then have to do disparity map, and from the disparity map collect the points. So I think the sensor fusion approach requires multiple, let's say you need for each flavor, for each flavor you need to make a different spice, if I may say so. I'm a cook myself, I like cooking, so for each type of food you have a different spice.
Another question, do you see an opportunity to implement your LiDAR system on the plane itself to secure taxiing?
Yes and no. So the field is moving in a different direction. The field is moving in the direction to save fuel. What you want to do is, as soon as the plane has landed, you want to turn it off. Yeah. So what you are looking for is tow trucks. Yes, we're looking into deploying our systems on the tow trucks, which will pick up the plane at the landing spot and taxi it all the way autonomously into the gate. So you don't want the plane to move itself. This is a very inefficient. A plane is very inefficient on the ground. It's super efficient in the air. On the ground, wheeled vehicles are the key. Yeah. So yes, but in a different flavor again.
You are bringing LiDAR to many different technologies, and you have your own proprietary software for that. And the idea here is you are really a huge business opportunity. I hope people see that and they invest, because this really is obvious for me, a clear investment. Actually, I just got a very interesting question in the chat. I believe that 1550 nanometer in the airport will be a must because there are always people around in the airport. Is it true? Do you really see that 1550 nanometer the right wavelength for LiDAR in the airport?
Again, it depends on, it's a spice versus food. So it depends on which range you're looking for and so forth. I will be aware, so the buses are the fastest vehicles on the airport. Probably there you would need that because you need fast data processing, very long range. For something like what we are doing, 50 meters is the longest range and so forth. So you don't need so much power. And again, there are not so many people at the airport. Actually, there's virtually no people on the airport. Airport with people is not a good airport.
Airport with people is not a good airport. And the LiDAR technology of Lux C. Remember, these people are actually using hardware to implement their systems, and their proprietary know-how is in the system design and the software. Thank you very much, Mirvais. That was really spectacular. And stay with us, because now we want to go to Valeo. And with Valeo, we're going to explore how we're going to bring LiDAR technologies. Before we explore every market but automotive, now let's go automotive. Thank you very much for being with us in this fantastic afternoon talking about LiDAR. I would like to welcome to our fantastic meeting today one of the tier 1 supplier that we have most in our network. And with this, we have Joachim Mates, the CTO of Comfort and Driving Assistance. Thank you very much for being with us. Joachim, the floor and the attention of about 400 people is yours.
And that's a pleasure and an honor as well. So I'm going to talk about our scanning LiDAR in a moment. But before that, as unfortunately not so many people know Valeo, I've brought a short video that gives you an idea of what we are doing. And I'll see you in a minute.
Someday, you'll be able to dream, eyes wide open, connect to cities. Choose the air you breathe. Be here, there, and everywhere. See beyond objects. Harness time. Feel the emotions. And transform energy. Be together even when far apart. In awe with those beside you. And make light your ally.
As you've seen, Valeo is committed to provide people all over the world with sustainable individual mobility. We design systems to reduce CO2 emissions in all vehicle segments, and 1 in 3 new cars all over the world comes with a Valeo system to reduce fuel consumption and CO2 emissions. Just recently, we announced to achieve carbon neutrality by 2050. And that across the entire supply chain worldwide. We have committed to achieve 45% of this objective already in 2030. And mobility is more than cars. 2 months ago, we launched a super interesting e-bike transmission, which is automated and electric, offering a unique combination of performance, efficiency, and ease of use. In addition to being a leader in vehicle electrification, we are also a leader in ADAS, making parking and driving not only more pleasant, but above all, safer for everyone. We bring 30 years of volume production experience. Our worldwide manufacturing facilities turn out currently more than 30 million ADAS systems per year. And 30% of cars sold worldwide are fitted with Valeo technology to protect you and the people around you. It all started 30 years ago with our ultrasonic parking assistance. Near-field sensors that indicate what space is available before or behind your car. And what looks like a simple function was actually revolutionary at the time. And while the basic function is so intuitive and easy to use, the technology behind is actually pretty challenging. As the car design evolved to become more aerodynamic or crash-friendly, visibility degraded and demand for the system soared. Today, it pretty much comes as a standard with new cars. And over the years, we have added new technologies to complement this ultrasonic technology to offer the broadest portfolio in the automotive industry. Through collaborations, partnerships, and acquisitions, and as well, thanks to our incredible engineers all over the world, we've never stopped innovating. A very important milestone was the introduction of our lane departure warning camera in 2004. Only 2 years later, we launched the first multi-beam radar for automotive use to provide blind spot detection. And 4 years ago, we completed our portfolio when we launched our Scala 3D laser scanner. I will come back to that later on. Every sensor brings its own strengths and weaknesses, and for many state-of-the-art functions these days, it's the combination that does the trick. Different kinds of sensors are needed for the very near range compared to the very long range, where you need to detect small objects far down the road. While ranging sensors like our ultrasonics and radar offer good performance at low cost, cameras have been the ones gaining importance in the last decade. One factor is that it's nice for the end user to see what's going on, but as well, the software allows good perception to understand and interpret the scene all around the vehicle. Therefore, computing power and software play a very important role, and more we can see that these functions are centralized bringing together the information from multiple sensors in a safety cocoon around the car. As a consequence, system integration and system validation on all levels cannot be underestimated. In some projects, this amounts to more than half of the actual development effort, even when using very efficient platforms. Speaking about system engineering, we offer car manufacturers the option to just purchase individual components like the sensors, but of course, it's best if we can provide the entire system, including all of the elements up to the vehicle control. So one example is on the slide here, where in 2016, we launched the first remote parking assist function, which was able to park the car with you being outside and just watching. We provided all of the hardware as well as the software components, perfectly optimized and safe to use. Now, in 2019, we've launched something very different and kind of fun as well, because it's the first camera system that allows you to look right through your trailer. We are using several cameras, calibration, as well as computer vision algorithms to create a video feed on your central display, which allows you to look straight through your trailer. Therefore, trailering has never been that safe and relaxed before. And most recently, we helped to make active safety features like automatic emergency braking, lane keeping, adaptive cruise control, and traffic jam assist affordable for the lower market segment or emerging markets with a vision-only level 2 system. We are using a smart camera, which offers the functions that normally require a radar in addition. Taking out the radar is not only taking cost from the system, but as well it eliminates wiring complexity, brackets, and therefore weight, which as well helps to improve the CO2 emissions. Another highlight in the recent past is the Scala 3D laser scanner that I mentioned before. When we launched it in 2017, it was the first such device that complied with fierce automotive requirement catalog, and today it still is. It brings unique perception characteristics which allow for a truly redundant perception system, which is required for level 3 automation. Level 3 meaning that as a driver, you're actually out of the loop. You fully delegate the responsibility to the vehicle. We are involved in 2 such projects, which are scheduled to go in production later this year. And in both cases, the Scala is one of the enablers. It offers a long detection range with extreme accuracy combined with a very wide field of view and high resolution. All of that 25 times a second. You cannot find that combination anywhere else in the industry. So far, already more than 125,000 Scalas are on the road in vehicles all over the world. And we are readying the launch of the second generation later this year. That evolution offers 4 times the vertical field of view. We increase the precision for long-range perception, and as well, the computing software and perception has evolved along with that. While this is the right product for long-range and high accuracy, our near-field LiDAR offers a 3D safety belt close to the vehicle, which is needed for driverless applications like robotaxis and droids. This flash sensor can cover the area around the car as well in the full height, so that overhangs or low objects in urban environments can safely be detected. And again, we don't stop here. We make this highly robust technology available to new mobility players or smart infrastructure. Most of our sensors are already available in mobility kits that make these automotive-grade products available to everyone, whether you just need one device or thousands. We will offer you the matching solution. Talking about automotive-grade quality, I mentioned earlier that the Scala is still the only automotive-grade 3D LiDAR on the market, despite the fact that there are so many LiDAR companies out there. So what does automotive-grade really stand for, and why is it apparently so hard to achieve? First of all, automotive-grade means you have to check all the boxes in this table. Being good or even excellent in a few cannot compensate if you fail in just one of the others. People often think it's about the product withstanding a certain vibration, shock, or just operating from -40 to 85 degrees Celsius, which is of course true, but automotive grade is just that much more. Can your product not only survive the vibration or temperature, but will it comply with the functional requirements? Will it deliver the necessary performance KPIs, performance indicators, over the full temperature range and over the complete lifetime as well? Just having the equipment in your basement is not sufficient. Another aspect is cost. In automotive, it's not pure performance that counts, but the good balance between performance and cost. So automotive grade is more than just making your product a little more robust or achieving a certain performance level. It's a mindset which requires completely different approaches in the development compared to other industries. One important element in that development is the software. So while even a brilliant software cannot generate good data from a bad sensor, garbage in, garbage out, as we say, the software defines just how much you really get out of a good sensor. It's not only about the object detection algorithms. That's, of course, an essential part in the system, but you also need to squeeze the maximum out of the sensor as a whole, which requires a good understanding of the physics. As a result, hardware and software engineers need to work closely together to optimize the system output. While there are many other software blocks to master, the most visible aspects are maybe the ones shown on this slide. So first, we have to make the sensor raw signal output useful for the following software modules. Hardware-specific inaccuracies or anomalies need to be corrected right at the beginning. Noise needs to be identified and eliminated. Signal jitter to be removed. After that, the software has to decide which data points belong to the same object. Ghost echoes need to be filtered or interferences suppressed. And of course, with all the filtering and elimination, you have to make sure that the very signal you're looking for in the noise is still there and you don't accidentally remove it. So this actual determination, tracking, and classification of objects uses increasingly artificial intelligence. Though for some of the applications, deterministic behavior is very important. So once again, it's not either or, but the combination of both, which actually gives you the best deal. To achieve an overall robust and reliable perception, we also need redundancy. I was talking about the ranging versus the vision sensors, for example, and therefore having an object confirmed by two or different sources brings you certainty, robustness, and reliability. It also brings you new challenges though, because what if two sensors don't agree? What if there are results from two different distances, but it could be either the same object and some inaccuracy, or it could be two different objects? Therefore, we also have to be very clear about the sensor fusion and the strengths and weaknesses of the individual technologies. And also as a consequence, it's dangerous to extrapolate the effort it took you to 80% to estimate what it takes you to 100%. It's the old Pareto rule. And the closer you get to the end of the development, the more effort you have to spend to close the remaining gap. This is exemplified in the validation. And you can see some examples here, because as mentioned, it can amount to about half of the development effort at the end of the road. And to get there, in some cases, you actually have to develop the tool chain itself to generate the ground truth. While this keeps an entire department busy, as well, you have to collect petabytes of data all over the world, share it across different sites in your engineering team, and you have to have a data management system to complement that. So again, automotive grade is a mindset as well as a commitment to go all the way, right up to the end and to deliver. And deliver is what we do. We deliver dozens of model launches every single year. Our production facilities all over the world are turning out hundreds of thousands of sensors every single day at a constant quality and as well at a precision which often is measured in micrometers. We are delivering the right sensing technology for every use case. We deliver the matching software systems to make the best out of those sensors. And we design the system architecture so that those systems are scalable and offer the right performance at the right price for the market segment. Because after all, what it's about is making mobility more pleasant and especially more safe for everyone. That's the goal we are fighting for. And now I'm happy to take your questions.
Thank you very much for a great presentation. I was told that the video quality was low, but the sound was very clear. And we heard very clear that delivery is what you do. So let's help you deliver even better. I have a lot of questions for you. The first one is obviously the one that you are very prepared for. The first one is about wavelength. What is the wavelength for LiDAR? Are we talking 9XX, 905, 940, or 1550 nanometers?
Well, I liked the analogy of cooking and spices. So really depends on what you want to do. But clearly what we have here is all 905. We're looking at 1550, we're benchmarking it. On the other hand, besides the obvious advantages, we see some clear disadvantages, especially for high volume automotive applications. It's still very expensive. So we will try to get as much as possible out of 905, and we're confident there is more to come.
The second question coming from Coreactive. Are all the legal aspects surrounding self-driving cars, assurance, responsibility in case of accident, etc., going to be the main limitation for the acceptation and deployment of LiDAR technology in the future?
That's a tricky question because
I know.
There are very different definitions of self-driving cars. What I was referring to was level 3 for privately operated vehicles, and there the legislation, for example, in Germany, where I happen to live, has just been passed. So from that point of view, no obstruction there, and for sure, LiDAR is part of the recipe for that. If what you want to do is robotaxis or completely driverless vehicles, obviously it's a different story, but it's very much a regional legislation that will probably see some countries like China going very, very quickly. So in this case, we're a global company. We're ready to play everywhere. And once again, I'm sure there will be no level 4 or higher vehicle without a LiDAR.
I also have slides because I have given a lot of presentations about LiDAR in the future, and I want to show you one of my slides to see what kind of things we can do together. So this is my slide. I don't know if you can see it. It's a slide from the market report that EPIC members have access to that we published last year together with Joel Development. And in that slide, we talk about a huge market pool for SPADs. SPADs integrated with different technologies for the LiDAR. Is Valeo looking at SPAD arrays for different applications?
Now that is something that leads us into areas where we are not communicating, actually, okay? So I have to evade the question a bit. Yes, for sure, we're looking at it. And once again, it depends on what range you want to address, whether that actually is a solution that we will see in volume application.
Very good. My second question, which, sometimes you cannot answer, but not being able to answer is enough information for me to start cooperations. The second part is about moving parts. We are in the world in which FNCW is appearing. We're in the world in which new silicon photomultipliers are appearing. We're in the world in which photonic integrated circuits and companies like Scantinel are growing. I would like to ask you, moving parts or no moving parts?
Both. Moving parts, got them here. Okay, that's the Scala with a rotating mirror, which gives you a good aperture and therefore long range. So I'm convinced that was a good choice. For the short range, flash LiDAR, no moving parts. So yes, both.
There's a lot of room for cooperation, and I'm a strong believer that all the moving parts are going to go away in 10 years. That's what I believe. But 10 years is a long time, and there is a lot of market to be surrounding here. What I want to see, what I want to do with Valeo is to have an entry point for all the innovation of the photonics community that is developing new SPADs, new lasers integrated in silicon photonics, new indium phosphide solutions. I want them to have a way of entering the automotive market, and we have the amazing tier 1 supplier of Valeo interacting with EPIC. I cannot be more thankful for that. Thank you very much.
My pleasure.
And now we are going to go for a short break. And before we do that, I would like to remind you that the next session is EPIC. Because in the next session, we have L'Oreal looking for optics cooperations. And we also have Quartus, which is one of the main suppliers of NASA for CubeSats, looking for optics and freeform optics solutions. This is going to be an epic session on optics and freeform optics. It's going to start exactly at 4 p.m. So you have 18 minutes to get to know each other better. See you then. Ladies and gentlemen, welcome Welcome back. I hope you had some time to network and to get to know more of your potential partners, suppliers, and customers in the fantastic networking experience. But today, right now, is a super important day for me. Super important day for me. Not every day in my life I get to welcome L'Oreal to an optics and freeform optics session. And this is fantastic because they're looking for cooperations, and it's L'Oreal. This is incredible. I'm so happy with this. I would like to welcome Benjamin Askenazi and Veronica Marek, both of them based in Paris, working at L'Oreal, and both of them optics experts. I don't know if you notice how excited I am about this. Thank you so much for making me such a happy boy today. The floor and the attention of everyone, I cannot say this enough, goes to L'Oreal.
Thanks a lot for the very energetic introduction. So we are very happy to be here, and we'll give you today a very strong presentation about what we try to do in optics and photonics at L'Oreal with two voices, mine and Veronica.
Hi, thank you very much. Great to be here. And so, Benjamin, I let you start and I will follow up.
Yes, so I'll share my screen now. Just let me show my face again, and we should be ready to go. Okay, so what we want to talk to you about today is optics in new beauty services that we are thinking about. And when you think about cosmetics and L'Oreal, you
Benjamin,
think...
we need to go to presentation mode.
Well, I am in presentation mode.
But then you're sharing the wrong screen with us. You're sharing the screen that contains spoilers. So I hope nobody's watching that.
Whoa, that's really too bad.
Start from the beginning, because I saw some human tissue diagram, and I know that's a very important part of the presentation. No spoilers allowed.
I'll try again, and you tell me if it works.
Let's try again.
Is this better? It should be in presentation mode.
I think we are ready to rock, yes.
Yes, great. So when you think about L'Oreal, you generally think about cosmetic products, and so you think about this. We also think about our great team on point of sales and our sales force and beauty advisors that we work every day with. But today we're going to talk about something that is slightly different, which is all the devices that can be linked to beauty and beauty routines, and especially the one that concerns optics, because as we will show you today, L'Oreal is also this. So very few words about the company. So it's a huge group with several brands. Most of the brands are international. Some are very local. We work on all the distribution channel and on all cosmetic segments. So now, why do we have photonics in L'Oreal, and how does it appear in the product chain? So we have first photonics when we go into advanced research, because we are in the need to understand how products and cells are combining, and what's the effect of our actives on a cellular level. So we have a very strong need of imaging, for example, and high-end diagnosis. We also have a need of very accurate diagnosis when we want to evaluate the performance of our products. And so we have a whole team that's called the product performance evaluation, which has a very strong knowledge about optics. But yet, that's not what we're going to discuss today. Today, we're going to talk about a new métier at L'Oreal, which is called augmented beauty, and where we try to deliver new services through technology. And the team we work on, we have a department that works on different kinds of energy, on mechanics, on data science and AI, and of course on applied and digital optics. And Veronica and I are from this team, and we're going to tell you about the projects that we run there. So what we do in the team, generally, it's separated in 3 different steps. We first need to measure accurately the hair, the skin, or the products, and this goes into what we call diagnostics. Then we have to model the data that we just collected. So we have a strong activity on algorithms, being purely AI and just data-driven, or based on mathematical model and physics. And then we need to make it real. So we put this into the rendering part, and we have 2 ways basically of making it real. One is to making it digitally real and have a simulation, an accurate simulation of how it looks, like VTO, a virtual try-on, for example. Or you can actually make it real with a machine that is going to make the product for you. And it's a personalization in the cosmetic industry is going very strong. For example, you can see here Le Teint Particulier, so foundation colorite for hair and Perso for lipstick at home, being launched over the years by L'Oréal. And the common ground of all those is color science and color modeling. So why is this so important for cosmetics products? And we'll take the example of foundation to drive you to this. So it's very important because personalization is the way to really understand a market that is complex, and skin is typically this because skin colors are very, very different. And there is no way that, I mean, everybody has a specificity that they want to take into account. And what we have trying to do since a few years now in L'Oréal is going from a very luxury experience in point of sales, like Le Teint Particulier, where we have a personalized foundation on the counter, to something that is more scalable and more massified for so that everybody has the access to that. Yeah, well, apparently I need to put my camera on. Sorry about that. It should have been, oops. Here we go. So yes, shade finder, as we said, so it's a recommendation around in ranges that exist, and then we made a shade finder online with something that's called AI Foundation Adapter, and that was launched last year. So that these kind of services are now available to a larger and larger audience. And to do that, you need to know very well two things. First, the media, the skin. So skin color is mostly two-dimensional. And you need to know very well your products to be able to understand physically how they will behave on skin or on substrate that looks close enough to skin. So skin knowledge and product knowledge are very important. And if you want to be able to go from point of sale to home, there are a few things to do. And I will give the example of shade finder to explain how. So for example, when we have a consumer on point of sale, we do a measurement with a handheld device, which is local, and will give three different measurements of three parts of the face. But that is not what defines the color of the face. It's a bit more complex than this. So we had to build an algorithm which takes those three inputs and is able to reproduce the recommendation that a human being would have given to a person. And so with this this algorithm called Shade Finder, we're able from this measurement to recommend three products. But now what we want to do is bring this home, and it's very difficult because we need to have the same level of accuracy that we get from a colorimeter with a smartphone, because there is not a lot of ways to give devices or calibration cards or any physical device to our consumer. We have to rely on digital technologies. And so we build this algorithm which enables to the consumer to do a 360 selfie video, and we have an AI algorithm that transforms this video into the measurement that a device would have done on the skin color. And so the fact that we have the knowledge of the skin, the knowledge of the products, and the internal knowledge about the algorithm makes this whole value chain possible. Moving on to another topic on hair. So we are also working on hair as hair scalp diagnostic. So mostly on this topic, we're working on with brands on devices that exist. For example, Aramovis is doing a huge, have a lot of product on those area. But we are also looking about more physical parameters. For example, when it's linked to colors. And so basically hair color, it's very difficult to define properly because hair is a complex media. And when you do a BRDF or a BTDF of a hair swatch, you get quite a complex phenomena. But those phenomena that you see in the BRDF corresponds to the colors that you see on a hair picture. So it makes actual physical sense, and it's very easy to understand why it's important. You have the diffuse color, you have the specularity, the reflection, the white reflection, and you have this first colored reflect, which is very specific of the hair. And we can easily understand how why it's that way when you do basic modeling of the hair fiber. And if you do that and you take into account the colorant eumelanin and phenylalanine that can be into the hair, you are able to simulate the rendering of a given hair color. Of course, to do that, you need to have a good understanding of the physical parameters, and you need to have a physical characterization of the hair swatches in the lab. So we have several devices that we like. This one is nice because it's multi-angle, and you see the complex behavior of hair color. So you need angle resolution if you want to be accurate when you take when you want to model that. And virtual try-on of hair is a big topic at L'Oréal. We have acquired a company called Modiface, which was the champion of virtual rendering for hair at the time we bought it. So this is done with AI technology, but AI and augmented reality is not the only way to do some virtual try-on. We can also think about 3D rendering and avatarization instead of augmented reality on a video stream. And we had a project using an open source code with NVIDIA that we worked on a little bit. And now we are able to generate some very physically realistic, based on light transport equations, rendering in few seconds. So not completely real time, but close. Okay, so that closed the part on hair, and now I will lead the presentation to Veronica for the skin. So Veronica, the floor is yours.
Thank you. Okay, now I hope you can see it. Please let me know if it is the case. Can you see my screen?
Yes.
Gorilla Glass clear.
Okay, great. So, as you can imagine, skin is a very complicated stuff. So for the customer, in order to know what kind of products she has to use, she first has to understand what problems her particular skin has. And in order to address this issue, we are making a local skin diagnostics, as you may see on these images. So this device, here we have a small camera that through different lighting modes takes pictures of the skin that we further analyze in order to be able to evaluate skin characteristics like wrinkles or, for example, redness. There's a good approach. That the better approach would be the full face one, the holistic one. And so this device, this photo booth, takes the pictures of the face from various angles and through 3 different lighting modes. And here you may see the results of this the resultant pictures that we further analyze either by classical computer vision or by artificial intelligence in order to evaluate quantitatively. So here you may see the scores, different skin characteristics, like here again, wrinkles, skin texture, maybe pores that are clogged by the bacteria, or even facial sagging. If we want to go deeper, and we do want to go deeper, we have to make an appeal to life scientists. And indeed, biological evaluation may help us to look into details what's going on that's really either human-related characteristics like this, either genes or proteomics or even metabolomics, or microbiota, skin microbiota-related characteristics. That's something that can be done at home by the kit that the customer will use herself, or in the boutique, and that's something that was realized with this device that you can see here several years ago. So that was a kind of rapid ELISA test to detect proteins that were important for skin aging. But there is another possibility to look deeper into the skin. Skin contains a lot of various things, but in addition to be just biologically interesting, they also contain chromophores. And so then we can use hyperspectral imaging to target these chromophores. For example, to detect the classically considered things like water content of the skin related to skin hydration, melanin content related to discolorations, hemoglobin related to redness, or many other things. So we're working on skin inflammation, like you might see here, the origin of dark circles, color homogeneity, etc., etc. Another thing we're working on is 3-dimensional imaging, because it allows us to be more precise in terms of geometry, so in terms of wrinkles and skin texture, to get rid of several biases caused by shadows due to inhomogeneous lighting. It also provides us with a nice wow effect for the customer. And the best case scenario, of course, would be to be multispectral and 3-dimensional simultaneously. We're also working on the devices and services that are for home use, like smartphone applications, like these two ones, that target either specific skin problems like acne, or provide you with a genuine analysis of your face and then advises you a tailored set of products to use, or small sensors, or even patches that contain UV-sensitive dyes that are so sensitive to sunlight and may tell you when you are overexposed, send you some warnings, and also recommend you as well as sunscreen to use. And to finish, some words about other miscellaneous project we had in the department. The Light Me Up, here again, is about virtual try-on that Benjamin has already mentioned. So this is a mini projector that projects virtual makeup on your lips and on your eyes. That works quite well on the dummy heads, but also on real people when they turn their head or close their eyes or just move. Another thing is Perso device that Benjamin has also already mentioned, but it's another implementation related to skincare products. So here again, it detects skin problems, then it is connected to your smartphone, and then smartphone. This is the device that you have the ingredients that you are going to mix on your own at home. Through the diagnostics that is provided by your smartphone. And custom dose, the device that creates in real time on the basis of the dermatological evaluation a personalized serum for the client. That's all for me. Thank you very much for your attention, and now we will be happy to answer your questions.
And there are many, many questions and a lot of goosebumps in my skin for what you just presented. Really, truly awesome. Let's start with the questions right away. Ruth Nielsen from a company called Ocean Insight, one of our favorite spectroscopy companies in EPIC. He's curious about how you plan to make this technology, the technology that Benjamin presented, available for the big audience.
Well, it depends. What we like to do is to start not with a so big audience, but with the highest quality in terms of sensor, algorithm, or whatever we need to make it happen. And then we have to find a way to have it at home. And generally, have it at home means going to use only a smartphone. So we have to think about ways to complement the data that we cannot acquire, being with approximations or assumptions, or using, let's say, a data profile that the consumer would be able to fill in by going to a point of sale or something like this, so that we're able to somehow get access to the missing information.
I was quite amazed by the spot scan project. In the spot scan project, you're also trying to do imaging with the mobile phone. Is there any other hardware solutions? And if I can ask you, with your Santa Claus Christmas list for a potential cooperation?
I think we can go back to things that I just mentioned related to biology, because that's very complicated. The thing is what we are looking for, how we can detect it, how we can detect it rapidly, and whether it's going to be related to skin aging scientifically or not. So if somebody can provide us with a solution on this topic, that would be great.
Yes, and to go on with what Veronica said, we presented the Nexa project, which is quite close to what we have done on smartphones. So let's say that it's the next level of accuracy. What we want to do in the future is to bridge the gap between what we can do today on the point of sale and what we can do on a smartphone, as well as improving what we can do on the point of sale using 3D multispectral and creating this ideal capture system that will encompass all the information that we miss today.
Furthermore, so I was extremely happy when you showed this slide, because you showed this slide about biomarker quantification, and you talk about having disposable biosensors to perform ultra-fast chemical composition and diagnosis. In EPIC, we have an entire community working on definition of photonic integrated circuits for biosensing applications. Are you aware of this technology, and how do you react to this?
Say it again, what kind of technology?
Silicon photonics,
Silicon
silicon
photonics,
nitride, photonic
yes,
integrated circuits.
I am aware on this technology, and I think actually thanks to EPIC conferences, since I follow them. But as far as I know, we are not currently using it. Maybe in the advanced research, but for sure not for the customer-related solutions and on the point of sale. So that indeed might be interesting.
Well, be prepared for a lot of introductions. You also talk about multispectral and 3D imaging. And here it was quite clear that you want to really detect water. Is there any activities on hyperspectral imaging? Basically a camera in which every pixel is a spectrometer.
Yes, that's a project in progress. That's something we are actually currently working on in order to relate the image to, because hydration is usually measured by means of chroniometer. So that's still a contact device and a physical measure. And what we are looking for, and to be able to do it optically without any contact.
I organized, I don't know if you attended, I organized a fantastic meeting on dermatology with medical doctors. Of course, it was not about beauty, it was about health. But I see a lot of potential cooperations with the technology that you presented. I was very interested in that meeting about picosecond laser technology. And this slide is from the EPIC member Irisium that has been working with many...
we know them and we have worked with them actually.
Yes.
So that was my interest. Now you work with them. So what is your potential collaboration with a company like Irisium? What could you do with them?
For example, this kind of, so we said that, so it's not our department, but people that work closely with us, so work with what we can do in bringing performance without chemicals and using mechanical, optical, or electrical means to do that. And so typically, when you can bring energy into the skin by a laser, you can do a lot of things and activate a lot of biological phenomenons. And for example, you can think about depigmentation, you can think about rejuvenation and things of that sort.
You both told me offline that you are EPIC fans of the EPIC meetings, so you wouldn't be surprised with the next question. The next question is the famous EPIC question. I have 685 companies behind me, and they love working on photonics, and they would love to work with you. Tell me one specific item in the Santa Claus Christmas list for the next cooperation with L'Oreal.
Ah, that's a good one. I would tend to stay on the idea of this ultimate capturing imaging device that we try to design. But Veronica, I'm sure that you will be more biologically oriented in your answer than I am.
I would like to integrate everything inside. So if they can do both, that would be really a Christmas present.
We have one more question for you. This one is coming from Eindhoven, from the company Anterion. Askis Chailan is wondering, did you study both the skin of women and men? And are there differences?
To be honest, most of studies have been done on the skin of women. But fortunately, and you probably noticed it of one of the images Benjamin showed, today we're going forward to the skin problems of men and even related to makeup. But today I would say that most of studies have been done on women's skin.
Yes, and in terms of algorithm, we're also looking into having the best possible inclusivity. And it's true that as a lot are trained on women, it does not work for now as well on men, and that's a big part of the work that we do. And on bearded men, it's even worse, I can tell you.
I also would like to tell you that I'm a proud user of L'Oreal products. And for me, today was a fantastic experience having the two of you with me talking photonics. I will cherish this day forever. Thank you so much for making me and the EPIC community happy.
And thank you for having us.
And now from this, let's relax a little bit because I'm too excited. And we're going to talk now about the space market. And we're going to talk to the space market with a company called Quartus Engineering. Most of them in the freeform optics know them for all the activities we do with NASA in the CubeSats. This is one of the main suppliers of freeform optics for CubeSat applications in NASA. And I already met Alexander J. Halterman a few months ago, and we discussed about what can we do together. He's very well prepared for the EPIC question. Alexander, thank you very much for being with us today. It is 4:24 in the Netherlands. What time is it for you?
It's 9:24 in Milwaukee.
Good morning, Milwaukee. The floor and the attention of everyone goes to Quartus Engineering.
Thank you very much. Let me share my screen here. Is that all working well?
Gorilla Glass clear.
Perfect. Camera back on, and we should be good to go. So thank you for the warm introduction. And my name is Alexander Sheff-Holtzman. I'm the Director of Technical Program Development at Quartus Engineering. And I'm going to be talking about how freeform optics are enabling low-cost custom spaceborne science instruments, which is really exciting for us. And a lot of you might not be familiar with Quartus, so I'm going to really quickly give you an overview of who we are and our design philosophy, which lends itself to what we're going to be talking about today. And then the instrument that started this all out for us is a program called SAGE 4. So I'm going to talk about that and how we can leverage the tools and the freeform methodology from that for future instruments and how we can do more science for less money. So really quickly, Quartus is a solutions provider. We were founded in '97. We have over 100 degreed engineers, and we focus on mechanical engineering analysis, precision engineered optical systems, and industrial metrology, automation, controls, and robotics. We're in San Diego and Herndon, Virginia. And when it comes to instrument development, we can really meet you where you need us. We start at the requirements, kind of TRL1, and carry that all the way through assembly, integration, and test. And the analysis is an area that we focus on explicitly, so people can bring us their instruments and design them. And it's with this 18 years of experience for spaceborne observation instruments, starting with the Mars Reconnaissance Orbiter and carrying it through over 15 years of support with the James Webb Space Telescope on all sorts of analysis, including on-orbit jitter analysis, that led us to start doing instrument development for NASA about 5 years ago, starting with this program, SAGE 4. And that's moved into some small business innovative research work that we've been doing to take that technology and validate those tools such that we can accelerate the development of other small format imaging systems to really do more science for less money. And in 2020, we were awarded Small Business Subcontractor of the Year from NASA Langley, which is really a big honor for a lot of the work that's been doing. So again, Quartus brings simulation-driven engineering to all sorts of engineering applications, whether it's aeroelastic analysis for spacecraft and or for aircraft, or orbital analysis to get thermal environments for how what thermal loads are going to be on instruments, and then translating that into predictive modeling for optical systems and trying to be able to predict how something is going to behave in an area that it's very challenging to test. So you can take your thermal models and put it onto a structural model, and then from that you can get rigid body motion and surface figure errors to get whatever optical performance metrics you're looking for, like the spectral line width on a detector for a hyperspectral spectrometer like this. But the real question is, how can we use these tools to do more science for less money? And for us, that journey really started on the SAGE 4 telescope here. And SAGE is looking to be the next instrument for the stratospheric aerosol and gas experiment. So this monitors ozone and other gases and aerosols, and it's important for the climate model. And so what we do is we look at the sun as you orbit the Earth, going through sunrises and sunset events for the spacecraft to get absorption at different wavelengths. And that absorption translates into the presence of particular species. We have a very high signal to noise ratio, but you can only take 2 measurements per orbit. So there's a desire to reduce the cost and size of this instrument, which is currently flying on the International Space Station, the 3rd generation there. You can see in the upper right-hand corner with a couple of people standing next to it for a sense of scale. But if we can reduce this instrument to a 6U CubeSat, which is about the size of 3 tissue boxes, all of a sudden you can do a constellation of these. You can get a lot more measurements. So NASA engaged with Quartus to bring our simulation engineering approach to this. And we've developed a thermally insensitive small format imager with about a 10x reduction in size and cost from what's currently flying on the space station right now. And this is a 1 degree field of view instrument, 42 millimeter clear aperture. Optical performance is near diffraction limited at 90% in squared energy. And for this, stray light rejection is key. So any errant photons hitting the detector just manifest as errors in the data product. So we have a very folded design that passes through a lot of isolation stops in order to minimize any sort of stray light here. And of course, it's a spacecraft, so it needs to be able to survive launch and perform on orbit. And as you go in and out of eclipse, you get really harsh transient thermal environments. So we needed to have that low susceptibility to thermal variation. The optical design itself went through a series of trade studies in order to come up with the approach that that we ended up with, which is 2 decoupled 3-mirror anastigmats using 10th order off-axis A-spheres. So these optics, while conventional in appearance, are truly complicated from a fabrication standpoint and are fabricated as free-form optics. We'll talk about the fabrication methodology and the metrology techniques that we use for this, but these reductions in sizes for science-grade instruments would not have been possible without the introduction of these deterministic shaping and polishing methods that are being used for all sorts of applications currently. So how do we leverage these applications and these analytical tools going forward? So for the Sage 4, we realized at the end we just had a really nice telescope that happened to be used for this multispectral imaging use case. And it's certainly not new or unusual for companies to leverage existing designs for other instruments, but it's rare in our experience that we saw something that was so easily repurposable for future missions with a little bit of forethought. And so in 2017, when the Earth Science Decadal Survey came out, calling for a reduction of mission costs for Earth observation instruments, we saw an opportunity there for the science community to make significant gains on these low format, smaller missions, right? So if you can save a few $1 million of development across tens of instruments, you're talking significant money that allows more funding of more missions. And so we submitted an SBIR working with NASA to figure out how we can amortize this development in a way that a single program can't justify to validate these tools beyond just these mission needs. And that leads us to the validation of the optical mounts that we see here. All of these are high performance aerospace hardware mounts that can be positioned within about 5 microns in free space and 6 degrees of freedom and maintain about a 5 micron positional stability over these operating temperatures. And you can see that they're radially mounted for mirrors, so you can put transmissive elements in there going forward. But the tools that we're really talking about utilizing here are performance merit functions and macros that are elaborate in their creation for closing optical designs, operational wavefront error budgets, stray light models, which have been validated with BRDF measurements and mid-spatial frequency tolerancing for all the fabrication of these freeform elements. And then the metrology techniques we'll talk about in a second. All of that work, in addition to the mechanical tools, such as the fabrication tolerances, thermal models, structural models, all of this work is expensive to develop for a single instrument. And so if these can be validated beyond this, we can accelerate and reduce the cost of future missions and start to have families of instruments that aren't related due to what their mission parameters are, but they're related due to the design approach used to build and design the instruments. So to validate all of these tools, we've gone through kind of 2 primary goals in this, this research. One is the structural, thermal, and optical performance validation, and the other is designing the tool, or validating the design itself. And so it's really challenging for these low CTE materials to validate their performance over temperature and to validate the tools used to predict their behavior, because you've selected materials that inherently shouldn't move. So have you analyzed them well, or did you design or select the right materials? So we've created a set of correlation test setups that utilize a lot of the same design features as the Sage 4 instrument, but we put different materials in there. So instead of using a low CTE metal like Invar, we were using a high CTE metal like aluminum to throw a lot of stress into the system and get appreciable motion that we can then correlate all of our analytical models to. And then the test sets were done in two different parts. So one was the component level testing to validate each of these components that they can be repurposed for mounting other optics in the future. Excuse me. Or the system level validation of the Sage instrument itself, so that you can see how the different optical elements interact with each other. And you can see on the upper left of the middle picture there that we're focusing only on the afocal front end, which allows better thermal testing in and out of a thermal chamber with collimated light in and out. And so we talked about the complexity of these optics being, 10th order A-spheres. And so we worked with Optimax out of Rochester, New York for this project. And at the time, we were really pushing the metrology capabilities of these optics. They were completely convinced that we'd be able to fabricate them. The problem always is, how do you prove that you made it correct? And so in these, they were all fabricated as parents. And then we were coring out the areas of interest in order to use the off-axis portion that we needed. And so this was all sorts of surface profilometry relevant to reference datums, both mechanical and optical. And so all of those are used to build these up such that we can position these optics, again, in free space relative to about within 5 microns and move that going forward. So all of that process development allows us to have serious economy of scale in a way that you typically can't get in one-off space systems. So now we get to doing more science with less money. So this instrument, which you can see here on the right, can be repurposed in a lot of kind of simple ways. You can use completely different wavelengths of interest. So you can use this same design and just switch out the detector to get to a completely different wave band. So instead of using the silicon, visible and near infrared, you can get out more into the shortwave infrared or even in the longer wavelengths if need be. You can change the filters themselves so that you have a multispectral imaging system that looks at different wavelengths within that silicon band for other areas of interest, or you can remove the filter wheel altogether and just have a broadband imaging telescope with a high confidence and low risk posture going into that mission. You can also change the form factor of the detector, and then each of these are decoupled modules, so you could change the layout or format of these, increasing the aperture if you want for the large front end telescope. But then where it gets really exciting is where you see what freeforms could do, right? So if we're talking about being able to position optics mechanically in free space to about 5 microns, that gives you some idea of the flexibility that you have when you start bringing freeform metrology and fabrication capabilities to bear on this. And our ability to hold these elements in free space, you can kind of do whatever you want. You come up with an optical design, you put the mechanical structure around it, and then you've positioned all of these freeform optics in free space, allowing you to do some pretty incredible imaging systems, right? So you can take just the back-end module, taking that 1 degree field of view to a 4 degree field of view system within a really, about a 100 by 100 millimeter cube. You can leverage the mounts for completely other purposes. Instead of using reflective elements, you can use refractive elements and use it to radially bond lenses and or diffractive gratings and get some hyperspectral imaging. And then you can really get into some fun with the freeform fabrication approaches, allowing you to compensate for spherical error that you have challenges with when you get to really wide fields of view systems. You can get some low Earth orbit line scanning systems, turning that into a hyperspectral line scanner, if you will, or you can do broadband radiometry, which we're working on for another program. But we have the ability to position all of these prior to staking anything or locking it down. So you can build this up, verify the performance, and you can actually take some of the elements or add a corrective mirror or a corrective lens in there or a corrective window such that you can then deterministically polish that additional freeform on the back end to get a higher quality wavefront system, wavefront error through the whole system as well. So there's a lot of potential here. And really to meet the increasing demands for spaceborne science missions, it's imperative that we bring costs down. And what we've done here is we've taken a look at this one instrument that we built and developed and found a way to leverage it going forward. And the goal is that we can just start doing a lot more instruments with this design. But what we're really encouraging the science community to do is to explore what they can do with their existing designs and what can be done from an analysis verification approach to validate tools more than validate instruments. And if we can just have that paradigm shift, we can take a step back and look at the beginning of programs on, how can we make small tweaks to the instruments in order to heavily leverage the work that we've done in the past. That paradigm shift can really allow the limited science resources in the world to be stretched a lot further. So I just want to thank the SBIR office for continuing to fund this work. They've seen the potential here. It's really exciting for us. My contact information is here. Love to communicate with people on this, see what they can do, see what ideas they have, and see how we can, continue to do more science for less money, which, is all fun.
Thank you, SBIR. Thank you, NASA. Thank you, Optimax, all the way in Rochester, New York. And especially thank you, Quartus, for a fantastic presentation and so much room for cooperation. So I'm going to go directly to the questions. The first question is coming all the way from beautiful Karlsruhe. The company is PI, one of our key members in positioning systems. Marcus Witherspoon is wondering, are the mirrors in the instrument fixed in position, or do they need to be positioned dynamically during usage?
Yeah, no, great question. So they are all positioned, they're all static. We go through a lot of adjustments to position them in free space. But if you do have instrument requirements, you know, where that 5-micron positional stability isn't good enough, you could absolutely put in some piezos in there for some adaptive optics. You could have a deformable mirror put in place. There's a lot of versatility when it comes to adding flexibility. What we've really done is we've taken the skeleton from a structural standpoint and validated all of those tools. So there's absolutely no reason that you couldn't either have active wavefront correction, pointing correction if you know, there's more induced jitter from onboard electronics or something. You could have fast steering mirrors. There's a lot of possibility there, but this particular one, with exception of the filter wheel, everything's static.
I agree with you. I share a passion with you of it's amazing what freeform optics can do. And you are bringing freeform optics to space, which is double cool. I would like to ask you something. When it comes to freeform optics, coatings is always a challenge. Coatings in space is double the challenge. Is there any experience or any room for cooperation that you see in that particular field?
Yeah, absolutely. So Cordis is primarily a systems integrator. So we work with suppliers like Optimax from the fabrication of the optic standpoint for this instrument, and we work with coating suppliers as well. So there's a lot of work to be done. In this particular case, we used a coating that went way down into the ultraviolet. We were getting reflectivity down in a 300 nanometer range. So there's a lot of challenges there. And then again, you're going to have to verify all of that, and you have added complexities when you're working with freeform. So pushing all those test capabilities and improving the verification of those coatings, it's going to be paramount. And spaceborne coatings, you need that heritage. So you need those opportunities to fly. And one thing that's nice about this whole approach that we're talking about is that you're bringing down the mission cost. So your barrier of entry for those qualifying flights becomes a lot lower. So you can take a little bit more risk because you're saving a lot of money across all of these instruments, where you can move things forward with qualifying more coatings, qualifying more fabrication techniques, and getting that flight heritage, because everything's not hundreds of millions of dollars to fly anymore. You can get things up there for 7-8 figures.
During your amazing presentation, I was quite amazed by this slide. I was very amazed by this slide because you are claiming precisions that are typical in industrial manufacturing, but you are putting them in space under the harshest of environment, and you talk about operating temperatures. Could you tell us what is really the big challenge here, and what are those operating temperatures?
Yeah, so for these, when you're orbiting in low Earth orbit, we're kind of going between negative 30 C and 60 C. So it's not quite as harsh as terrestrial military environments. But the challenge really comes with using the low CTE materials like Invar, Zeradur, carbon fiber, and then your adhesives all have high CTE. So the biggest challenge there is balancing thermal stability with stress over temperature, because you're still going to get that stress at the bond level, and that's where a lot of the validation really comes in play from a survivability standpoint. You need to not only be able to maintain alignment and performance, you need to be able to survive those temperature swings. So for us, the adhesive bonds is one of the hardest challenges to overcome, and that's what a lot of the fine tuning and validating. You're kind of on the head of a pin for the solution that works, as opposed to having a lot of flexibility there. But we do maximum and minimum material condition analysis, and those breakout models, like to get to the point where that it's all going to survive, is really expensive. So being able to use those same interfaces and those same bonds for future instruments is going to pay dividends.
5 micrometer with 6 degrees of freedom. I love the exapods of many of our members. This is something out of this world. Is there any recalibration, real-time recalibration project? Any ideas to actually recalibrate something that has been deviated a little bit?
So in this one, you're not going to be able to, but as the question from PI illustrated, if you do have that sensitivity, you can put that active adjustment in situ. The goal here was a passive system, but when you've got tighter requirements, you can, or you have recalibration needs, you can put that in place. And that's, you know, added cost for lower risk. So you just need to play the balance game there on what makes sense. And as you bring the cost down of the instrument development, you can more easily afford that, you know, you shift the risk to, well, what if it moves out of alignment? Okay, well, this was so cheap to do, let's just put on a you know, space flight compensator and you're in good shape.
In Epic, we have technologies that cover the entire supply chain for optics. One of our companies in metal optics is Space Optics. And Matthias Bayer has a question for you. He said that you were mentioning an aluminum alloy for the mirrors. Can you detail that and have the mirrors being nickel coated?
Good question. So for this one, the mirrors are actually zero door. We're using aluminum for the validation models. But these are all zero door. We have other instruments that we do use aluminum for, and generally those need to be nickel plated in order to get the form factor. There are some polishing techniques out there for aluminum which are coming along, which are great, because then you don't have that bimetallic effect that you get from nickel and aluminum over the temperature ranges that we're talking about. So yeah, I hope that answers the question.
If you're ever looking for metal optics, Space Optics, or Sonex, they are great companies. I will be more than happy to make an introduction.
Yeah,
but it has
always.
been such a fantastic chat. Thank you so much for connecting all the way from beautiful Milwaukee. And I would like to come soon and visit you. I want to come and visit you. I can't wait to start traveling again.
I know, same. Soon. Looking forward to it.
We close this fantastic session. Oh my God, I got goosebumps with the presentations from L'Oreal and Quartus. We close this fantastic session, and now we take a little break, only 14 minutes, for all of you to go to the networking area, this virtual networking area, get to know each other better and do some business, at least make some friends. See you exactly at 5 p.m.
Thank you.
Is here as the General Manager for Photonic Integration at Intel, and we want to talk to them about their activities on co-packaged optics, on CPO. Thomas, thank you very much for being with us today. It is 5 o'clock in the Netherlands. What time is it for you?
8 a.m.
Good morning. Let's have a coffee together. The floor and the attention of everyone goes to Thomas, goes to Intel.
Great. Thank you, Jose, and thank you for the opportunity to speak here today. I appreciate it. We're always happy to share our work and our view of where we're heading with co-packaged optics. So my name is Thomas Liljeberg. I'm with the Silicon Photonics product division at Intel, as Jose said. And I'll speak about co-packaged silicon photonics or co-packaged optics in the context of Ethernet switches, and go through where we are, what we've done, and where we see things heading in that area. I have completely left out the obligatory chart showing how fast traffic and data is growing. I think we've seen that enough. We've all made that slide and presented that slide, so I'll assume we all agree. But that explosive growth in data is driving also an aggressive cadence on switch bandwidth. And we've seen for multiple generations now, and looking ahead multiple generations, that every 2 years the switch bandwidth will double. So it's attempting to keep up with that explosion in data. Now, the I/O technology, the SerDes, is not doing quite as well, I would say. And so it's more of a 3 or 4 year cadence to double the bandwidth. And the math of that drives that we're seeing more and more pins. We're seeing more and more challenges breaking the bandwidth out of a package, out of the silicon and out of the package. We're spending more and more energy on I/O versus the actual switching action and the actual interconnects, taking away power also from the value-add compute of the data center. So we have a scalability problem as we're looking ahead, and it's not as much running into a wall. It's more climbing up a steep hill, and it gets more and more uncomfortable. And at some point, the model breaks. So what is the answer? Well, one very compelling answer is let's take the front plate optics that we've gotten so used to and pull it inside the switch package. And we achieve a number of things by doing that. First and foremost, we take away this energy overhead of moving bits from out of the package and across a board onto the optical pluggable on the front plate. So that gives us a much better channel, lower loss channel, that allows us to have a lower power I/O on the switch and on the optics for that matter. So we reduce immediately here the non-value add power of the interconnect, if you will. We also get higher density. We take away any and all retimers that we may have on board to even get to the front plate, and we're seeing increasingly that as we go 50 gig, 100 gig, 200 gig out on the horizon, that we're going to need these retimers. And by moving inside the package, obviously we take away the power and the cost of the retimers. And then integration, the Photonics will be more cost effective ultimately, and the system implementation also becomes simpler, and that drives the cost reduction. So we think that this is really an enabling technology to sort of break the constraints of copper and front plate optics, and enable this continuous scalability of bandwidth in the Ethernet network. So we've talked about this for years, and it's always been this thing out there on the horizon. It's coming. We all know we need to do it, but like always, the sort of incumbent technologies are great at bringing out one more generation of life before things break. So we went last year, we built a demo to kind of highlight the fact that we're ready as an industry, and then also as a vendor, obviously, for Intel. The technology pieces are there, the capabilities are ready for us to go do this. So this was supposed to have been on the floor at OFC, but alas, it never made it out of the lab. But we did build a live Ethernet switch. It was designed around 25T in terms of bandwidth. Ultimately, it became a 12.8T because that's the silicon that was available in time to build the demo. So what you see here in the picture is a full functional Ethernet switch, 12.8T to Pheno 2 switch ASIC sitting under this retention, shiny retention piece of metal here in the center. There are 8 sites for co-packaged photonics, built in chunks of 1.6 terabit per second photonic engines. We've populated here in this configuration here 4 of them, the 4 in the back, and you can see they sit also under the retention mechanics with heat pipes coming out, pulling the heat out to these fan stacks out here on the side, fiber coming out the back routed to the front plate, and then we have optical connectors on the front. The other 4 sites in this setup here is we're using flyover cables. So we designed this that the same socket, the same landing site on the package can either accommodate the photonic engines, or we can plug in flyover cables. So we enable still to have front plate sockets if there's a need for that, or copper back planes, or whatever mixed kind of configuration that's of interest to a deployment. As mentioned, this was designed. If we have photonics on the all 8 sides, you would see 2 more of these copper blocks here and heat pipes pulling out from the front 4 sites as well. What's also not shown in the picture is the big center copper block that sits on top to manage the heat from the switch. So in this design, we've created separate thermal zones, so we don't have to maintain. We're not letting the very high power dissipation hot switch heat up our photonics. They sit in separate thermal zones. Everything here was built to be compliant, so compliant optical interfaces and the electrical channels are also built around standards. This is capable of excess of 1.2 kilowatt. Like I said, it was designed for 25T, so thermal solution as well. Now we're not in or intending to get in the business of building switch systems like that. This was really to show that technology pieces are ready, and we can put together something that's entirely manufacturable that would support this finally bringing co-packaged optics to life in a commercial way in the market. So I'm going to spend the next part of the talk here to peel layers off and show what's under these shiny plates here in the center, and then how we actually implemented the photonic engines and the co-packaged optics. So first layer of that is you see a picture here of this photonic engine, 1.6 terabit per second. This is about the size of a quarter, so just over 20 millimeters across. Bigger than it would have to be because we built with the silicon available at the time. This was really a technology demo, obviously not a product. So it's not as small as it could be. But even here at this size, it represents a 40x improvement in bandwidth density over 100 gig pluggable, and a 30% improvement in energy efficiency by bringing this together in this highly integrated fashion. So this was the first step towards sort of a commercial photonic engine that can support co-packaged optics in volume in the market. We're iterating on that to bring it denser, and I'll show towards the end of the talk, or highlight at least that we're now seeing more than 2x the bandwidth in something that's even smaller than this. Performance was great. Also, I'm showing here 100 gig channels. So again, this was built around a 100 gig per lambda standard interfaces. You can think of it 1.6T as 400 gig DR4 ports or 16 DR1 ports. And we believe that this is the first full demonstration of an actual compliant link based on microring resonator transmitters. So that's a key enabling technology that I'll highlight in a later slide in order to get to the density and the power efficiency that we needed. So great eyes at 100 gig across all the channels that we see here. We have to show 8 of the ports. Receiver, no airflow, at least not airflow above 10 to minus 10 prefix. We hooked this up in our lab, looped back through a commercial pluggable DR4 plugged into an off-the-shelf commercial switch, and we're able to run error-free post-fit for more than 4 days. We were able to keep this setup sitting there. Right when COVID started, we're a little bit constrained there, but very stable, very great performance, and very encouraged by the status of the Photonics to support sort of a productization here. In the build we did last at that point, the TX and RX was separate. So I'm showing here a 1.6T transmitter die, more complex of it. We were doing that as test chips, if you will, and we had a separate TX and RX. As we productize these things will move on to a single die with both TX and RX. But looking at the TX die, we had 32 lasers or a 2x16 laser array to support 16 channels, and that's done. This was full 1-to-1 redundancy in order to mitigate any reliability concerns when you put 500 or 1,000 lasers in a separate assembly. Obviously, reliability becomes brought to 4. So we put full redundancy in here, and I'll talk about what that means for system level reliability. We have a bank here of 16 2x1 switches to pick which of the 2 lasers, the redundant lasers that we're running active. The microring resonators, array of 16 of those, capable of 100 gig PAM4 modulation with integrated heaters for control and temperature compensation. We had integrated detectors, 48 of them scattered around here to control power and control the bias point of rings. And then on the output here side, at the 5, we have mode converters to match the fiber mode, and then SV grooves to enable a high volume friendly passive fiber alignment, and that's something that we're working on bringing out as a way of scaling things and dealing with the large fiber count here. So this was, as mentioned, a DR4 or a parallel single wavelength iteration, and I'll show how we're making that into a support of the WDM kind of performance. I want to stop for a moment. I think maybe most people know that at Intel we had sort of the unique capability of putting lasers and amplifiers and gain material onto our silicon platform, and that's a great enabler for a lot of things. You always have to be careful that you don't assume just because you have the coolest tools that it's always the right tool to apply here. So we do want to be smart about, is it the right thing to put the laser on the chip, or should we bring the laser outside to an external source? So we looked at that from a different angles here, and clearly from a reliability and serviceability, we're absolutely convinced and have data to back it that we get better device reliability with the on-chip laser. But we're now also working with a field replaceable unit of a 50T or 100T switch. It's obviously a serious thing to have to pull out and replace. So we have to deal with the serviceability, and clearly the remote laser has a sort of obvious field serviceable answer. And we dealt with that with redundancy, and I'll show in the next slide or so what that looks out to. Power dissipation with the effective coupling efficiency of more than 90%. Compared to an external laser that needs to go through at least 2 fiber couplings. We're at least half, or there's at least twice the power dissipation in the laser for an external laser, and so that's clearly an advantage. And one of the big reasons for doing all this is to reduce the total power dissipation. So we want to get out every single picojoule per bit that we can. That said, it is lower power, but it's also more power at the inside the package. So we get a higher power density, higher thermal density for the package. We believe that that's a price worth paying because the increment is really less than 10% of what's in the package already. But clearly, that's a factor to take into consideration. And then cost, the wafer scale manufacturing of the laser really is hard to beat as long as we can maintain the high yield that we have. There's no PM fibers to align. There's no laser back-end processing, coding, testing, burn-in. It's all done at wafer level, and we have this great known good die that come out of it. No gold boxes, no text, and so on. So there's a number of advantages, and for based on sort of the consideration in this slide and some of the points I make here below, including eye safety and manufacturability and testability, we're moving forward with the on-chip laser, and believe that that's the best answer that we can provide. Now, it should say that we have concept drawn out, and we're quite convinced that it's quite possible to design a single platform that can accommodate both external and on-chip lasers, so they can coexist in the market, and then they can play out there. Performance of the lasers are clearly compatible with the integration, and what we see here is shown data before that up to 200 C and even beyond, we can still deliver the power that we need to close links and at an efficiency that's consistent with the power efficiency that we're trying to hit on the overall product and assembly. I want to dwell a moment on reliability. We have a ton of stress data, and really, if I have to synthesize, I can see here I'm running very late on my clock here. We have data here more than 3 years of aging. We have more aggressive cells that are beyond 3,000 hours, and really what it shows is that the lasers barely move. They're very stable, rock solid, and we're not concerned in the context of the lifespan of a data center deployment. We're not really concerned about wear out mode. We have more than 4 million modules in the field now, most of them with 4 lasers for CWM4, and we're getting data now that we can say in terms of random failures, we're below 2 fit failure rate on lasers. So also from a random failure rate, it looks great. But we're proposing now to put 500 or eventually 1,000 of these inside. So even at 2, or if we sort of hedge and saying let's assume it's worse than what we're seeing, even 10 fit, we get into areas where the overall failure rate is too high just by accumulating that many lasers or aggregating that many lasers into one assembly. On the other hand, as soon as we introduce the one-to-one redundancy, we get 4 orders of magnitude roughly in improvement. And the laser-induced failure rate, we now have a fit rate of 0.1, which corresponds to 1 in 1,000 switch system will fail because of the laser in 10 years. So I think this is certainly in the acceptable range, I would say, from a total assembly point of view, and much better than you could hope to do with a pluggable or any kind of that type of technology. So with the redundancy, we really don't have a concern on the reliability of what we have here. We've shown the high-speed results of our modulators before. I'd say what made great performance at 100 gig. You saw that earlier also on the results page. We've also done some device-level testing and looking at control
Thomas,
loops.
we are having a bit of problem seeing your slide, and I am so amazed by what you're doing that I really want to make sure that people can actually see it. So let's try. Don't worry about the time. People are at home. We didn't travel today. Unfortunately, we cannot go for dinner tonight, so we are okay. So let's try to share the screen again. And also, we'd like to congratulate you on the hybrid laser. It is out of this world, the work that you're doing there. Okay, back in business. The floor is yours, Thomas. Can you also share your camera? Switch on the camera, please.
Yeah.
Fantastic, Thomas. The floor is yours.
Yeah, I don't know why it dropped. I'm trying to not touch my keyboard, but hopefully you can see now. So again, we've shared before, and I showed the 8-channel results on 100 gig modulation of ring modulators. I think we have great performance here. We have not yet published, but we have now devices in the lab that makes us very comfortable to look ahead to sort of 224 gig PAM4 with the same kind of structure optimized and designed for the higher frequencies. Now, what we haven't shown as much is the device level testing on the stability, and we've put these control loops and the control scheme through pretty aggressive temperature gradients all the way up to 45 degrees per minute, also ranging across 85 degrees span. And what we see is that we see no burst of errors, no post-effect errors that come through there. So we have pretty good confidence in the control scheme and our ability to operate these modulators even in a pretty aggressive thermal environment. Let's see. So this was a lot of what went into the demo and what has been in the works up to now. What we're really working on now is obviously the next generation and what goes into a product. So we're taking everything we learned from here and sort of the improvements we made along the way. And what we're building now is a 3.2 terabit per second photonic engine. We're folding in WDM technology that was sort of developed in parallel with the integration work, so that we're ready. And we have sort of a high-level floor plan I'm showing here on the right-hand side. So 4 wavelength lasers. We have the same redundancy I spoke about earlier. We have selector switches to pick which of the redundant lasers we're activating. We have a wavelength, a waveguide swizzle, so that we can group these in 4-way groups of all 4 wavelengths for each FR4 link, if you will. We'd like to keep the lasers sitting this way in this kind of grouping, so that we can leverage the way we apply the gain material muxes, and then on the receive side we have polarization control as well, so we can manage to unknown incoming polarization. So this is what's in the works right now. We're packaging that with 16-channel 100 gig SerDes to build this 3.2 T engine. As I mentioned, it's actually smaller than the 1.6 T engine that I showed earlier, even with 3.2 T. And we're doing everything we can to align with emerging standards. So to the best visibility we have now, this is built to be compliant with where both OIF and the co-packaged optics collaboration is heading in terms of requirements. We do absolutely in support and want to contribute to development of this multi-source ecosystem, healthy, vibrant ecosystem, as a sort of prerequisite for this being widely adopted commercially. So this is in the works, and this is what we're seeing and looking at in the lab right now, in terms of devices and next generation. So very brief summary. I think that we certainly have the maturity on the high level. The platform, we ship more than 4 million units now, and we're deploying that same technology into the co-packaged optics. We think this is a requirement to address these scalability issues and get the right cost and power to continue to scale the bandwidth. We're committed to a healthy standards-based ecosystem. We think that's like I said, requirement for successful market adoption. And the thing with the demo we did last year and that I went through today, we've really highlighted that we're ready to do this. We've talked about it for years now, but all the technology pieces are ready and in place, and it's a matter of putting it all together in the right way that fits our customers and end users' requirements. So went over time. Apologize for that, but thank you for your attention, and I'm happy to take questions too.
Thomas, after this presentation, you should never apologize. Thank you so much for the great information you have provided us. As you may be very well aware of, I am taking co-packaged optics as the next challenge for the photonic industry, and we are organizing set of meetings every month. In the next one, for those who want to join, it's on the 3rd of March, and we already have confirmed Intel, Thomas will be there, Facebook, Microsoft, Ranobus, and Broadcom to try to match what they are doing to opportunities in photonics. One thing that raised a bell on me when you gave the presentation was when you talk about the passive alignment of the fiber. So I would like to share with you one slide from our previous meeting on CPO, on co-packaged optics, and we had a speaker from Ficontech. Actually, the CEO, Torsten Varenkamp. Torsten, if you're watching, hello. And here we really have to understand a little bit where is the market going. On one hand, of course, you talk about the passive alignment of the fiber because of cost and price. On the other hand, there are, of course, lots of different advantages on having active alignment. Have you considered this potential alternative? Is a decision being made? Is still up for discussion?
So what we're building right now is building to enable passive alignment, but there is no, and I would say our results are very promising for the ability to do that and to deploy that into volume. But I would say there is a broader effort looking at sort of longer term. What is I'd say it's not an irreversible decision, or it's not something that can't change over time as we learn more. But right now, that's our plan to go ahead with.
We have a comment in the chat from a very promising startup, Lumiface. They are very happy with the way that you're presenting the hybrid laser, and they would like to see if you are also still working on other different alternatives, like for example the flip chip, or is this really the technology of choice, the hybrid silicon laser?
So we're always trying to check ourselves and not so that one single technology piece does not become religion. And clearly, if the market direction or if other applications have different trade-offs, we have looked at how we would build the external laser. I don't think we would be likely to pursue sort of a concept of building a laser and then attaching it to the die. That seems to be a step back from where we are with the integration we have right now. But certainly a completely remote laser is absolutely within the capability and possibility for certain applications.
You remember the space race that was nice between the US and Russia, beautiful times? I think there is another big race coming. I also have a slide to share with you to see what you think. I think there is something big happening right now for the 200 gigabaud channels. If we go to 800G or 1.6 terabit, and I know you talk about 400G as being tomorrow, but I always look at the day after tomorrow. We need 70 gigahertz modulators, and I see a lot of really amazing technologies, like the technology that was presented by Nokia Bell Labs at ECOC before COVID, that it was really fascinated by the plasmonic structures. I also saw, as I said before, the technology of polariton, also based on plasmonics. I also saw a technology of Lumiface using BTO material. There is lots of things happening. Where do you stand? Does it make you as excited as it makes me, this new race for 200 gigabaud channels?
Yeah, so I think as I highlighted, and we'll publish fairly soon some of our results, but we have with an extension of sort of the current technology with microring resonators, we have pretty good line of sight to supporting 224 gig PAM4. How much beyond that we can take that technology, I think is maybe more questionable, and we have people looking at these alternative technologies, but not a committed strategy or direction, or at least not something we can talk to in any detail at this point. But I think the next generation, sort of supporting the 100T switches with 200 gig channels, I think we have a good line of sight with building on and extending what we have already.
Intel joined EPIC, and since then we have made so many introductions of potential technologies that can help Intel. An amazing success story, being even amazinger. Thank you so much, Thomas, for a great presentation, and thank you, Intel, for being such a great supporter of the little thing that we are trying to achieve here at EPIC.
Thank you. Thank you, I was happy.
Have a fantastic day all the way here from Europe in the afternoon, all the way to Thomas in the morning. There is no better way of closing this event to going into my dream, which is merging photonics and semicon technology. And for that, our closing speaker today is from Global Foundries. Global Foundries is investing heavily on silicon photonics, and they want to really understand the technologies of the photonic industry that can be suitable to the volume productions that Global Foundries is going to enable. And for this, we have Anthony Yu, Vice President of Computing and Wire Infrastructure at Global Foundries US. Anthony, thank you so much for being with us. Thank you for taking the place of the last speaker of today's session. It was a fantastic session with L'Oreal, with Intel, and now we go to Global Foundries. The floor and the attention of everyone. 400 people watching is yours, Anthony.
Very good, very good. First of all, Jose, can you see my screen?
Gorilla Glass clear, but I would like to also see you. Could you switch on your camera?
Okay.
It's so beautiful when it goes like that to the infinite. Let's see.
How about now? You should be able to see me now and the screen.
I actually do see a black spot. So if your camera is off for whatever reason, just don't worry about the camera, switch it off, and let's start with the presentation.
Okay, very good. So first of all, thank you very much for inviting me to speak here. I was in your networking rooms yesterday, Jose, and it was a lot of fun. There was a lot of energy in the room, and I was very pleased to be here and to talk briefly about GlobalFoundries silicon photonics. The last speaker was really exciting, and I agreed with many of the conclusions, if not all of them. We are as I discovered yesterday in the networking rooms, there was not a wide-scale recognition of GlobalFoundries. So let me spend a couple minutes talking about who we are. We're the third largest silicon foundry in the world, with fabs in Singapore, Germany, and in the US. I am speaking to you today from my home in New York. So I am based in the US, where we have two fabs, two 300 millimeter silicon fabs that are currently building silicon photonic foundry wafers for a variety of customers, including several people that are probably in the audience or co-speakers as well. We have pivoted our strategy in 2018 away from the conventional semiconductor technology, which is chasing after the attainment of Moore's law, smaller and smaller optical lithography. We pivoted to a direction of differentiated technology, which has resulted in us investing a considerable amount of research and development funding and capital into photonics, silicon photonics, with a mission to bring optics to wider scale adoption. That your audience is highly skilled in this area, and many of the points I'll make on this chart are self-obvious to the audience skilled in the area. But from a manufacturing standpoint, it's a radical departure in terms of making a CMOS-based factory capable of building light-based chips. So we had to change the vernacular, the vocabulary of our manufacturing, and move people away from building transistors and diodes, resistors, capacitors, and bringing signal on and off the chip using things like bond pads and solder bumps. This goes back to our topic of co-packaged optics, and move them to a new technology discussion in terms of bringing light on and off chips, using modulation and detectors, using waveguides to control the light and manage the link budget. And over the last 4 years, we have now installed a process in our 300 millimeter fab, which differentiates itself from the conventional 3.5 technology by bringing high volume manufacturing, high volume PDK deployment, high volume testing, and ultimately bringing lower cost and of course lower power consumption. Everybody is well aware of the fact that this horrible pandemic has actually accelerated the digital transformation. And so we find ourselves in an enviable and yet very challenging situation where we face now unprecedented demand driven by 3 megatrends that are driving the uptake of photonics. The uptake of photonics because of the need for higher bandwidth, low latency connections, and of course, low power. And it's well known that within the cloud, power is becoming an absolute requirement to stay within the envelope within the data centers. So driven by 3 megatrends that we call frictionless networking, which you can think about as the uptake of computing power from the core to the edge, driven by things like virtualization, which requires the interconnect of computing, storage, and memory, and driven by the rapid gains in hierarchical artificial intelligence. Our technology in photonics, as we launched this business in 2016, has just exploded into 2 main technologies. One of them, 90WG, which is in production today, 90 nanometer, and then a developed process that we expect to have in production at the end of this year based on the 45 nanometer node for RF CMOS. The point that this audience has seen, though, is that photonics over the last 4 years, demand is exploding, and we see the base of photonics in the data center as you look at the migration from 40 gigabits to 100 to 400. We're seeing aspects of that technology from a foundry perspective start to move into adjacent spaces. In addition to 5G and telecom, we are seeing photonics, particularly at 800 gig, be reused for chip-to-chip interconnect. i.e. co-packaged optics, i.e. in-package optical interconnects, but we're also seeing the deployment of many of the features that we see in these other bases into areas like time of flight LiDAR sensors, both for cars and in mobile phones. So the message here is that we believe that by driving photonics into high-scale manufacturing and driving down costs, we can help accelerate and bring a wider scale adoption of silicon photonics into adjacent spaces. Jose, I liked your aspect of a space race, because I think that the long-awaited uptake of photonics into the market, I believe that we're at that inflection point now. So Global Foundries, we've introduced a 300 millimeter technology that we believe is unique. Again, Thomas gave a really nice description of some of the things they're working on. Again, we are not a product company, we're a foundry company, but within our PDK, we offer many recognizable optical components that designers can pull from, and then we build in our 90 and 45 nanometer technology. Very quickly, starting at the 12 o'clock position, we have a currently production multi-center modulator technology, which is happily serving the 100 and 400 gigabit optical transceiver market. But we are, like Thomas indicated, we are moving toward ring modulators as well, bringing about lower power, much smaller structures, and ultimately probably will be deployed for areas for co-packaged optics.
Anthony, this presentation is fascinating, and that's why I'm going to ask you if you could switch off your camera, because we have a black spot which is covering perhaps the most interesting part of the slide, and I think it is a pity that we're missing that. So just switch off the camera, and let's continue the presentation. Sorry for that, but I really want people to get this, because it's a really huge room for cooperation here.
You know, my camera says that it's on. Do you not?
Just click on the icon with. Now it's perfect. Thank you so much.
Perfect. Okay, very good. So we have ring modulators. We have experience with our silicon germanium technology, which we have in production, which allows us to have high responsivity germanium epi photodiodes built in the waveguides. We build all the waveguides that you would expect our customers would look for us: rib waveguides, bends, tapers. We do phase shifters, both standard and undercut, for low power optimization. We have polarization splitters and rotators on the receive end. We feature direct laser attach, mainly for our optical transceiver modules. I agree with some of the previous speakers. I think for co-packaged optics, we're looking at off-chip lasers in terms of comb lasers, for example. And then again, I was very keenly interested in Thomas's presentation. We have a V-groove-based passive fiber attach that we are putting into production. It's a tricky process, and we're going to really be testing that technology as you move to wide fiber array ribbons. But a differentiation really is on the left-hand side, because what we've done is we have monolithically integrated RF CMOS onto the same chip as photonics, and that is the feature of our monolithic EO integration. Very quickly, we have EDA partners that allow us to put these photonic P cells into the PDK, allowing you to pull down the active and passive components that you want, lay it out in electrical optical designs. We validate all these different P cells, much like the ASIC model. We validate it with hardware models. We give ease of layout, trying to advance the first time right probability of the designs. We have inline tests, and we have a virtuous circle, which is trying to allow, again, the uptake of photonics into mass production, into high yield. There's a lot of detail on this chart here, but just look at the very bottom. Over the last 3 years, we have inline tests. So those of you, again, familiar with wafer acceptance criteria, we have inline tests very quickly. Over the last 4 years, we've done 31 million optical inline raw optical measurements, which once you de-embed them, for example, we have over 7 million data points on active components. If you squint hard on the right, you'll see the types of things we measure are waveguide loss. We can measure a modulation frequency. We can measure phase shift rotation. We can measure the typical components that you'd want to look at, but we're doing it inline in the kerf. And so we were able to compile a very tight process distribution of these parts within the foundry. Now, switching quickly to co-packaged optics, again, I just have a few minutes left. Again, the main features of our foundry process, which is driven by our foundry customers, are monolithic RF CMOS. So as opposed to having separate RF chips for the TIA and the driver, for example, we're putting it onto the same chip as the rest of the photonics. Obviously, that simplifies the packaging. You go from 3 chips to 1, but you also get significant advantage putting the TIA that close to the diode, and you eliminate the need for ESD, and you have very low input capacitance, which allows you to have very high TIA bandwidth, for example, with our 45 nanometer process. In the middle, you see an example. Jose, I liked your previous slide there. Here's our example of a fiber block attached to a chip there, again, using the V-groove fiber attach process. It's tricky to scale it from the few fibers per few fibers per chip you have for optical modules to probably an array of 16, 24, maybe even 32 fibers for co-packaged optics. So we'll have to make sure that you can reproduce every one of those fibers into the V-groove cleanly with low dB loss per facet. And then on the right, you'll recognize, again, resonant from previous speakers, an example of a micro-ring resonator married with also the inclusion of copper pillars and copper receive pads. Why is that important? That's important because like the rest of the industry, as a foundry, we are moving in the direction of our different customers who are operating to the OAF standard and the CPO JDF. And so we have different customers. We have way more than 4, but I'm giving you a flavor here of the different approaches that people are taking within the industry to respond to these specs. So you see a different amount of fiber accounts per PIC. You see most people using our passive fiber attach, people doing on-chip and off-chip lasers, and doing a full array of packaging to support the CPO spec. So my point to this audience, though, is that as I described, this is my last chart, from a foundry standpoint, we have focused more on the PIC chip. So we're focused a lot on making sure that you can get light in without a lot of loss, and get light out without a lot of loss. And those are very simplistic, but very important technological things. The real trick, though, is integrating this within a co-packaged optic, within a economically based package. So we find ourselves developing multiple technology options in response to the JDF spec and the emerging standards that previous speakers were talking about. The problem is it's creating a very inefficient situation for us in the foundry. While we are spending a lot of R&D money on this, it's probably not the most efficient way because you're looking at mixing 2.5D, 3D, on-chip laser, off-chip laser, passive or active fiber attach. All these options are necessary to exercise, but are probably slowing down the adoption of co-packaged optics. And so I have been talking to different people, and I think other people agree as well. This might be an appropriate time, Jose. In fact, you could influence this as well, to look for some sort of consortium, much as like what we did in the CMOS industry, which is where I come from, to consolidate the different technologies and approach a standard that's more manufacturing based. The sooner we can get these solutions into the data center, the better we can all realize the benefits of co-packaged optics, high bandwidth, low power, and low latency, and move the industry forward. Right now, as a foundry standpoint, we are faced with great inefficiency, and we'll probably, my prediction is packaging for co-packaged optics will actually gate the implementation more so than the photonic technology. So I thank you for your time, Jose. It was a pleasure speaking to you. My email is on the slide here. I am anthony.u @globalfoundries.com. I look forward to hearing from your audience and from yourself.
Anthony.u at globalfoundries.com. It was such a pleasure talking to you. In 2016, I made one life dream come true. I went to Singapore and I visited Global Foundries in Singapore. And that was an experience of a lifetime. And I really, hearing you talking about silicon photonics like that, it is really fascinating. So let's see how we can work together. The first thing that you mentioned is that you want a private-public partnership on photonic packaging. There's a logo here behind me which says PIXAP. So in Europe, we actually enabled a public-private partnership for packaging of photonic integrated circuits coordinated by Tyndall National Institute. Peter O'Brien, if you're watching this, hello. I would like to formally introduce you to them because definitely you would be a great addition to this public-private partnership.
I would welcome that. I have great respect for Tyndall and their manufacturing platform, and I would welcome that, Jose. That would be terrific.
Furthermore, okay, let's talk. You talk a lot about packaging, and I love packaging. But you know, I always say there is something called the elephant in the room, which is the testing. Nobody wants to talk about it. But you Global Foundries wants to talk about it because we did organize an event on peak packaging. We had a speaker from your fantastic company showing us this beautiful, beautiful slide. And this slide shows that you got it all figured out. And I'm quite amazed by this. Could you tell us a bit what you do in silicon photonics wafer level packaging?
Yeah. So I think ultimately for co-packaged optics in particular, Jose, I think we're going to end up with more of a passing on of good die onto a packaging house in order to put it together. But this chart is one that's familiar to me, and you saw the data that I talked about, which basically mentioned the first two on the left-hand side. So as we develop the technologies, we do the technology verification, which fed into the chart that I showed before, where we do hardware-based models. We validate the performance of it, control it within a normal distribution of manufacturing, and then we verify that. So that's what the one on the far left talks about. Inline optical test is what we try to use to validate the yield expectations relative to wafer acceptance criteria. That was the one where we have, for example, made 31.4 million measurements to date. The rest of them on the far right-hand side are more or less used on a lower level of volume than the first two. We do have the ability to measure packaging, package parts. We can actually measure modules. We do that on occasion for our customers, but in general, most of our PIC foundry work is restricted to testing for the first two columns on the left.
Anthony, this is an EPIC meeting, and this is all about cooperations. I would like to ask you the EPIC question. What kind of challenges, what kind of collaboration opportunities, low-hanging fruit you could see with the other 685 members of EPIC?
I think we need, as I said, we need to kind of work together to help standardize, get clarity on the standards for co-packaged optics. I think I'd like to see more of a collaboration with the various tool vendors, such as what you have with Tyndall and Ficotech. I think I'd like to see the industry work together while still allowing people to differentiate at a product level, but come up with a low-cost solution, because at the end of the day, the cloud providers are very cost focused, and they will not be adopting these complicated packages if they're economically not viable. So I'd like to see people work together with a tool, foundry, and user level, and to move this whole thing forward. It will take that level of collaboration.
I have a lot of EPIC members in the chat asking for questions, asking for cooperations. Let's select a few. The first one from Kasruge, Physik Instrumente, PI, Marcus Witherspan. How many optical test points do you typically have on a wafer?
We have about 25 macros per wafer. Per chip. I'm sorry, 25 macros per curve per chip.
The second question is, fantastic. The second question is, a big group manufacturing process seems to require lots of manual handling. Is Global Foundries looking for alternative processes?
I think we have to look for alternatives. I think it's one thing to do this on a per fiber basis and demonstrate the loss per facet, but I think we should continually explore the need for different means of passive alignment. So we are definitely always looking for alternatives and manufacturing improvements.
There is a question in the chat that is out of the scope completely, but I'm going to ask because I'm curious about your answer. From University of Missouri, Columbia, Nanda Kasani, which potential devices in my daily life can be replaced by silicon photonics technology?
In your daily life?
In her daily life.
Well, in daily life, if you're watching that, you're calling from Missouri, so you're probably at home in a pandemic watching lots of movies. I think there's a high bet that if you want to watch your undisturbed Netflix or Hulu, you're using probably a Photonics device today. 5 years from now, 5 or 7 years from now, as you're driving to work in your self-driving car, that may very well be controlled by Photonics relative to your LiDAR. So I think Photonics is probably touching your life right now if you're in the US in the pandemic, and it will touch your life even more in the coming 5 to 10 years.
I want to make a second life dream come true. I want to visit you in the US. As soon as I can travel again, I can't wait, Anthony. I want to visit Global Foundries in the US.
We look forward to that. And in the meantime, thank you for letting me speak to your team today and to the audience. Everyone stay safe and stay healthy. And Global Foundries is looking forward to working with every one of your 600 members.
Thank you very much, Anthony, for this. This is the end of an amazing 2 days of collaboration. We took the challenge of going to the end users of Photonics and asking them for potential interest in working with the photonic companies. It was great to talk to companies like Volvo, like L'Oreal, like Valeo, and today Global Foundries, Intel, all of them looking for cooperations with us. Photonics is driving the world, and I am having so much fun seeing it happen, seeing it reaching the LiDAR industry, seeing it reaching the biosensing industry. Today, L'Oreal was talking to us about optics. This is how far Photonics has gone. Thank you very much for fantastic 2 days. We are not over. You can still go to the networking room and get to know each other better. It is all about making friends, creating trust, and starting new cooperations. Until the next time, this was Jose Pozo. Take care of each other. Wash your hands, wear a mask. I can't wait to start traveling again.
Very good. Have a good day. Bye-bye.